The Undivided Universe. An Ontological Interpretation of Quantum Theory. D. Bohm and B.J. Hilley. Over the last 20 years or so, David Bohm and I have spent many hours discussing the main theme of this book, namely, whether it is possible to provide an ontological interpretation of quantum mechanics, an issue that has been fiercely debated since its inception. It was quite clear from the outset that it was not going to be possible to return to the concepts of classical physics, and we found it necessary to make some radical new proposals concerning the nature of reality, in order to provide a coherent ontology. The results of our deliberations form the content of this book. Just as the final touches were being put to the manuscript, David died suddenly. The week before his death we had a series of meetings in which a few outstanding questions were resolved. Indeed, in our last meeting David expressed general satisfaction with the final draft and was anxious to proceed quickly with publication. I have included the results of those discussions, but have resisted the temptation to make any significant alterations while preparing the final manuscript. I hope this book will be a fitting testimony to this very radical and original thinker who rejected the view of conventional quantum mechanics, not for ideological reasons, but because it did not provide a coherent overall view of nature, a feature that David felt an essential ingredient of any physical theory. It was like Escher's The Waterfall, a fascinating picture in which region by region appeared to be carefully constructed and consistent, but when one stepped back to perceive the whole, a contradiction was there for all to see. Indeed, the most radical view to emerge from our deliberations was the concept of wholeness, a notion in which a system formed a totality whose overall behavior was richer than could be obtained from the sum of its parts. In the ontological theory that we present here, this wholeness is made manifest through the notion of non-locality, a notion that is seemingly denied by relativity. Yet there is no observational disagreement with experiment. Nevertheless, non-locality does not fit comfortably within a space-time structure that is Thalian as a priori given and described by a differential manifold. Thus in the final chapter we present some radically new ideas which tally us beyond the present paradigm. It was these ideas that David and I were anxious to develop further. Unfortunately, his deep perceptions of these new possibilities will be sadly missed. Finally, I should like to warmly thank all our colleagues for helpful discussions. Particularly Chris Dudney, Henry Falls, Sheldon Goldstein, Deepankar Home, Pankal Rowe, Abner Shimony and Henry Stapp. I should also like to thank Nora Leonard for her exceptional patience and skillful preparation of the manuscript. B.J. Hilley. January 1993. The formalism of the quantum theory leads to results that agree with experiment with great accuracy and covers an extremely wide range of phenomena. As yet there are no experimental indications of any domain in which it might break down. Nevertheless, there still remain a number of basic questions concerning its fundamental significance which are obscure and confused. Thus, for example, one of the leading physicists of our time, M. Gell-Mann I, has said quantum mechanics, that mysterious, confusing discipline, which none of us really understands but which we know how to use. Just what the points are that are not clear will be specified in detail throughout this book, especially in chapters 6, 7, 8, and 14. We can, however, outline a few of them here in a preliminary way. 1. Though the quantum theory treats statistical ensembles in a satisfactory way, we are unable to describe individual quantum processes without bringing in unsatisfactory assumptions, such as the collapse of the wave function. 2. There is by now the well-known non-locality that has been brought out by Bell II in connection with the EPR experiment. 3. There is the mysterious wave-particle duality in the properties of matter that is demonstrated in a quantum interference experiment. 4. Above all, there is the inability to give a clear notion of what the reality of a quantum system could be. All that is clear about the quantum theory is that it contains an algorithm for computing the probabilities of experimental results. But it gives no physical account of individual quantum processes. Indeed, without the measuring instruments in which the predicted results appear, the equations of the quantum theory would be just pure mathematics that would have no physical meaning at all. And thus quantum theory merely gives us, statistical knowledge of how our instruments will function. And from this we can make inferences that contribute to our knowledge, for example, of how to carry out various technical processes. That is to say, it seems, as indeed Bohr, 3, and Heisenberg, 4, have implied, that quantum theory is concerned only with our knowledge of reality and especially of how to predict and control the behavior of this reality, at least as far as this may be possible. Or to put it in more philosophical terms, it may be said that quantum theory is primarily directed towards epistemology, which is the study that focuses on the question of how we obtain our knowledge, and possibly on what we see and do with it. It follows from this that quantum mechanics can say little or nothing about reality itself. In philosophical terminology, it does not give what can be called an ontology for a quantum system. Ontology is concerned primarily with that which is and only secondarily with how we obtain our knowledge about this, in the sense, for example, that the process of observation would be treated as an interaction between the observed system and the observing apparatus, regarded as existing together in a way that does not depend significantly on whether these are known or not. We have chosen as the subtitle of our book an ontological interpretation of quantum theory because it gives the clearest and most accurate description of what the book is about. The original papers in which the ideas were first proposed were entitled An Interpretation in Terms of Hidden Variables 5, and later they were referred to as a causal interpretation 6. However, we now feel that these terms are too restrictive. First of all, our variables are not actually hidden. For example, we introduce the concept that the electron is a particle with well-defined position and momentum that is, however, profoundly affected by a wave that always accompanies it, see chapter 3. Far from being hidden, this particle is generally what is most directly manifested in an observation. The only point is that its properties cannot be observed with complete precision, within the limits set by the uncertainty principle. Nor is this sort of theory necessarily causal. For, as shown in chapter 9, we can also have a stochastic version of our ontological interpretation. The question of determinism is therefore a secondary one, while the primary question is whether we can have an adequate conception of the reality of a quantum system, be it is causal or be it stochastic or be it of any other nature. In chapter 14 section 14.2 we explain our general attitude to determinism in more detail, but the main point that is relevant here is that we regard Introduction 3. All theories as approximations with limited domains of validity. Some theories may be more nearly determinate, while others are less so. The way is open for the constant discovery of new theories, but ultimately these must be related coherently. However, there is no reason to suppose that physical theory is steadily approaching some final truth. It is always open, as has indeed generally been the case, that new theories will have a qualitatively different content within which the older theories may be seen to fit together, perhaps in some approximate way. Since there is no final theory, it cannot be said that the universe is either ultimately deterministic or ultimately indeterministic. Therefore we cannot from physical theories alone draw any conclusions, for example, about the ultimate limits of human freedom. It will be shown throughout this book that our interpretation gives a coherent treatment of the entire domain covered by the quantum theory. This means that it is able to lead to the same statistical results as do other generally accepted interpretations. In particular, these include the Bohr interpretation and variations on this, which we shall discuss in Chapter 2. E.g., the interpretations of von Neumann and Whitney are. For the sake of convenience, we shall put these all together and call them the conventional interpretation. Although our main objective in this book is to show that we can give an ontological explanation of the same domain that is covered by the conventional interpretation, we do show in the last two chapters how it is possible in our approach to extend the theory in new ways, implying new experimental consequences that go beyond the current quantum theory. Such new theories could be tested only if we could find some domain in which the quantum theory actually breaks down. In the last two chapters we sketch some new theories of this kind and indicate some areas in which one may expect the quantum theory to break down in a way that will allow for and test. Partly because it has not generally been realized that our interpretation has such new possibilities, the objection has been raised that it has no real content of its own and that it merely recasts the content of the conventional interpretation in a different language. Critics therefore ask, if this is the case, why should we consider this interpretation at all? We can answer this objection on several levels. Firstly, we make the general point that the above argument could be turned the other way round. Thus de Broglie proposed very early what is, in essence, the germ of our approach. But this met intense opposition from leading physicists of the day. This was especially manifest at the Solvay Congress of 1927-7. This opposition was continued later when in 1952 one of us five proposed an extension of the theory which answered all the objections and indeed encouraged de Broglie to take up his ideas again. For a discussion of the history of undivided university this development and the sociological factors behind it, see Cushing, 8 and also Pinch, 9. Let us suppose, however, that the Solvay Congress had gone the other way and that de Broglie's ideas had eventually been adopted and developed. What then would have happened, if 25 years later some physicists had come along and had proposed the current interpretation which is at present the conventional one? Clearly by then there would be a large number of physicists trained in the de Broglie interpretation, and these would have found it difficult to change. They would naturally have asked, what do we concretely gain if we do change, if after all the results are the same? The proponents of the suggested new approach would then probably have argued that there were nevertheless some subtle gains that it is difficult to weigh concretely. This is the kind of answer that we are giving now to this particular criticism of our own interpretation. To fail to consider such an answer seriously is equivalent to the evidently specious argument that the interpretation that gets in there first is the one that should always prevail. Let us then consider what we regard as the main advantages of our interpretation. Firstly, as we shall explain in more detail throughout the book, but especially in chapters 13, 14, and 15, it provides an intuitive grasp of the whole process. This makes the theory much more intelligible than One that is restricted to mathematical equations and statistical rules for using these equations to determine the probable outcomes of experiments. Even though many physicists feel that making such calculations is basically what physics is all about, it is our view that the intuitive and imaginative side which makes the whole theory intelligible is as important in the long run as is the side of mathematical calculation. Secondly, as we shall see in Chapter 8, our interpretation can be shown to contain a classical limit within it which follows in a natural way from the theory itself without the need for any special assumptions. On the other hand, in the conventional interpretation, it is necessary to presuppose a classical level before the quantum theory can have any meaning, see Bohm. 10. The correspondence principle then demonstrates the consistency of the quantum theory with this presupposition. But this does not change the fact that without presupposing a classical level there is no way even to talk about the measuring instruments that are essential in this interpretation to give the quantum theory a meaning ng. Because OFTHE need to presuppose the classical level, and perhaps even truly an observer, there is no way in the conventional interpretation to give a consistent account of quantum cosmology. For, as this interpretation now stands, it is always necessary to assume an observer, or HIS proxy in the form of an instrument, which is not contained in the theory itself. If Introduction 5. This theory is intended to apply cosmologically, it is evidently necessary that we should not, from the very outset, assume essential elements that are not capable of being included in the theory. Our interpretation does not suffer from this difficulty because the classical level flows out of the theory itself and does not have to be presupposed from outside. Finally, as we have already pointed out, our approach H as the potentiality for extension to new theories with new experimental consequences that go beyond the quantum theory. However, because our interpretation and the many others that have been proposed lead, at least for the present, to the same predictions for the experimental results, there is no way experimentally to decide between them. Arguments may be made in favor or against any of them on various bases, which include not only those that we have given here, but also questions of beauty, elegance, simplicity and economy of hypotheses. However, these latter are somewhat subjective and depend not only on the particular tastes of the individual, but also on socially adopted conventions, consensual opinions, and many other such factors which are ultimately imponderable and which can be argued many ways, as we shall indeed point out in more detail, especially in chapters 14 and 15. There does not seem to be any valid reason at this point to decide finally what will be the accepted interpretation. But is there a valid reason why we need to make such a decision at all? Would it not be better to keep all options open and to consider the meaning of each of the interpretations on its own merits, as well as in comparison with others? This implies that there should be a kind of dialogue between different interpretations rather than a struggle to establish the primacy of any one of them. This point is discussed more fully in Bohm and Pete, 1.1.1.2 brief summary of contents of the book. We complete this chapter by giving a brief summary of the contents of this book. The book may be divided roughly into 4 parts. The first part is concerned with the basic formulation of our interpretation in terms of particles. We begin in chapter 2 by discussing something of the historical background of the conventional interpretation, going into the problems and paradoxes that it has raised. In chapter 3 we go on to propose our ontological interpretation for the one-body system, which however is restricted to a purely causal form at this stage, See bohm and hilley, 12. We are led to a number of new concepts, especially that of active information, which help to make the whole approach more intelligible, and we illustrate the approach. 6. The undivided universe. In terms of a number of key examples. In Chapter 4 we extend this interpretation to the many-body system. And we find that this leads to further new concepts. The most important of these are non-locality and objective wholly new. That is to say, particles may be strongly connected even when they are far apart, and this arises in a way which implies that the whole cannot be reduced to an analysis in terms of its constituent parts. In Chapter 5 we apply these ideas to study the process of transition. Firstly in terms of the penetration of a barrier, and secondly in terms of jumps of an atom from one quantum state to another. In both cases, we see that these transitions can be treated objectively without reference to observation or measurement. Moreover, the process of transition can in principle be followed in detail, at least conceptually, in a way that makes the process intelligible, whereas in the conventional interpretation, as shown in Chapter 2, no such account is possible. This sort of insight into the process enables us to understand, for example, how quantum transitions can take place in a time that is very much shorter than the mean lifetime of the quantum state. In the next part of the book we discuss some of the more general implications of our approach. Thus in Chapter 6 we go into the theory of measurement. We treat this as an objective process in which the measuring instrument and what is observed interact in a well-defined way. We show that after the interaction is over, the system enters into one of a set of channels, each of which corresponds to the possible results of the measurement. The other channels are shown to become inoperative. There is never a collapse of the wave function. And yet everything behaves as if the wave function had collapsed to one of the channels. The probability of a particular result of the interaction between the instrument and the observed object is shown to be exactly the same as that assumed in the conventional interpretation. But the key new feature here is that of the undivided wholeness of the measuring instrument and the observed object, which is a special case of the wholeness to which we have alluded in connection with quantum processes in general. Because of this, it is no longer appropriate, in measurements to a quantum level of accuracy, to say that we are simply measuring an intrinsic property of the observed system. Rather, what actually happens is that the process of interaction reveals a property involving the whole context in an inseparable way. Indeed, it may be said that the measuring apparatus and that which is observed participate irreducibly in each other, so that the ordinary classical and common sense idea of measurement is no longer relevant. The many paradoxes that have arisen out of the attempt to formulate a measurement theory in the conventional interpretation are shown not. Introduction 7. To a rise in our interpretation. These include the treatment of negative assurance, i.e. results following from the non-firing of the detector. The Schrödinger-Cat paradox 13. The delayed choice experiments 14 and the watchdog effect, Zeno's paradox, 15. In Chapter 7 we work out the implications of non-locality in the frame work of our interpretation. We include a discussion of the Bell inequality 2 and the EPR experiment 16. We then go on to discuss how non-locality disappears in the classical limit, except in the special case of the symmetry and antisymmetry of the wave function, for which there is a superselection rule, implying TH at EPR correlations can be maintained indefinitely even at the large scale. This explains how the Pauli exclusion principle can be understood in our interpretation. Finally, we discuss and answer objections To the concept of non-locality. In Chapter 8 we discuss how the classical limit of the quantum theory emerges in the large-scale level, without any break in the whole process, either mathematically or conceptually. Thus, as we have already explained earlier, we do not need to presuppose the classical level as required in the conventional interpretation. In the next part of the book we extend our approach in several ways. Firstly, in Chapter 9, we discuss the role of statistics in our interpretation. We show that in typical situations the particles behave chaotically in a many-body system. From this we see A and infer that our originally assumed probability density, P equals 11/I1, 2, will arise naturally from an arbitrary initial probability distribution. We then go on to treat quantum statistical mechanics in our framework and show how the density matrix can be derived as a simplified form that expresses what is essential about the statistical distribution of wave functions. Finally, we discuss an alternative approach to this question which has been explored in the literature. 17. A stochastic explanation in which one assumes that the particle h as a random component to its velocity over and above that which it has in the causal interpretation. We show that in this theory, an arbitrary probability distribution AGE.IN approaches LL/IL2. But now this will happen even for single particle systems that would not, in the causal interpretation, give rise to chaotic motion. In Chapter 10 we develop an ontological interpretation of the Pauli equation. We begin with a discussion of the history of this interpretation, showing that the simple model of a spinning extended body will not work if we wish to generalize our theory to a relativistic context. Instead, we are led to begin with an ontological interpretation of the Dirac equation ANJ to consider its non-relativistic limit. We show that in addition to its usual orbital motion, the particle then has an additional circulatory motion which accounts for its magnetic moment and its spin. We extend our treatment to the undivided universe, the many-body system, and illustrate this in terms of the EPR experiment for two particles of spin 1/2. In Chapter 1 we go on to consider the ontological interpretation of B0ADN fields. We first give reasons showing the necessity for starting with quantum field theories rather than particle theories in extending our interpretation to B0AD systems. We then develop our ontological interpretation in detail, but from a non-relativistic point of view. The key new concept here is that the field variables play the role which the particle variables had in the particle theory, while there is a superwave function of these field variables that replaces the wave function of the particle variables. We illustrate this approach with several relevant examples. We then go on to explain why the basically continuous field variables nevertheless deliver quantized amounts of energy to material systems such as atoms. We do this without the introduction of the concept of a photon as a bullet-like particle. Finally, we show how our interpretation works in interference experiments of various kinds. In Chapter 12 we discuss the question of the relativistic invariance of our approach. We begin by showing that the interpretation is relativistically invariant for the one-particle Dirac equation. However, for the many-particle Dirac equation, only the statistical predictions are relativistically invariant. Because of non-locality, the treatment of the individual system requires a particular frame of reference, e.g. the one in which non-local connections would be propagated instantaneously. The same is shown to hold in our interpretation for bosonic fields 1/8. We finally show, however, that it is possible to obtain a consistent AP approach by assuming a sub-relativistic level of stochastic movement of particles. class which contains the ordinary statistical results of the quantum theory as well as the behavior of the world of large-scale experience which is Lorentz covariant. Therefore we are able to explain the covariance of all the experimental observations thus far available, at least for all practical purposes. We point out several situations in which this sort of theory could be tested experimentally and give different results from those of the current theory. In any domain in which relativity, and possibly quantum theory, were to break down. We then come to the final part of the book which is concerned with various other ontological interpretations that have been proposed and with modifications of the quantum theory that are possible in terms of these interpretations. The first of these is the many worlds interpretation which has recently aroused the interest of people working in cosmology. We begin by pointing out that there is as yet no generally agreed version of this interpretation and that there are two different bodies of opinion about it. One of these starts from Everett's approach 19 and the other from DeWitt's 20. Introduction 9. Though these are frequently regarded as the same, we show that there are important differences of principle between them. We discuss these differences in some detail and also the as yet not entirely successful efforts of other workers in the field to deal with the unresolved problems in these two approaches. Finally, we make a comparison between our interpretation and the many worlds point of view. The many worlds interpretation was not explicitly aimed at going beyond the limits of the current quantum theory. In Chapter 1-4 we discuss theories that introduce concepts that do go beyond the current quantum theory, at least in principle. The first of these is the theory of Girardi, Rimini and Weber 21, who propose nonlinear, non-local modifications of Schrödinger's equation that would cause the wave function actually to collapse. The modifications are so arranged that the collapse process is significant only for large-scale system, containing many particles, while for systems containing only a few particles, the results are the same, for all practical purposes, as those of the current linear and local form of Schrödinger's equation. Even more striking changes are proposed by Stapp 22 and by Gell, Mann and H. Arnold 23, the latter of whom develop their ideas in considerable detail. They deal with the whole question cosmologically from the very outset by introducing mathematical concepts that enable them to describe actual histories of processes taking place in the cosmos, from the beginning of the universe to the end. We give a careful analysis of these approaches. Both of them aim to do what the many worlds interpretation has not yet succeeded in doing adequately, i.e. to show that the quantum theory contains a classical world J within it. While they have gone some way towards this goal, it becomes clear that there are still unresolved problems standing in the way of its achievement. We also give a critical comparison between their approach and ours, pointing out that their histories actually involve a mathematical assumption analogous to that involved in the notion of particles in our interpretation. Therefore it is not basically a question of the number of assumptions. Rather, we suggest that the main advantage claimed over ours, at least implicitly, is that it expresses all concepts in terms of Hilbert space, whereas we introduce a notion of particles that goes outside this framework. Finally, we discuss some proposals of our own going beyond The Chu Antum, The Ori. Basically these are an extension of what we suggested in Chapter 1-2. The idea is that there will be a stochastic sub-quantum and sub-relativistic level in which the current laws of physics will fail. This will probably first be encountered near the Planck length of 10 to 33 centimeters. However, over longer distances our stochastic interpretation of relativistic quantum theory will be recovered as a limiting case, but as we have suggested earlier, experimental Ments involving shorter times could reveal significant differences from the predictions of the current relativistic quantum theory. Up to this point we have, in a certain sense, been discussing in the traditional Cartesian framework, even though many new concepts have been introduced within this framework. In chapter 15, the final chapter of the book, we introduce a radically new overall framework which we call the implicate or enfolded order. In this chapter we shall give a sketch of these ideas, which are in any case only in early stages of development. We begin by showing that the failure of quantum theory and relativity to cohere conceptually already begins to point to the need for such a new order for physics as a whole. We then introduce the implicate order and explain it in terms of a number of examples which illustrate the enfoldment of a whole structure into each region of space, e.g. as happens in a hologram. We show that the notion of order based on such an enfoldment gives an accurate and intuitive grasp of the meaning of the propagator function of quantum mechanics and, more generally, of Hilbert space itself. We indicate how this notion is contained mathematically in an algebra which is essentially the algebra of quantum mechanics itself. These ideas are connected with our ontological interpretation by means of a model of a particle as a sequence of incoming and outgoing waves, with successive waves very close to each other. For longer times, this approximates our stochastic trajectories, while for shorter times it leads to a very new concept. What is to be emphasized here is that in this way our trajectory model can be incorporated into the framework of Hilbert space. When this is done, we see that it is part of a larger set of possible theories, which include those of Stapp and Gell-Mann and Hartle. One of the main new ideas implied by this approach is that the geometry and the dynamics have to be in the same framework, i.e. that of the implicate order. In this way we come to a deep unity between quantum theory and geometry, in which each is seen to be inherently conformable to the other. We therefore do not begin with traditional Cartesian notions of order and then try to impose the dynamics of quantum theory on this order by using the algorithm of quantization. Rather, quantum theory and geometry are united from the very outset and are seen to emerge together from what may be called pre-space. Finally, we discuss certain analogies between the implicate order and consciousness and suggest an approach in which the physical and the mental sides would be two aspects of a greater order in which they are inherently related. Chapter 2. Ontological versus epistemological interpretations of the quantum theory. 2.1 Classical ontology. In classical physics there was never a serious problem either about the ontology or about the epistemology. With regard to the ontology, one assumed the existence of particles and fields which were taken to be essentially independent of the human observer. The epistemology was then almost self-evident because the observing apparatus was supposed to obey the same objective laws as the observed system, so that the measurement process could be understood as a special case of the general laws applying to the entire universe. 2.2 Quantum epistemology. As we have already brought out in Chapter 1, in quantum mechanics this simple approach to ontology and epistemology was found to be no longer applicable. In the present chapter we shall go into this question in more detail, especially in connection with the way the subject is treated in the conventional interpretation. Let us begin with the fact that quantum mechanics was introduced as an essentially statistical theory. Of course, statistical theories in general are capable of being given a straightforward ontological interpretation, for example, in terms of an objective stochastic process. The epistemology could then be worked out along the same lines as for a deterministic theory such as classical mechanics. But Bohr and Heisenberg raised further questions about the validity of such an approach in the quantum theory. Their argument was based on two postulates: a, the indivisibility of the quantum of action, and b, the unpredictability and uncontrollability of its consequences in each individual case. It follows from the above assumptions, as we shall show in more detail presently, that in the measurement of p and x, for example, THR is a maximum possible accuracy given by the uncertainty principle px h. This is clearly a limitation on the possible accuracy and relevance of our knowledge of the observed system. However, THs has been taken not as a purely epistemological limitation on our no WL edge, but also as an ontological limitation on the possibility of defining the state of being of the observed system itself. To bring out what is meant here, let us briefly review Eisenberg microscope argument. A particle at some point P, see figure 2.1, scatters a quantum of energy, hv, which follows the path POQ to arrive at the focal point Q of the lens. From a knowledge of this point Q, THR is an ambiguity in our ability to attribute the location of THE point P to within THE resolving power of the lens x equals /sin, where is THE wavelength th and is the aperture angle of the lens. This follows from THE wave nature of THE quantum THAT links P to Q. But because the light has a particle nature as well, the quantum has a momentum hv/c, and it produces a change of momentum in THE particle P equals hv sin j/c, where j is the angle through wh the quantum has been scattered by the particle. The indivisibility of the quantum guarantees that its momentum cannot be reduced below this value, while the assumed unpredictability and uncontrollability of the scattering process within guarantees that we cannot make an unambiguous attribution of momentum to the particle within the range 6.p equals h/c. And it is well known that from this we obtain Heisenberg's uncertainty relation 6.p 6.x, h. Relationships of this kind implied, for Heisenberg and Bohr, that the basic properties of the particle, i.e., its position and momentum, are not merely uncertain to us, but rather that there is no way to give them a meaning beyond the limit set by Heisenberg's principle. They inferred from this that there is, as we have already pointed out, an inherent ambiguity in the state of being of the particle. And this in turn implied that, at the quantum level of accuracy, there is no way to say what the electron is and what it does, such concepts being applicable approximately only in the classical, corresponding lim it. THIS evidently represented a totally NEW situation in physics, and Bohr felt that what was called for was a correspondingly new way of describing an experiment in which the entire phenomenon was regarded as a single and unanalyzable whole. 1. In order to bring out the full meaning of Bohr's very subtle thoughts on this point, let us contrast his view of the quantum phenomenon with the ordinary approach to the classical phenomenon. 2. Do this we may take the classical counterpart to the Heisenberg microscope as an example. The relevant phenomena can be described by phi-rst of all, giving the overall experimental arrangement, the lens, the photographic plate, the scattering block and the incident light. Secondly, one has to specify the experimental result, the spot on the photographic plate. But, of course, this result by itself would be of very little interest. The main point of the phenomenon is to give the meaning of the result. In this case, the location of the particle THAT scattered the light. Evidently this is possible only if we know the behavior of the light that links the experimental result to this meaning. Classically this behavior is well defined since it follows from the wave nature of light. Since the light can be made arbitrarily weak and of arbitrarily short wavelength, there is clearly no limit to the possible accuracy of the link between the experimental result and its meaning. That is to say, the disturbance of the particle E and the ambiguity of its properties can be made negligible. This implies that the particle can then be considered to be essentially independent of the rest of the phenomenon in which its properties were determined. Therefore it is quite coherent to use the customary language which says that we have established a state of being of this independent particle as having been observed, and so that the measurement could be left entirely out of the account in discussing the behavior of the particle from this point on. In the corresponding quantum phenomenon there is an entirely different state of affairs. For, as we have already pointed out, the quantum link connecting the experimental result with its meaning is indivisible, unpredictable and uncontrollable. The meaning of such a result can, therefore, no longer be coherently described as referring unambiguously to the properties of a particle that exists independently of the rest of the phenomenon. Instead, this meaning has to be regarded as an inseparable feature of the entire phenomenon itself. Or, to put it more succinctly, the form of the experimental conditions and the content, meaning, of the experimental results are a whole, not are analyzable. It is this whole that, according to Bohr, constitutes the quantum phenomenon. It follows from this that given a different experimental arrangement, e.g. one needed to measure a complementary variable more accurately, we would have a different total phenomenon. The two phenomena are mutually exclusive in the sense that the conditions needed to determine one are incompatible with those needed to determine one the other, whereas classically the two sets of conditions are, in principle, compatible. Bohr emphasizes that one compatible phenomena of this kind actually complement each other in the sense that together they provide a complete, though ambiguous description of the atomic object. These complementary descriptions cannot be combined into a single picture by means of ordinary concepts, they represent equally essential aspects of any knowledge of the object in question that can be obtained in this domain too. Classically, two such concepts can always be combined in a single unambiguous picture. This enables us to form a well-defined concept of an actual process, independent of the means of observation, in which, for example, a particle actually moves from one state to another. But at the quantum level, where the indivisibility of the quantum of action implies an ambiguity in the distinction between the observed object and observing apparatus, there is no way to talk consistently about such a process. It follows from Bohr's approach that very little can be said about quantum ontology. One has at most an unambiguous classical ontology, and the quantum theory is reflected in this ontology by requiring basic concepts such as P and X to be ambiguous. One might perhaps suppose that THR could be some unambiguous deeper quantum concepts of a new kind. But Bohr would say there is no way to relate these definitely to WH at we ordinarily regard as objective reality, i.e. the domain in which classical physics is a good approximation. We can summarize Bohr's position as saying that all physical concepts must correspond to phenomenon, i.e. appearances. Each phenomenon is an abstraction. This is also true classically. But because the correspondence between the phenomenon and the independent reality which underlies it may, in principle, be unambiguous, and because all the phenomena are mutually compatible, we may say that the independent reality can be reflected completely in the whole set of phenomena. This means in effect that we can know the independent reality itself. But quantum mechanically we cannot apply all relevant abstractions together in an unambiguous way, and for whatever we say about independent reality is only implicit in this way of using concepts. What then is the meaning of the mathematics of the quantum theory? Which is very well defined indeed. Bohr describes this as the quantum algorithm, which gives the probabilities of the possible results for each kind of experimental arrangement for. Clearly this means that the mathematics must not be regarded as reflecting an independent quantum reality that is well defined, but rather that it constitutes in essence only knowledge about the statistics of the quantum phenomena. All this, as we have already pointed out, is a consequence of the indivisibility of the quantum of action, which is very well verified experimentally. Bohr therefore does not regard his notion of complementary as based on philosophical assumptions. Rather, it has for him an ontological significance, in the sense that it says something about reality, i.e., that it is ambiguously related to the phenomena. He would probably say that attempts to define the ontology in more detail would be contradictory. 2. 3. The quantum state. Bohr's view seems to have had a very widespread influence, but his ideas do not appear to have been well understood by the majority of physicists. Rather, the latter generally thought in terms of a different approach along lines initiated by Dirac and von Neumann, in which the concept of a quantum state played a key role. With Bohr this concept was hardly even mentioned and was certainly not a fundamental part of his ideas. To understand what is meant by a quantum state, we can begin with Dirac's notion that each physical quantity is represented by an Hermitian operator which is called an observable 5. When this is measured by a suitable apparatus, the system is left with a wave function corresponding to an eigenfunction of this observable. In general, such a measurement will, in agreement with Heisenberg's principle, alter this wave function in an uncontrollable and unpredictable way. But the probability of a certain result n is ICN12, where Cn is the coefficient of the n1h eigenfunction in the expansion of the total wave function. Once we obtain such an eigenfunction, we can measure the same observable again and again, in principle, in a time so short that the wave function does not change significantly, except for a phase factor which is not relevant. Each measurement will then reproduce the same result. In terms of the naive ontology that pervades ordinary experience, this leads one to suppose that, between measurements of the same observable, the system continues to exist with the same wave function Tpn, again, except for a phase factor. Therefore one could say that during this time the system is in a certain state of being, i.e. at stands independently of its being observed. Of course, this state might change in longer times of its own accord, and, in addition, it would also change if a different observable were measured. In contrast, Bohr would never allow the type of language that admitted the independent existence of any kind of quantum object which could be said to be in a certain state. That is to say, he would not regard it as meaningful to talk about, for example, a particle existing between quantum measurements, even if the same results were obtained for a given observable in a sequence of such measurements. Rather, as we have seen, he considered the experimental arrangement and the content, meaning, of the result to be a single unanalyzable whole. To talk of a state in abstraction from such an experimental arrangement would, for Bohr, make no sense. This general point can be clarified by considering what is in essence an intermediate approach adopted by Heisenberg. He suggested that the wave function represented, not an actual reality, but are either a set of potentialities that could be realized according to the experimental conditions. A helpful analogy may be obtained by considering a seed, which is evidently not an actual plant, but which determines potentialities for realizing various possibly forms of the plant according to conditions of soil, rain, sunlight, wind, etc. Thus when the measurement of a given observable was repeated, this would correspond to a plant producing a seed, which growing under the same conditions, produced the same form of plant again, so that there was no continuously existent plant. Measurement of another observable would correspond to changing the experimental conditions, and THs could produce a statistical range of possible plants of different forms. Returning to the quantum theory, it is clear in THIS approach the apparatus is regarded as actually helping to see the observed results. It must be emphasized, however, that BOHR specify CALLY reject this suggestion which he probably felt gave TOO much independent reality to whatever is supposed to be represented by the wave function. As we recall, he regarded this as only part of a calculus for predicting the statistics of experimental results. Thus he states, I warned especially against phrases often found in the physical literature, such as disturbing of phenomena by observation or eating physical attributes to atomic objects by measurement. Such phrases are apt to cause confusion. 7. Bohr is evidently saying here essentially what we have said before, i.e. that for him it has no meaning to talk of a quantum object with its attributes apart from the unanimous elicible whole phenomenon in which it is actually observed. It is thus clear, as we have indeed already pointed out earlier, that Bohr's objection to the potentiality approach, as well as to taking the concept of quantum state too literally, does not represent for him a purely philosophical question. Indeed, in his discussion of the Einstein, Podolsky, and Rosen experiment (EPR), it was just this point that was crucial in his answer to the challenge presented by EPR, as we shall show in more detail. In Chapter 7, Bohr would say that the EPR paradox was based on an inadmissible attribution of properties to a second particle solely on the basis of measurements that could be read out on the first particle. 2.4 Von Neumann's approach to quantum theory. It is clear then that there is an important distinction between Bohr's approach and that of Heisenberg with his notion of potentiality, and perhaps an even greater difference from that of most physicists, who give a basic significance to the concept of quantum state. The notion of quantum state has indeed been most systematically and extensively developed by von Neumann, who not only gave it a precise mathematical formulation, but who also attempted, in his own way, to come to grips with the philosophical issues to which this approach gave rise. It was a key part of this development to give a proof claiming to show that quantum mechanics had an intrinsic logic closure, in the sense that no further concepts, e.g. involving hidden variables, could be introduced that would make possible a more detailed description of the state of the system than is afforded by the wave function. On this basis he concluded that the wave function yielded the most complete possible description of what we have been calling quantum reality, which is thus totally contained in the concept of a quantum state. In order to clarify the physical meaning of these notions he developed a more detailed theory of measurements. This theory still gave a basic significance to epistemology because the only meaning attributed to the wave function was that it gave probabilities for the results of P08 measurements, i.e. it did not begin with the assumption of an independently existing universe that would have meaning apart from the process in which its properties were measured. Nevertheless, this theory gave more significance to ontology than Bohr did, because it assumed the quantum system existed in a certain quantum state. This state could only be manifested in phenomena at a large scale, CLAS sickle level. Thus he was led to make a distinction between the quantum and the classical levels. Between the M, he said there was a cutoff. This is, of course, purely abstract, because von Neumann admitted, along with physicists in general, that the quantum and classical levels had to exist in what was basically one world. However, for the sake of analysis, one could talk about these two different levels and treat them as being in interaction. The effect of this interaction was to produce at the classical level a certain observable experimental result T. The probability of the N1H result was, of course, ICN12, where the original wave function was T slash equals LCN T slash N, and T slash N is an eigenfunction of the operator being measured. But reciproca LLY, this interaction produced an effect on the quantum level, that is, the wave function changed from its original form T slash to T slash N, where N is the actual result of the measurement obtained at the classical level. This change H has been described as a collapse of the wave function. Such a collapse would violate Schrödinger's equation, which must hold for any quantum system. However, this does not seem to have disturbed von Neumann unduly, probably because one could think that in its interradian with the classical level such a system need not satisfy the LAWs that apply when it is isolated. Only difficulty with this theory is that the location of the cut between quantum and classical level is to a large extent arbitrary. For example, one may include the apparatus and the observed object as part of a single combined system, which is to be treated quantum mechanically. We then observe this combined system with the aid of yet another apparatus, which is, however, treated as being in the classical level. The CUT has then been moved to some point between the first apparatus and the second. Von Neumann has given a mathematical treatment of this experiment, which we shall sketch here. Let 0 be the operator that is to be measured. Let on be its eigenvalues and t slash n, x, the corresponding eigenfunctions in the x representation. The initial wave function is, as we have already stated, n. The apparatus may have a large number of coordinates, but it will be e. Sufficient to consider one of these, y, representing, for example, a pointer, from whose points one can read the result T of the measurement. Initially. Ontological versus epistemological interpretations 2-1. The apparatus is in a fairly well-defined state represented by a wave packet. 4-0-11. The initial wave function of the combined system is then ILA equals cent. O, y. LCNT slash in, x. 2.1. N. We then assume an interaction between the observed system and the apparatus which lasts only for a time FLT. For the purpose of explaining the principles involved, it will be sufficient to consider what is called an impulsive measurement, i.e. one in which the interaction is so strong that, throughout the period in which it works, the changes in the observed SYS TEM and the observing apparatus that would occur independently of the interaction may be neglected. The interaction Hamiltonian may be chosen as 2.2, where .x is a suitable constant. Since this is the same as the total Hamiltonian during this period, we can easily solve Schrödinger's equation. IH \11 equals in .xo \11 at I to obtain for the wave function after an interval FLT. N. If the interaction is chosen so THAT 2.3, 2.4, 2.5, where flan is the change of on for successive values of n, then it follows that the wave packets multiplying different 1/in, z, will not overlap. To each cent o, y, dot x on FLT, there will correspond a wave function cn1/in, z. If we now observe the system with the aid of a second piece of apparatus, then in accordance with the postulates that have been described earlier, the latter will register the value of y. But it will NOWHAVE to be in one of the packets, while 1/in, z, will then represent the corresponding state of the original QUANTUM system. In effect, the total wave function H has collapsed. 22 THIRD-WORLDISM univary. From the original linear combination of products to a particular product. N, Z, L/low, Y, AONT. The probability that this H happens can be shown to be ICNL2 exactly as it was when we had only one measuring apparatus. In a naive view of this process, one could readily say that this collapse represented merely an improvement of our knowledge of the state of the system which resulted from its being measured by the second apparatus. Indeed, in the application of classical probability in physics, such collapses are quite common. Thus, before one has observed a specified ensemble, the probability of a certain result n may be Pn. When one observes the result S, the probability suddenly collapses from Pn to 8n. But this interpretation is not valid here because in the classical situation we have a linear combination of probabilities of Ea.ch of the results. Whereas quantum mechanically we have a linear combination of wave functions, while the probability depends quadratically on these wave functions. Before the second measuring apparatus H has functioned, we therefore can not say that the system is definitely in one of the n states with probability ICN12. 4. A whole range of subtle physical properties exist which depend on the linear combination of wave functions. Thus, although the wave pack ETS corresponding to different values of n do not overlap, they could, in principle, be MA.DE to do so once A. Gain by means of further interactions. For example, one could introduce a suitable term in the Hamiltonian that brought such an overlap A.bout. Moreover, one could have subtle observables corresponding to operators that couple the combined states of both systems, and the mean values of these would depend on the existence of linear combinations of the KINDWHAVE discussed above. This point is discussed in some detail in Bohm 9. A2 of this means that such linear combinations have an ontological significance and do not merely describe our knowledge of the probabilities of possible values of n which could be the result of this measurement. Actually, a similar problem was present even when we had only one piece of apparatus. But this is not generally felt to be disturbing because of the THIRD assumption that the quantum of action that connects the observed system and the observing apparatus could readily introduce significant physical changes in a microsystem such as an atom, along the general lines described in connection with the Heisenberg microscope experiment. However, we.re now led to the conclusion that observation could also introduce significant changes of this kind in a macrosystem which includes the first piece of apparatus. Or, to put it differently, we may readily accept the notion that in an observation, the quantum state of a microsystem undergoes a real change when the wave function collapses from a linear combination 111 equals LCNI.Vn, z, down to one of the eigenfunctions cent, z. It is not clear, however, what it means to say that there is a ontological versus epistemological interpretations. 23. Euler real change in a macro system when the wave function collapses from equals LCNF n z t/jo y a on at to a single state p z p0 y a o at. This difficulty arises in SNCE because von Neumann introduced the basically ontological notion that the wave function represents a quantum state that somehow stands on its own, alt hoc, of course, in interaction with the classical level. Bohr avoids this problem by never speaking of a quantum object that could stand on its own, but rather by speaking only of a phenomenon which is an unanalyzable whole. The question of interaction between a quantum level and a classical level thus cannot arise. Therefore, in this sense, he is more consistent than von Neumann NN. At phi rs t side one might be inclined to regard these questions as not very important, for after all the cut is only an abstraction and one can see that the statistical results do not depend on where it is plocked. However, in so far as von Neumann effectively gave the quantum state a certain ontological significance, the net result was to produce a confused and unsatisfactory ontology. This ontology is such as to imply that the collapse of the wave function must also have an ontological significance. W erase for Bohr it merely represents a feature of the quantum algorithm which arises in the treatment of a new experiment to show the extent of this difficulty. One could, for example, introduce a third apparatus that would measure a system that consisted of the observed object and the first two pieces of apparatus. For this situation the collapse would take place between the second and third piece of apparatus. One could go on with this sort of sequence in phi nit hilley to include, for example, a computer recording of the results on a disk. In this case the collapse would take place when the disk was read, perhaps even a year or so later, in which case the whole system would be in a certain quantum state represented by a linear combination of wave functions over this whole period of time. And, as von Neumann himself pointed out, one could even include parts of the human brain within the total quantum system, so that the collapse could be brought about as a function of the brain. It is evident that this whole situation is unsatisfactory because the ontological process of collapse is itself highly ambiguous. Perhaps Bohr's rather more limited ambiguity may seem preferable to von Neumann's indefinitely proliferating ambiguity. Wigner has carried this argument further and has suggested that the above ambiguity of the collapse can be removed by assuming that this process is definitely a consequence of the interaction of matter and mind 1-0. Thus he is, in effect, placing the cut between these two and implying that mind is not limited by quantum theory. Pauli has also felt for different reasons that mind plays a key role in this context. 1l. We see several difficulties in the attempt to bring in the direct AC. 24. The undivided universe of the mind to give an ontological interpretation of the current physical JAWS of the quantum theory. Thus in ALA Boratri, it is hard to believe that the human mind is actually significantly affecting the results of the functioning of the instruments, which as we have already pointed out, be recorded on a computer that is not even examined for a long time. Moreover, quantum theory is currently applied to cosmology, and it is difficult to believe that the evolution of the universe before the appearance of human beings depended fundamentally on the human mind, e.g. to make its wave function collapse in an appropriate way. Of course one could avoid this difficulty by assuming a universal mind. but if we know little about the human mind, we know a great deal less about the universal mind. Such an assumption replaces one mystery by an even greater one. One may ask why physicists have felt the need to bearing in mind in their attempts to make sense of the quantum theory. Such a need is, indeed, implied in the work of those following along the lines of von Neumann NN. These want to say that the wave function H has an ontological significance, i.e., as representing the quantum state, and at the same time to assume that it is a complete description of reality. However, as we have already pointed out, Bohr has claimed, apparently with greater consistency, that any ontology whatsoever is ruled out by the very nature of reality as revealed throughout the quantum theory. This would suggest that it would be better to adopt Bohr's point of view. 2.5 Are Bohr's conclusions inevitable? But does the fact that the quantum theory H has been applied so successfully lead inevitably to Bohr's conclusion concerning the nature of reality? Clearly it does not. For as we have already explained, it involves certain assumptions about real physical processes. In order to examine these as assumptions properly, let us repeat them. Firstly, the quantum of action is taken to be indivisible, and secondly, it is assumed to be unpredictable and uncontrollable. From this, Bohr draws the conclusion that the state of being is inherently ambiguous at the quantum level of accuracy. It is essential to look more carefully at this conclusion, which is based, in part, on a tacit identification of determining Sm with predictability and L controllability. This identification is clearly characteristic of positivity philosophy. In this philosophy, science is not regarded as dealing with what ones, so that concepts cannot be regarded as reflecting reality. Rather, they have to be defined empirically, i.e., in relation to their manifestation in observation and experience. In such a philosophy, it follows that determinism can have no meaning beyond predictability and controllability. Ontological versus epistemological interpretations 25. Since the quantum theory was first formulated, the relationship of determinism to predictability and controllability has been clarified by the discovery that a very general class of deterministic systems, i.e. those having unstable and chaotic motions, are neither predictable nor controllable. As has been discussed in some detail by Penrose, 12. Thus the identification of determinism with predictability and controllability has been invalidated. It follows that the mere controllability and unpredictability of quantum phenomena does not necessarily imply that there can be no quantum world, which could in itself be determinate. What about the indivisibility and unanalyzability of the quantum of action? It is true that in some sense, at least, the quantum of action is neither divisible nor analyzable at the level of the phenomena. Consider, for example, an atom emitting a quantum of light. We have two distinct states. A. The atom in an excited state and no quantum present, and B. The atom in its ground state and a quantum present. The process of going from A to B is said to be a quantum jump. In the sense that there are no phenomena which correspond to any state in between. Of course, we may try to find such phenomena by observing the system in its process of transition. But as implied in Bohr's views, this would constitute an entirely different experimental arrangement that would be incompatible with the process of transition that we are considering. From this, however, it does not follow that there is no more complete description, perhaps at a deeper, more complex level in which this process can be treated as continuous and analyzable. One can indeed easily conceive of such a process in general terms. For example, the same kind of non-linear equations THAT give rise to unstable and chaotic motions can also lead to what are called stable limit cycles, in which the system stays near a certain state of motion. But more generally, the stability may be limit, so that the system can jump from one such limit cycle to another, in a movement so fast and unstable THAT it could neither be predicted, controlled, nor followed. Thus it would not appear in the pH phenomena. Indeed, as we shall see in Chapter 5, our interpretation of the quantum theory implies just such jumps between what are in essence stable limit cycles. INTHIS way 1 may explain processes that in the quantum theory are called unpredictable. UN controllable and indivisible quantum transitions between discrete orbits. But as we recall, Bohr's entire position depended crucially on his assumptions of the nature of the quantum of action. Therefore, from what we have said above, it follows that there is no inherent necessity to adopt Bohr's position, and that there is no thing in Bohr's analysis that could rule out a quantum ontology. But of course, THISLAT would require the introduction of new concepts beyond that of the wave function and the quantum state. We would have to begin by simply assuming the new concepts and define them through their participation in the laws of physics. In doing this, we have to differ from Bohr, who and TLEA.ST tacitly required that all hadotzic physical concepts be defined by referring them to specific phenomena, in which they re measure ed. In contra.st we derive the probable phenomena. A.S forms on the overall structure of concepts and their relationships. An example of this is given by Einstein's derivation of particles, obeying the usual laws of motion, either as singularities, or A.S very strong static pulses in a continuous nonlinear phi LD. The test of the theory is then to see whether the derived phenomena not only explain the genera.I form of the observed phenomena, but also their detailed relationships. In such an approach, the epistemology follows naturally from the ontology, just as it does in classical physics. At this point, however, we have to return to von Neumann, who, as we have already pointed out, believed that the wave function contained the most complete possible description of reality, thus implying that there was no way to do what we have suggested above. Von Neumann based this belief on his theorem, to which we have alluded earlier, that claimed to show that a more detailed description would not be compatible with the laws of the quantum theory 1.3. This proof was however questioned by Bohm 14 in 1952 and later by Bell 1.5. A number of those who followed along von Neumann's lines refined his arguments in several ways. But these refinements were also shown by Bell to make ta.cit assumptions about ontological theories that re2 limited. ALL of this will be discussed in more detail in Chapter 7. We conclude that there are no sound reasons against seeking an ontological interpretation of the quantum theory. This book presents in essence the first complete ontological interpretation that has been proposed. As indicated in the introduction, there have been several other ontological interpretations since then. In Chapter 14 we shall discuss these and compare and contrast them with the interpretation given in this book. Chapter 3. Causal interpretation of the 1-body system. In this chapter we develop the basic principles of our ontological interpretation of the quantum theory in the context of a one-body system, WHIL. The many-body system will be treated in the next chapter. 3.1 The main points of the causal interpretation. Let us begin by considering the THIRD-WORLDISM approximation for THECLAS. Sickle limit in quantum mechanics. To do this we write the wave function. In polar form 1 equals REXP, IS/H, we insert this form into Schrödinger's equation. Where V is the classical potential, this gives rise to two equations. And AS, \75, 2N2 \72R, plus V, equals 0. OT2M2MR, 3 1, 3, 2, 3, 3. In order to obtain the WKB approximation, we note that in the classical limit in which there is a wave packet of width much greater THA and the wave length TH, the term H2 \72R/2MR will be very small compared with the term \75, 2/2 M, we therefore neglect it and obtain 3 4. Causal interpretation of the ONE, BOD-ISTM 29. In the above we have written S equals SC to indicate that we are dealing with the classical Hamilton-Jacobi equation representing a particle with momentum 3.5, which moves normal to the wave front. SC equals const. It follows then that equation 3.2 can be regarded as a conservation equation for the probability in an ensemble of such particles, all moving normal to the same wave front, with the probability density P equals R2. I of this may seem familiar, but nevertheless there is something very noteworthy here. For though we have started with the quantum theory, with all its ambiguities about the nature of a quantum system, we have somehow slipped over into what is in essence the ordinary classical ontology. It seems natural at this point to ask whether this kind of ontology could not be extended to the quantum domain. Thus we note the quantum equation 3.2 differs from the classical equation 3.4 only by the term N2/2M \L2R/R, which evidently can be regarded as playing the role of an additional potential in what we may call the quantum Hamilton-Jacobi equation. To bring this out we shall define what we call the quantum potent IL N 2V2R Q equals 2MR. The quantum Hamilton-Jacobi equation then becomes as plus Vs 2 plus V plus Q equals O 8T2M 3.6 3.7. The equation 3.3 still expresses the conservation of probability, but for an ensemble of particles which satisfies 3.7 rather than 3.4. Let us now discuss this ontology in a more systematic way. Its key points are L. The electron actually is a particle with a well-defined position xt, which varies continuously and is causally determined. 2. This particle is never separate from a new type of quantum field that fundamentally affects it. This field is given by RNS or alternatively by 1/ equals REXP is /n. 1/ then satisfies Schrödinger's equation. R other than, for example, Maxwell's equation, so that it too changes continuously and is causally determined. 3. The particle has an equation of motion. dv m equals \L v \L q dt. 3.8. 30. The undivided universe. This means that the forces acting on it are not only the CLM force Vv, but also the quantum force \Q. 4. The particle momentum is restricted to P equals \S. Since the quantum field is single valued, it follows, as can easily be shown, that F P dx equals nh. 3.9. This resembles the old Bohr Sommerfeld condition, but differs from the latter, in which P equals \sc, where Sc is the solution of the classical H.A.-Milton-Jacobi equation, 3-4, rather than the quantum H.A.-Milton Jacobi equation, 3-7. 5 in a statistical ensemble of particles, selected SO that all have the same quantum field 1/, the probability density is P equals R2. We shall discuss the significancy and CE of this in more detail in a later section, but we can now note that if P equals R2 holds initially, then the conservation equation, 3-3, guarantees that it will hold for all time. Given that the particle is always accompanied by its quantum field 1/. We may say that the combined system of particle plus field is causally determined. The statistics merely apply to an ensemble of causally determined trajectories. For this reason the above proposals have been called the causal interpretation in some of the earlier papers. It must be emphasized that the basic ontological point of view given here can be extended, as we shall indeed do in Chapter 9, to a more general stochastic context. Finally, it should be pointed out that unlike what happens with Max Well's equations, for example, the Schrödinger equation for the quantum field does not have sources, nor does it have any other way by which the field could be directly affected by the conditions of the particles. This, of course, constitutes an important difference between quantum fields and other fields that have thus far been used. As we shall see, however, the quantum theory can be understood completely in terms of the assumption that the quantum field H has no sources or other forms of dependence on the particles. We shall in Chapter 14, Section 14, 6, go into what it would mean to have such dependence, and we shall see that THIS would imply that the quantum theory is an approximation with a limited domain of validity. In this way, as well as in other ways, we will see that our ontological interpretation permits a generalization of the laws of physics going beyond the quantum theory, yet approaching the quantum theory as a suitable limit within which physics H has thus far been contained. Coal interpret a tion of the 1 Badra Ratem 3.1. 3.2 New concepts implied by the ontological interpretation. At first sight it may seem that to consider the electron, for example, as some kind of particle that is affected by the quantum field T/J is just a return to older classical ideas. Such a notion is, however, generally felt to have long since been proved to be inadequate in understanding quantum theory, which possesses so many features that are very different from those of classical mechanics. However, closer inspection shows that we are not actually reducing quantum mechanics in this way to an explanation in terms of classical ideas. For the quantum potential H as a number are of strikingly new features which do not cohere with what is generally accepted as the essential structure of classical physics. In TH's connection, it is important to note that the form of Newton's laws alone is not enough to determine that the general structure of classical physics shall hold. For example, a great deal of work has been done showing that to obtain determinism, H is surely an essential feature of classical physics. We require further assumptions on the nature of the forces 1. For example, if infinite particle velocities or signal velocities are allowed, it has been demonstrated that determinism may fail. But no one has claimed to have given an exhaustive treatment of all the requirements, even for determinism alone. Moreover, it seems reasonable to suppose that other features of classical physics may also depend on further largely taciti. Assumptions about the nature of the forces. Indeed sweshlic, the new qualitative features of the quantum potential that we have mentioned above are just such as to imply the new properties of matter that are revealed by the quantum theory. The phi-rst of these new properties can be seen by noting that the quantum potential is not changed when we multiply the field 1/ by an arbitrary constant. This is Be cos 1/ appears both in the numerator and the denominator of Q. This means that the effect of the quantum potential is independent of the strength h, i.e. the intensity, of the quantum field but depends only on its form. By contrast, classic A waves, which act mechanically, i.e. to transfer energy and momentum, for example, to push a floating object T, always produce effects that are more or less proportional to the strength of the wave. For example, one may consider a water wave, which causes a cork to bob. The further the cork is from the center of the wave the less it will move. But with the quantum field, it is as if the cork could bob with full strength even far from the source of the wave. Such behavior would seem strange from the point of view of classical physics. Yet it is fairly common at the level of ordinary experience. For example, we may consider a ship on automatic pilot being guided by radio 32 the undivided university or 0.9 waves. Here, too, the effect of the radio waves is independent of their intensity and depends only on their form. The essential point is that the ship is moving with its own energy, and that the form of the radio waves is taken up to direct the much greater energy of the ship. We may therefore propose that an electron too moves under its own energy, and that the form of the quantum wave directs the energy of the electron. This introduces several new features into the movement. First of all, it means that particles moving in empty space under the action of no classical forces need not travel uniformly in straight lines. This is a radical departure from classical Newtonian theory. Moreover, since the effect of the wave does not necessarily fall off with the distance, even remote features of the environment can profoundly affect the movement. As an example, let us consider the interference experiment. This involves a system of two slits. A particle is incident on this system, along with its quantum wave. While the particle can only go through one slit or the other, the wave goes through both. On the outgoing side of the slit system, the waves interfere to produce a complex quantum potential which does not in general fall off with the distance from the slits, too. This potential is shown in Figure 3. 1. Note the deep valleys and broad plateau ux. In the regions where the quantum potential changes rapidly, there is a strong force on the particle. The particle is thus deflected, even though no classical force is acting. We now consider a statistical ensemble of particles which may be obtained, for example, by having electrons boiled out of a hot filament in a random way. Each electron has its own quantum field, but with the aid of suitable collimators and velocity selectors, we choose only those electrons with quantum fields corresponding approximately to waves with given direction and wave number that are incident on the slits in the manner described above. While all the electrons now have essentially the same form of the quantum field and therefore of the quantum potential, they will all approach the slit system from different starting points, as will be shown in Section 3. 4. As well as in Chapter 9, for the C as E we may expect an essentially random distribution of such incident electrons. The resulting trajectories, which are shown in figure 3. 2 are then bunched into a series of dense and rare regions. These evidently constitute what are commonly called interference fringes. If, however, just1 slit had been open, the quantum field, 1/. Would only pass through the slit, so that beyond the slit system air would have been a different quantum field and therefore a different potential. This would produce a more nearly uniform distribution of particles ng at the screen, rather than a set of fringe-like regions. In this way we explain why the opening of a second slit can prevent particles from arriving at points to which they would not have come if only one slit had been open. In this explanation of the quantum property 11 of the electron, the fact that the quantum potential depends only on the form and not on the amplitude of the quantum field is evidently of crucial significance. As we have already suggested, although at first sight such behavior seems to be totally outside of our common experience, a little reflection shows that this is not so. Effects of this kind are indeed frequently encountered in ordinary experience wherever we are dealing with information. Thus in the example of the ship guided by radio waves, one may say that these waves carry information about what is in the environment of the ship and that this information enters into the movements of the ship through its being taken up in the mechanism of the automatic pilot. Similarly we explain the interference properties by saying that the quantum field contains information, for example about the slits, and that this information is taken up in the movements of the particle. In effect we have in this way introduced a concept that is new in the context of physics, a concept that we shall call active information. The basic idea of active information is that a form having very little energy enters into and directs a much greater energy. The activity of the latter is in this way given a form similar to that of the smaller energy. It is important to distinguish our concept of active information from the more technical definition of information commonly adopted in physics. In terms of, for example, Shannon's ideas 3 implying that there is a quantitative measure of information that represents the way in which the state of a system is certain to us, e.g. that we can only specify probabilities of various states. It is true that such concepts have been used to calculate objective properties of systems in thermodynamics and even black holes, etc. 4. But we wish to propose here a quite different notion of information that is not essentially related to our own knowledge or lack of it. Rather, in the case that we are discussing, for example, it will be information that is relevant to determining the movement of the electron itself. We emphasize again that it is our thesis that this sort of usage of the word information is actually encountered in a wide range of areas of experience. What is crucial here is that we are calling attention to the literal meaning of the word, i.e. to inform, which is actively to put form into something or to imbue something with form. As a simple example of what we mean, consider a radio wave whose form is a sine al. The sound energy we hear in the radio does not come directly from the radio wave itself, which is too weak to be detected by our senses. It comes from the power plug or batteries which provide an essentially UN-formed energy that can be given form, I.E. informed, by the pattern carried by the radio wave. This process is evidently entirely 36 the undivided universe. Objective and has nothing to do with our knowing the details of how this happens. The information in the radio wave is /1 active everywhere, but it is actually active only where and when it can give form to the electrical energy which, in this case, is in the radio. A more developed example of such a situation is given by considering the computer. The information content in a silicon chip can determine a whole range of potential activities which may be actuated by giving form to the electrical energy coming from a power source. Which of these possibilities will be actuated in a given case depends on a wider context and the responses of a computer operator. Although the above examples do indicate what we mean by the objective significance of active information, nevertheless they still depend on structures, like the radio set and the computer, which were originally designed and put together by human beings and so may be felt to retain a trace of subjectivity. An example that does not involve structures set up by human beings is the function of the DNA molecule E. The DNA is said to constitute a code, it is to say, a language E. The form of the DNA molecule is considered as information content for this code E, while the meaning is expressed in terms of various processes, e.g. those involving RNA moleculae, which read the DNA code, and DCARRY out the protein-making activities THATR, implied by particular sections of the DNA molecule. The comparison to our notion of objective and active information is very close. Thus, in the process of cell growth it is only the form of the DNA molecule that counts, while the energy is supplied by the rest of the cell, and indeed ultimately by the environment as a whole. Moreover, at any moment only a part of the DNA molecule is being read and giving rise to activity. The rest is potentially active and may become active according to the total situation in which the cell finds itself. While we are bringing out above the objective aspects of information, we do not intend to deny its importance in subjective human experience. However, we wish to point out that even in this domain, the notion of active information still applies. A simple example is to be found in reading a map. In this activity we apprehend the information content of this map through our own mental energy, and by a whole set of virtual or potential activities. In the imagination, we see the possible significance of this map. Thus, the information is immediately active in arousing the imagination, but this activity is still evidently inward within the brain and nervous system if we are actually traveling in the territory itself. Then, at any moment, some particular aspect may be further actualized rough our physical energies acting in that territory, according to a broader context, including whathe. Human being knows and what he is perceiving at that moment. We therefore emphasize once again THATEVENTHEIN formation HELDHY. Human beings is, in general, active rather than passive, not merely reflecting something outside itself but actually, or at least potentially, capable of participating in the thing to which it refers. Passive information may in fact be regarded as a limiting case in which we abstract from the activity of information. This is essentially the kind of information that is currently used in information theory, e.g. as used by Shannon. The puzzle in this approach is that of how information that is merely passive within us is able to determine actual objective processes outside of us. We suggest that passive information is rather like a map reflecting something of these processes which can guide us to organize them conveniently for our use, e.g. by means of algorithms that enable us to calculate entropy and other such properties. If the notion of active information applies both objectively and subjectively, it may well be that all information is at least potentially active and that complete passivity is never more than an abstraction valid in certain limited circumstances. In this context, our proposals to use the concept of active information at the quantum level does not seem to be unnatural. To show how these ideas work out in more detail, we can go once again into the example THAT we gave earlier of the electron in an interference experiment. We could say that this PRT=H as the ability to do work. This ability is released by active information in the quantum phi LD, which is measured by the quantum potential as the particle reaches certain points in front of the slits. It is in form to accelerate or decelerate accordingly, sometimes quite violently. Although equation 3.8 may look like a classical law implying pushing or pulling by the quantum potential, this would not be understandable, because a very weak field can produce the full effect, which depends only on the form of the wave. We therefore emphasize that the quantum field is not pushing or pulling the particle mechanically, any more in the radio wave is pushing or pulling the ship that it guides. So the ability to do work does not originate in the quantum field, but must have some other origin. A suggestion which we shall discuss presently. The fact that the particle is moving under its own energy, but being guided by the information in the quantum field, suggests that an electron or any other elementary particle has a complex and subtle inner structure, e.g., perhaps even comparable to THAT of a radio. This notion goes against the whole tradition of modern physics, which assumes THAT as we analyze matter into smaller and smaller parts, its behavior always grows more and more elementary. But our interpretation of the quantum theory indicates as THAT. Nature is far more subtle and strange than previously thought. H.O. Weaver. This sort of inner complexity is perhaps not as implausible as may appear at first sight. For example, a large CR out of people can be treated by simple statistical laws, whereas individually, their behavior is infinitely more subtle and complex. Similarly, large masses of matter reduce approximately to a simple Newtonian behavior, whereas the molecules and atoms out of which matter is built have a more complex inner structure. To make this suggestion yet more plausible, we note that between the shortest distances now measurable in physics, of the order of 10 IECM, and the shortest distances in which current notions of space-time probably have meaning, which is of the order of 1033 cm, there is a vast range of scale in which an immense amount of yet undiscovered structure could be contained. Indeed, this range of scale is comparable to that which exists between our own size and that of the elementary particle. Moreover, since the vacuum is generally regarded as full, see Wheeler, 5 and Hilley, 6. For example, with an immense energy of fluctuation, revealed for example in the Casimir effect, 7, it may be further suggested that ultimately the energy of this particle comes from this source. Some of it may also come from the rest energy of the particle. It should be added here that, as happens with the radio wave, the quantum information field may also have some energy. However, as has been made clear in the many analogies given here, this must be negligible in comparison to the energy of the particle which it guides. Though perhaps these might be detectable in new kinds of experiments of the sort suggested in Chapter 1.3, Section 1.3. 6 and Chapter 14, Section 1.4.6, which would go beyond the domain of current quantum theory. A very important further implication of the notion of active information is that in a certain sense an entire experiment has to be regarded as a single, undivided whole. This arises because the motion of the particles can be strongly affected by distant features of the environment such as the slits. On the other hand, in the corresponding classical experiment the slit system can be ignored once the particle has passed through it. And as has been pointed out, a different slit system would produce a different quantum potential, which would affect the motion of the particles in a different way. Therefore, the motion of the particles cannot properly be discussed in abstraction from the total experimental arrangement. This is reminiscent of Bohr's notion of wholeness, but it differs in that the entire process is open to our conceptual gaze and can't therefore be analyzed in thought, even if it cannot be divided in actuality without radically changing its nature. The idea of a pilot wave that guides the movement of the electron was phi-rst. Suggested by De Broglie, 8 in 1927, BUTONLYIN connection WITH the 1. BODY system. De Broglie presented this idea at the 1927 Solvay Congress, where it was strongly criticized by Pauli IX. His most important criticism was that, in a two-body scattering process, the model could not be applied coherently. In consequence, de Broglie abandoned his suggestion. The idea of a pilot wave was proposed again in 1952 by Bohm 10, in which an interpretation for the many-body system was given. This latter made it possible to answer Pauli's criticism and indeed opened the way to a coherent interpretation including a theory of measurement which was applicable over a wide range of quantum phenomena. As a result, de Broglie took up his original ideas again and continued to develop them in various ways. An important part of De Broglie's early approach was to try to explain the assumptions underlying the pilot wave interpretation in terms of what he called the theory of the double solution. This was based on the assumption of a nonlinear field equation which, I11 the linear approximation, approached the ordinary Schrödinger equation. However, for large amplitude, the nonlinearity became important. He suggested that there would exist solutions which would correspond to a stable singularity or pulse when the amplitude was high and would gradually shade off into solutions of the linear Schrödinger equation at larger distances. The pulse would evidently correspond to a particle. He then gave arguments aimed at showing that, in order to obtain continuity of the field, the movement of this pulse would have to be determined by the relation p equals \7s, where s is the phase of the linear part of wave at the location of the pulse. However, AC loser analysis shows that this is actually only a necessary condition and not a sufficient one. Indeed, we can see that it cannot be sufficient by considering the fact that energy and momentum conservation are necessary consequences of the kinds of equations discussed by de Broglie. The momentum in the singularity will be very large in comparison with that available in the extremely weak pilot wave. Therefore, it will not be possible to obtain solutions of the field equations which would lead to the very great accelerations that are in general implied by the guidance relation, e.g. as seen in our discussion of the two-slit interference experiment. Rather, we have seen that to obtain a powerful effect from a very weak field we need something like our concept of active formation. For the fuzzy S, clear Ly depends only on the form of the field and not on the amplitude. In our approach, it is this form which informs the energy of the self-movement of the particle. Therefore, the key difference of our idea from that of de Broglie is that we do not attempt to explain the guidance relation in a simple mechanical way as an effect of nonlinear propagation of fields. Instead, we are appealing to the notion that a particle has a rich and complex inner structure which can respond to information and direct its self-motion. Accordingly, in addition, it should be noted that the concept of the double evolution has never yet been extended to the many-body system, nor is there any idea available as to how this is to be done. On the other hand, as will be seen in later chapters, the notion of active information can quite naturally be extended to the many-body system. For these reasons as well as for those given earlier, it seems that the general idea of something like active information is strongly indicated as needed for an ontological explanation of quantum theory. Returning to a consideration of the Guida-NCE relationship, we emphasize that this by itself is not enough to determine the behavior of the particle. It is necessary also to have some equation that determines the changes of S. In our case this is, of course, the Schrödinger equation. And as we have seen, it follows that the equation of motion is given by the modified form of Newton's law, 3.8, which contains the quantum potential. If we start from the guidance relations, it is then implied that the quantum potential, q, will contribute to the acceleration in the way described above. However, we emphasize once again that the significance of this potential is not that it represents the mechanical effects of attraction and repulsion of the particle by various features of its environment, e.g. the slit system. Rather, its significance is that it represents a contribution to the acceleration of the particle in its self-movement. But it must also be stressed that if the field satisfies an equation other than that of SC Schrödinger, then there will be a different formula for this contribution. For example, as we shall see in chapters 1.0 and 1.2, this actually happens in the case of the Pauli equation and the Dirac equation. Thus far we have mainly BEN considering the individual particle. We shall now discuss in more detail how the concept of probability is used in the theory, in a suitable statistical ensemble. Let us first note that the function p equals r2 has two interpretations. One through the quantum potential and the other through the probability density. It is our proposal that the more fundamental meaning of r, and therefore indirectly of p, is that it determines the quantum potential. In contradistinction to the usual interpretation, its meaning as a probability is only secondary. Its significance in this respect is that it gives the probability for the particle to be at a certain position. Here we differ again from the usual epistemological interpretations which suppose it is the probability of finding a particle there in a suitable measurement t. Indeed, as will be brought out in more detail in chapter 6, the measurement process itself has to be interpreted as a particular application of the theory. This theory is formulated basically in terms of what Bell 1-2 has called beables rather than of observables. These beables are assumed to have a reality that is independent of being observed or known in any other way. The observables, therefore, do not have a fundamental significance in our theory but rather are treated as statistical functions of the beables that are involved in what is currently called a measurement. The above implies THATLL/IL2H as no necessary relationship to probability. That is to say, the two concepts are basically independent. It will be shown in chapter 9, however, that under typical chaotic conditions that prevail in most situations, an arbitrary probability distribution, P, will approach and remain equal to LL/IL2, the latter being an equilibrium distribution. The relationship between P and L/I2 is in this way seen to be contingent. We will indeed discuss, for example, a possibility that PFLIPL2 under certain new kinds of conditions which could in principle ultimately be investigated Even th of p would be equal to 1 1/2 in all those situations that we have been thus far able to investigate. Moreover, a stochastic model of the particle trajectories will also be given in Chapter 9. WH gives an additional possible explanation of WHYP approaches L/2. To illustrate these ideas, let us consider a statistical ensemble of particles. In WHICH, the experimental situation is so arranged that all THE particles have the same wave function. In the usual interpretation, this situation is called a pure state. We discuss the mixed state in Chapter 9. As an example, we may consider our previous discussion of THE2 slit experiment, in which electrons boil out of a hot filament and are then suitably selected to have the same quantum field 3 corresponding approximately to a plane wave, with a definite wave vector k incident on the slits. This is the process that Dirac 1-3 calls the preparation of the measurement, and for Bohr 1-4. It is, of course, part of the experimental conditions. Suppose then that electrons enter the system one by one. Each one will have its own quantum phi Ld, but the forms of all these fields will be entirely The same. However, The particles themselves will have a chaotically varying distribution of initial positions with a probability p equals Li plus W. It should be added that, as we shall show in Chapter 9, there is no way to control or predict these conditions even if the motion is determinate in each individual case. In THE experiment under discussion, our ensemble of particles with the same quantum field, 1/I, will pass through the slit system to be detect T at the screen. EACH individual result is determined by the initial conditions of the corresponding particle. As we have already point out, such a particle must pass through one slit or the other. Butits motion is determined by active information coming from quantum fields that have passed through both slits. Therefore, particles C and be kept away from certain points at which they could have arrived if only one of the slits had been open. As the results accumulate, one will then obtain the bunching of particles that produces the interference pattern in the way that has been described. To sum up then, the idea of probability that we have introduced here is clearly not essentially different from that used in classical statistical ensembles. Thus in no sense is probability being regarded as a fundamental concept. Rather, the properties of the individual system are taken as primary, and probabilities are interpreted in terms of these. The main new quantum properties of matter follow not from the use of the probability theory, but rather from the qualitatively new features of the quantum potential which, for example, imply a novel quantum wholeness such that TLLE behavior of a particle may depend crucially on distant features of the environment. 3. 5 stationary states. We shall now go on to show how our interpretation can be applied to a number of specific examples which help to bring out the meaning of this interpretation. We shall begin by considering stationary states. In a stationary state, the wave function oscillates harmonically with the time. It can be written as 1/z t equals IPO z exp iet/h 310. The quantum Hamilton-Jacobi equation 3.8 becomes E equals v5 2/2m plus v plus q 311. Let us first consider an atom INANS state. In this case the wave function 1/0 z is real, so that one can write s equals 0. This implies that p equals O and E equals v plus q. 312. The above result means that in an S state the electron is at rest. This may seem surprising, since classical physics leads us to expect a condition of dynamical equilibrium for a state of definite energy as an explanation of why the potential does not cause the particle to fall into the nucleus. However, Equation 312 shows that in terms of our interpretation, the stability of the state arises from the fact that the quantum potential cancels out the space variation of the classical potent IAL, leaving a constant En E that is independent of position. It must be remembered, however, that we are interpreting the quantum forces in terms of the new notion of active information that we have intro ducate in the previous chapter. This information info RMS the particle in coal interp re tat ion of the one Boj agatum 43. Its self-motion to contribute an acceleration, vq/m, which, in a stationary state, BAL is the classical acceleration \jv/m. The particle is therefore able to remain in a phi xed position, and the reason it does not fall into the nucleus is that this is prevented by the outward acceleration due to the quantum potential. There is no state more closely bound to the nucleus than the lowest state. Indeed, if we try to find one, we would discover that the repulsive effect of the quantum potential will be much stronger than the attractive effect of the classical potential. This explanation must be contrasted with the one usually given, which attributes the stability of the lowest state to a kind of pressure due to the random motion that is said to be implied by the uncertainty principle 1.5. More generally, however, in a non-stationary state, the balance between ILQ and ILV will not hold. Moreover, if the system is coupled to one with which it can exchange energy, then a transition is possible from one stationary state to another. We shall discuss this process in Chapter 5, where it will be seen that the probability that the particle will arrive at the point z is LT/J, z, 1, 2. In this way we understand how such a distribution of static particles can arise. Nevertheless, one may ask how the stationary values of z are related to what is implied by the usual interpretation for this case, i.e. the probability of obtaining a certain momentum p in a measurement is ICP12, where camp is the Fourier coefficient of the wave function. It will be shown, in fact, in Chapter 6 dealing with the theory of measurement according to our interpretation, THAT. If we measure THE momentum of the particle in a stationary state, the resulting disturbance will change the quantum field and cause the particle to be accelerated by the quantum potential in a way that depends on its initial location. The probability of obtaining a net momentum pin. This process will be shown to be just ICP12. This means that for this case we have reproduced the results of the usual interpretation, but that we have given a different account of the meaning of THSA results. In Chapter 6 we shall go into this question in more detail and show that our account of this process is consistent. Moreover, if one is not aesthetically satisfied with this picture of a static electron in a stationary state, one can go to the stochastic model given in Chapter 9. In this model the particle will have a random motion round an average p equals Vs, and the net probability density in this random motion comes out as p equals 1 z, L2. In principle, all stationary state wave functions can be taken as real. So at the above considerations apply. However, if The energy levels are degenerate, it is possible to form stationary states that are complex linear combinations of these real wave Fu and Ct ions. As an example, let us consider 44 the undivided UN ivory. The 3p states I and their real forms. The basic wave functions are x, f, r, /r, y, f, r, /r, tp3z f, r, /r, 313, where r is the radial distance from the nucleus. From these we can form linear combinations H having a definite angular momentum in any direction, which may with sufficient generality be taken as that of z. The three corresponding wave functions are then t/j plus x plus e, f, r, /r, t/j, tp, z f, r, /r, x, iy, f, r, /r, 314, which represent, respectively, angular momentum projections in THEZ direct tion of plus h, 0 and h. The phases of these wave functions are respectively s plus h/I. So s underscore 0 HP 315, where cent is the polar angle ρ and d the z-axis. The particle momenta for these phases are p plus h4i/p, po, p, 0, hj/p, 316, where p is the radius in cylindrical polar coordinates around the z-axis. Clearly the particle withz component of angular momentum 0 is at rest. But p plus and p underscore correspond to motion in a circle around d the z-axis at an arbitrary value of z, with angular momentum plus or minus h. SEE figure 3.3. The velocity becomes infinite at p equals 0, but as is well known the wave foo nct ion vanishes on this line so that there is no probability that a partition E will be there. The energy is E, V's 2/2m plus V, R, plus Q, with, so that, Coal interpretation of the 1 body iridium 45, Z, X, Fig 11 Re 3, 3, possible particle orbit for the P plus state, as equals 0, AZAP, H2, E equals dash, plus V, R, plus Q, P, 317. In this case PART of the energy H2/P2 is kinetic, while the quantum potential balances V, R, plus H2/P2 only in THE directions of Z and P. We see then THAT by forming complex combinations of real stationary state wave foo and CTONS, we obtain situations in which some of the energy is kinetic. In the C as E of a free particle, the two complex wave functions corresponding to an energy E equals H2K2/2mREXP, XZ, and EXP, IK, Z. These correspond respectively to particle momenta P equals HK and P equals HK. This is an extreme C as E in which, as 1 CANREADILY verify, THE quantum potential is 0 and TH is why all the energy is kinetic. To understand our interpreted T-ion properly, it is necessary therefore to keep in mind that a part of what is thought of in classical intuition as kinetic energy is now treated as an energy associated with the quantum potential. 3. 6 non-stationary states. The general wave function is built out of a linear combination of station Airy state wave foo engines and represents a situation in which the quantum 46 the undivided universe potential is changing with time. A typical case of such a situation is represented by a wave packet that moves with a certain mean velocity inside This wave packet we consider an ensemble of possible positions of the par particle. As an example, let us take the special case of Gaussian wave packet. Initially centered at z0 equals 0 and with mean momentum 0. 0 colones, x, x, j, expk, 2, x, 2, plus xz, dk, 318. Each wave oscillates with frequency w equals hk2/2m and so as a function of Tim we have j 2 hk2t 1/j x t x exp k x plus 1 kz I 2m dk. The evaluation of this integral yields lf x t x iht x2 x2 x plus dash exp 2mx4 x4 plus h 2t2/4m2 319 iht/2m x2 x exp 4x plus h 2t2/m 2 320. The above represents a wave packet which remma ins centered at the origin, but which spreads so that for large values of t, its width is htpt, vt, mxm. This means that eventually the width of the packet corresponds to the spread of distances covered by the particles, which is in turn determined by the spread of velocities, which is equal to v. What the usual picture gives for this process is that there actually is an initial spread of velocities v equals p/m, which is implied by the uncertainty pr incipal ph/z. But in the causal interpretation, the velocity is always well defined at each point. Its value is h8 cents v equals m ox, where cent is the ph as e of the wave function. Since cent equals hx2t/2m 4x4 plus h2t2/m2 321, we obtain h2 xt v equals m2 4x4 plus h 2 t2/m2. Causal interpretation of the 1-6 Audrey 47. It is clear then that the particles are accelerated from zero velocity, and for large values of t the velocity is v equals x/t. This acceleration is evidently a result of the quantum potential, which is h2v2rh2 li x22 lix2 x2 q equals 2mr equals m4ax 4 plus n2t2/m2 4ax 4 plus h2t2/m2 2 322. Evidently the quantum potential decreases as the wave pa it spreads, falling eventually to zero. The picture is then that as the wave packet spreads, the particle gains kinetic energy, the amount depending upon where it was initially in the packet. This clearly denies the common idea to which we have already alluded, that the spread of velocities was there from the start and given by the uncertainty principle. A similar situation was seen to arise in the case of stationary states with real wave functions, where likewise we had a zero velocity. The measurement process disturbed the system so that the energy represented by the quantum potential was turned into kinetic energy. However, the difference is that, in the case of the wave packet, we do not need an external disturbance such as that produced by a measurement process to initiate the acceleration of the particles. 3. 7 are energy and momentum conserved in non-stationary states. It is clear that in a non-stationary state, the amplitude of the wave function, r, and therefore the quantum potential associated with it, will be a function of time. This evidently means that the energy of the particle, 8s/8t, will not be conserved in detail. It will however be conserved on the average, as can be seen by considering J as J Vs 2n2v2r Je equals p x at dx equals r 2 plus v 2mr dx. Putting 1jj equals rexp is/n I and the above, we readily obtain E equals j 2 1/j/7 2 1/j plus lj vlj dx. This is just the ordinary expression for the mean value of the Hamiltonian as given in the usual interpretation. And, as is well known, this is conserved as a consequence of Schrödinger's equation. Moreover, this is enough to ensure that there will be conservation of energy in the classical limit where we neglect Heisenberg's uncertainty principle. Even in the usual interpretation, energy need not be conserved in detail when there is a wave packet. Rather, the correct statement would be that energy is conserved only within the range defined by Heisenberg's principle, i.e., only within the mean width phi e of the wave packet. A similar situation can be found in what are called virtual states in the usual interpretation. These do not conserve the origin AL energy, but in compensation they can last only for a time h/phi e, where phi e is the extent of non-conservation 16. In our interpretation, however, the particle energy is definite but constantly changing. Thus, in the simple case of the Gaussian packet T, we saw that the energy of the particle changes monotonically. More generally, however, the motion will be more complex and the particle may be expected to jiggle in an irregular way. But whatever the motion, the range of variation in the energy will generally be of the order of the mean width phi e of the packet. To see that this is so, let us write for the wave packet, i.e. 0t degree dash 3 et 4 equals exp hl cae tri e plus ae x exp h t dot e, where e is the mean energy of the packet. Then, as at, it is clear that on the average the time dependent part of as I at will be of the order of phi e. Our picture is then that each individual particle moves with an energy close to the average E0, and with changes of energy of the order of phi e, which may in general give rise to a complicated pattern of motion. A similar treatment can be given for momentum, and one will find that a wave packet, even for a free particle, undergoes corresponding changes of momentum as well. However, on the whole these remain more or less within the limits set by Heisenberg's principle. Where does this fluctuating energy and momentum come from? Evidently it can be attributed to the quantum potential which is now a foo-nct ion of time. But as we have seen earlier, the quantum potential is impled by the guidance condition, p equals \js, which, we recall, is to be interpreted a.s being brought about by the activity of the information in the quantum field. The energy and momentum then come from t self movement of the particle, and, as we have suggested earlier, may ultimately originate in t vacuum fluctuations. in such movement there is no intrinsic reason whynergy and causal inte repetition of the one body istem 49. Momentum should always be conserved. To be sure, this conservation holds for an isolated system in the classical line it, but it also holds there in our approach. Its failure to hold quantum mechanically is, as we havecn, of exactly the order as it is in the usual interpretation. In our approach 1 may however say that the electron viewed as a particle is never completely isolated because it is always affected by the quantum field and possibly by the vacuum fluctuations, so that the degree of isolation of any given system is, in general, relative and limited. The energy of the particle is, in fact, strictly conserved only in special cases, i.e., stationary states. We must emphasize again that the one-body case is at best a simplification and an abstraction. For example, in the case of the slits, the particle may be strongly affected by the system through which it has gone, even when it is far away. If we treat the slits and the electron as a single combined system, as we shall show in Chapter 4, Section 4.2, it would then be possible to regard the resulting many-body wave function as expressing a direct non-local interaction between the electron and the slit, along lines to be discussed in more detail in the next chapter. In this case the total momentum of the combined system would be conserved because the slit system would take up the momentum lost by the particle. This would evidently also happen in the conventional interpretation, see Bohr 1.4. Since the slit system is so heavy, its response would be negligible in comparison with the statistical fluctuations of the momentum, so that this transfer would not show up in experiment T. Indeed, whenever we abstract a system from a larger one, the wave function will reflect the overall system from which the abstraction has been taken. Therefore the goal of obtaining complete conservation for what we have wrongly been calling an isolated system will prove to be unattainably. For example, even if we take the slits and the electron as a combined system, the incident quantum field would reflect the collimating slits and velocity selectors which determine the beam incident on the slit system in question. And so, because the quantum potent IL can be large even when the quantum field is small, it follows that we will inevitably have non-conservation of both energy and momentum resulting from the fact that complete isolation of any quantum system is actually impossible. This behavior is reminiscent of Bohr's argument mentioned in Chapter 2, merely that we cannot discuss the properties of a particular system apart from the context of the entire experimental arrangement with the aid of which these properties are observed. But of course, the difference is that we have GIV and a conceptual analysis that explains why all this happens, whereas for Bohr nothing more can be said that can go beyond the description of the experimental phenomenon itself. A beam splitter. Line of flux. Figure 3. 4. Schematic of effect. 3. 8. The Aharonov-Bohm effect. Screen. 8. A particularly interesting application of our interpretation is to the Aharonov-Bohm AB effect 1.7. This effect demonstrates that a magnetic line of flux can produce observable modifications of an electron on interference pattern, even if the electrons themselves never encounter a magnetic field. This is often felt to be mysterious because it is generally assumed that only the field B, X, is physically active and that the VECT or potential A, from which the field is derived via B, equals \7x. A, has itself no further physical significance beyond that of being a mathematical auxiliary in the description of the field. If no magnetic field acts on the electrons, how then can the interference pattern be changed? We now give a brief description of the experiment T. An electron beam from THE source and collimating system, A, is incident on a beam splitter. The two resulting beams go round a line of FLUX and are recombined to meet again at a screen B, as shown in figure 3. 4. When the flux is 0, a certain interference pattern is obtained but for a finite value of the FLUX. This pattern is shifted. This shift was predicted from THE qua NTUM theory, and it has been verified experimentally 1/8. The ordinary quantum mechanical treatment begins with the SCHRO-ling equation for THE case WH air. There is an electromagnetic vector pot ENTIL. A. This is causal interpretation of the 1 Bodr 111 Tem 51. IH TJT slash equals 1 IHV dash colon underscore A 2 T slash 8T2M. C. The above equation has a property called gauge invariance. That is, if we replace T slash by T slash exp9 x and A by a plus Vx x, then we find that T slash satisfies the same Schrödinger equation with A replaced by A. It is evident that the magnetic field B equals Vx A is not changed in this transformation. Thus the vector potential is not fully defined by the fields, but may be changed arbitrarily by a gauge transformation. It is for this reason that the vector potential is regarded as a mathematical auxiliary Y rather than a genuine physical concept. However, although A itself has no unique physical definition, we note that TA dl equals ls Vx A ds H as a unique physical significance for it is not affected by the gauge transformation. A equals a plus V x because F Vxdl vanishes with a line of flux of strength Ct. The vector potential is A equals underscore plus or minus underscore cent 27 rr, where is THEUNit vector in the direction. Since the magnetic field is 0 outside the line of flux, it follows that A should be derivable from a potential in this region. However, this potential cannot be single-valued, or else the FLUX Ct inside the circuit would have to be 0. Let represent this potential. We have F V dr equals Ct. This implies that there must be a CUT somewhere in this space which we are not allowed to cross, so that in this restricted space, the potential is single-valued. As long as we restrict ourselves in this way, we may write Schrödinger's equation as IH A T slash J equals 1 IHV V dot 2 T slash J AT2M C. If we make the gauge TRNS formation T slash equals T slash EXPIE slash C, we find TH at 1 slash slash satisfies the simple Schrödinger equation. IH AT slash J equals 1 IHVJ 2 T slash J AT2M. We can therefore write for the actual solution IE dot X T slash J equals I slash EXP This means that the flux line will affect the phase of the solution by a factor exp, x/c. In general, x will be different in the two BEA1T1B, and when the two beams come together, the relative phases will therefore have been altered by E, F, E, V, dl equals E. In this way we predict a fringe shift T, which we cannot explain as long as we believe that only the magnetic field can affect the electron. The above treatment is an approximation, but an exact treatment gives the same result 17. However, in our interpretation there can be additional quantum forces. Indeed, if we define the velocity as p evs e v equals a m m, we can show from Schrödinger's equation that m e dv m dt equals m dt plus m v equals vx vxa vq, where q is the quantum potential defined in the usual way as h2/2m v2r/r. Evidently r is not altered by the gauge transformation, which affects only the phase, and so q is gauge invariant. We see then that in general, in addition to the magnetic force, there is a quantum force which is present TeV n WHNT magnetic field is 0. This is basically how the effect is to be explained. It is clear that Q will be large, only WHERER is changing rapidly. There will, of course, be a small quantum potent IAL at the edge of the BEM, but the PAR-TIC LE deflections DUE to this correspond only to what is, in the usual interpretatio n, called diffraction of the beam at its edge GES. The main variation of R will occur where the two beams overlap to produce E interference. The quantum potential will be E large, indeed it is juice TW is residential po ns IBLE for THE interference, as WE have seen, for example, in the two-slit X prime E and T. The phase shift will THEN alter the quantum potent IAL in a significant way, and this WILLEXPLAI and the origin in the shift and the interference pat TERN. This pat TERN H as BEN calculated for a case I n WHICH the beam I S SPLIT BYA pair OF slits WITH the LINEOF mag NET ICFLUXI N. The geomet RIC shadow between them. The trajectories are shown in figure Re 3. 5. One can see how causal interpretation of the one Baudrillard 53. Figure 3. 5. Trajectories for the AB effect. 54. The undivided universe. Figure 3. 6. Quantum potential for the AB effect. The orbits are shifted so as to displace the net interference pattern. The corresponding quantum potential is shown in figure 3. 6 and can be seen to be similarly shifted, see unpaired WITH, for example, figure 3.1. The above completes the explanation of THEAB effect. However, it should be noted that this explanation H has an interesting further implication. i.e. that the vector potential actually have a physical effect at THE quantum level. The vector potential enters into Schrödinger's equation in such a way as to alter the wave function, and this leads to the corresponding force in the acceleration of the particle. However, in the classical limit this effect becomes negligible, and here it may be said the vector potential is physically not effective. The mistake in the common way of talking about this is the tacit assumption that the classical idea about the vector potential also holds quantum mechanically. Chapter 4. The many-body system. We shall now go on to consider the many-body system, in which we shall see, in several striking ways, a further development of the difference between the classical and quantum ontologies, along with new concepts that are required for the latter. 4.1 The ontological interpretation of the many-body system. Let us begin by considering the two-body system. The wave function cent R1, R2, t satisfies the Schrödinger equation. 4.1. Where \71 and \72 refer to particles 1a and d2 respectively. Writing cent equals REXP is /h, and defining p equals R2 equals cent 1/, we obtain where and h 2 \72 plus \72 r q equals __ I 2 mr 4.2 43 8p 75 plus \71 p \71s/m plus \72 p \7 2s/m equals 0. 4.4. As in the case of the1body system, equation 4.2 can be interpreted as the quantum Hamilton-Jacobi equation with the moment Ta of the two particles being respectively and d. 4.5. The Menrabadi item 57. The above is evidently an extension of the guidance relationship for the two-body system. It implies that the particles are guided in a correlated way to the significance of this correlation. One can consider the quantum potential L, Q, which follows from the assumption that satisfies Schrödinger's equation. As can be seen from equation 4.3, this potential contains R both in the denominator and the numerator, so that it does not necessarily fall off with the distance. We have already seen that for the one-body system, this means that the particle can depend strongly on distant features of the environment. In the two-body system we can have a similar dependence on the environment, but in addition, the two particles can also be strongly coupled at long distances. Their interaction can therefore be described as non-local. This is the first of the new concepts implied by the causal interpretation that comes out in the many-body case. Going on to the n-body system, we would obtain in a similar way, so that the behavior of each particle may depend non-locally on the configuration of all the others, no matter how far away they may be. As in the one-body case, we may take p equals R2 as the probability density, but this now is in the configuration space of all the particles. The Schrödinger equation will imply the conservation of this probability, see equation 4.4. Therefore if p equals R2 initially, this will hold for all time. And as explained for the one-body case, if p1 R2 initially, typical chaotic movements will bring about p equals R2 in the long run as an equilibrium distribution, as we will show in detail in Chapter 9. For several centuries, there has been a strong feeling that non-local theories are not acceptable in physics. It is well known, for example, that Newton felt very uneasy about action at a distance, 1, and that Einstein regarded it as spooky too. One can understand this feeling, but if one reflects deeply and seriously on this subject, one can see nothing basically irrational about such an idea. Rather, it seems to be most reasonable to keep an open mind on the subject and therefore allow oneself to explore this possibility. If the price of avoiding non-locality is to make an intuitive explanation impossible, one has to ask whether the cost is not too great. The only serious objection we can see to non-locality is that, at first sight, it does not seem to be compatible with relativity, because non-local connections in general would allow a transmission of signals faster than the speed of light. In later chapters we extend the causal interpretation to a relativistic context and show that although non-locality is still present, it does not introduce any inconsistencies into the theory, e.g. it does not 58 the undivided universe imply that we can use the quantum potent IAL to transmit a signal faster than light. While non-locality as described above is an important new feature of the quantum theory, THR is yet another new feature that implies an even more radical departure from the classical ontology, to which little attention has generally been paid thus far. This is that the quantum potential, Q, depends on the quantum state of the whole system in a way that cannot be defined simply as a pre-assigned interaction between all the particles. To illustrate what this means, we may consider the example of the hydrogen atom, whose wave function is a product of f, z, where z is the center of mass coordinate, and g, r, where r is the relative coordinate. Il equals f, x, g, r. The quantum potential will contain a term representing the interaction of electron and proton. Q equals underscore, I underscore, V2G, R, 2G, R, where I is the reduced mass of the electron. In the S state, Q is a function only of R itself, while with a linear combination of S and P wave functions it is easily shown to depend on the relative angles, 0 and cent, as we LL. Evidently, it is impossible to find a single pre-assigned function of R, which would simultaneously represent the interaction of electron and proton in both THS and P states. And, of course, the problem would be still more sharply expressed if we brought in all the other states, D, F, etc. The relationship between parts of a system described above implies a new quality of whole ens of the entire system going beyond anything that can be specified solely in terms of the actual spatial relationships of all the particles. This is indeed the feature which makes the quantum theory go beyond mechanism of any kind. For it is the essence of mechanism to say that basic reality consists of the parts of a system which are in a pre-assigned interaction. The concept of the whole, then, has only a secondary significance, in the sense that it is only a way of looking at certain overall aspects of what is in reality the behavior of the parts. In our interpretation of the quantum theory, we see that the interaction of parts is determined by something that not be described solely in terms of these parts and their pre-assigned interrelationships. Rather it depends on the many-body wave function, which, in the usual interpretation, is said to determine the quantum state of the system. This many-body wave function evolves according to Schrödinger's equation. Something with this kind of dynamical significance that refers directly to the whole system is the many BOD1Y1 Tem 59. Thus playing a key role in the theory. We emphasize that the IA the mode fundamental/le new aspect of the quantum theory. The above described feature should, in principle, apply to the entire universe. At first sight this might suggest that we could never disentangle one part of the universe from the rest t, so that there would be no way to do science as we know it or even to obt in knowledge by the t are additional methods of finding systems that can be regarded as at least approximately isolated from their surroundings. However, it is actually possible to obtain such approximate separation in spite of the quantum wholeness that we have described above. To see how this can come about, let us consider the special case in which the wave function 1jl, r1, r2, t, can be written as the product cent, r1, r2, t, equals cent a, r1, t, cent b, r2, t. The quantum potential then becomes the sum of two terms, where and qb, r2, t, equals underscore vrb, r2, t. 2mrb, r2, t. In TH's case the two systems evidently behave independently. In Chapter 8 we will show that there is a widespread tendency for such factorist wave functions to arise in typical situations that prevail in the present stage of the development of the universe. Moreover, we shall also show that in the classical limit where the quantum potential is negligible, non-local interactions will for this reason not be sine phi cant. We may say that while the basic law refers inseparably to the whole universe, TH's law is such as to imply that the universe tends to fall into a large number of relatively independent parts, each of which may, however, be constituted of further subunits that are non-locally connected. Therefore, we can deal with these relatively independent parts in the traditional way, as we do our experiments. We have seen that quantum theory implies a radically new behavior of matter in several respects. It has been shown that all of this can be understood in terms of our notion of active information applied, not only to the one-body system, but also to the many-body system. Of course, in a purely logical sense, the theory could be said to be defined without this notion, and could, of course, be thus expressed in a logically consistent way. But it is a key part of our intention in this book to help make the theory more intelligible in an intuitive sense, and not merely regard it as a system of equations from which could be derived algorithms permitting a calculation of interesting results. We feel that at least something like the notion of active information would be needed in any attempt to do THs, e.g. to account for quantum interference and the peculiar non-local properties of the many-body system in an intuitively understandable way. We emphasize again what we have said in Chapter 3, that the notion of active information responds to a tremendous range of common experience. We have generally devalued this sort of experience as far as physics is concerned and have assumed that physical laws should contain only mechanical concepts such as position, momentum, force, etc. When it is found that these do not apply coherently in a quantum context, then as explained in Chapter 2, it is effectively assumed that all we can do is to use the quantum formalism as an algorithm to calculate the probabilities of experimental outcomes. But what we are pointing out here is that if we suitably extend the kind of concepts that we are willing to admit into physics, e.g. to include active information, then we can obtain a much better intuitive apprehension of the theory. This, in 2Rn, may help guide our thinking in physics into new directions, some possibilities of which we shall discuss in chapters 1.4 and 1.5. Let us now consider the many-body system from this point of view. The wave function is defined in the configuration space of all the particles Its effect on the particles is determined by the pH as Es and the quantum potential Q, both of which depend on Ly on the form of the wave function, and not on its amplitude. Along the lines discussed in Chapter 3, we may therefore regard the wave function as containing active information. But this information is ordered in the configuration space rather than in the ordinary space of 3 dimensions. The fact that the wave function is in configuration space implies that we have to look more carefully into the meaning of active information in such a context. First of all, we may consider its implications for all the motions of the particles. These now respond in a correlated way to what is, in effect, a common pool of information. This information guides the particles according to the condition pi equals yi5, r1, rn, t, /mwhich, of course, leads to a generally non-local quantum potential that we have re-add y discussed. Different linear combinations of the wave functions will give rise to different pools of information, which in turn will give rise to corresponding differences in THE behavior of the system. When THE wave function is factorized into independent products, this will correspond to having independent pools of information. There is therefore an objective difference between systems which are wholes guided by a pool of common information and systems constituted of independent parts guided by separate pools of information. We may contrast this possibility of objective wholeness with what happens in classical mechanics, in which the notion of a whole is a subjective convenience for describing the behavior of what are in reality a set of independently existent parts in interaction. The fact that the wave function is in configuration space clearly prevents us from regarding the quantum field as one that carries energy and momentum. THAT was simply transferred to the particles with which it interacted, thus effectively pushing or pulling mechanically on the latter. This is a further factor in addition to the form dependence of the activity of the field, which leads us to consider the interpretation of this field as active information. The multidimensional nature of this field need not then be so mysterious, since information can be organized into as many sets of dimension as may be needed. We may illustrate these notions by looking at the interference experiment as a two-body system. To simplify the discussions, we assume that the slit system is rigid and can be described in terms of a single center of mass coordinate T, y. Clearly the mass, m, of the slit system is much greater than the mass, m, of the electron. In this C as E, it is well known that the wave function can be approximated as \2 equals L/J, Z, Y, F, Y. The quantum potential is __H2 V R Z Y \LIF Y I plus 2 \711 R Z Y \711 IF Y I J Q 2 MR Z Y plus MIF Y IMR Z Y if Y I. In the limit that m:\m, the part of QTHAT acts on the electron reduces to H2V R Z Y 2MR Z Y. The above is essentially THE same as THATOBTAIN in the one-body system. But the important difference is that it is a Fu NCTION Z Y. Therefore, as has indeed already been explained in Chapter 3, Section 3.7, the energy and momentum are not coming from the quantum field. Rather, the electron and the slit system are informed to respond in a correlated way by the pool of information that is common to both. The slit system is, of course, so heavy that its response can be neglected. But still, from the conceptual point of 62 THIRD-WORLDISM universe view, we have to look at this process as a kind of interaction between the electron and the slit system rather than as an effect of the quantum field in space-time. The one-body treatment is therefore an abstraction which leaves out this essential feature. Finally, we wish to point out that even the classical potential can be looked at as representing the effects of active information. To do this, we recall THAT. For example, in a two-body system, each particle is guided by the total phase s, x1, x2, of the wave function. As we have seen earlier, this guidance condition combined with Schrödinger's equation implies the extended quantum Hamilton-Jacobi equation. In the above equation, V and Q appear in essentially the same way. In fact, both describe certain effects of the guidance condition and therefore of active information in the wave function. What is then the difference? The difference is that Q describes a part of the change with time of the active information. THAT depends in a non-local way and in detail on the whole wave function, i.e. what is commonly called the quantum state. On the other hand, V describes a part of the change of this information that is independent of all this and that is generally low cal in the way that it acts. This part is what manifests in the classical limit. pH is xh as already developed in such a way that the classical potential V can be regarded as an actual existent field distributed throughout three-dimensional space. This field can be regarded as the source of the change of information with time brought about by V in the Hamilton-Jacobi equation. It obeys a wave equation implying the detailed conservation of energy and momentum. Therefore we can, if we wish, attribute the energy and momentum to the field and thus imagine it is flowing out space and into and out of the particle. But as we have seen, this picture could not be coherently applied to the quantum potential. Moreover, as we shall see in Chapter 1.1 when we consider our interpretation of the quantum field, the picture of a continuously conserved flow of energy and moment will not also apply except as a limiting C as E holding only INTHE classical approximation. We shall now give two further applications of the notions that have been described in this chapter, which will make the physical meaning of our interpretation clearer. The Man 1 Bod 11 TEM 63 /91 The chemical bond. We begin by considering the chemical bond. Classically it is incomprehensible why chemical bonds can form, and foo are there more, why there are 80 many specific kinds of such bonds. It is well known that the quantum theory has explained this in a generally satisfactory way. But this has been achieved at the expense of a loss of intuitive comprehension of what is involved physically in such a bond. In our interpretation we obtain a more intelligible way of understanding this. We shall illustrate these ideas in terms of the hydrogen molecule with its covalent bond. The molecule consists of two protons whose coordinates we label by Za and Zb, and two electrons whose coordinates are represented by R1 and R2. The interaction between the particles are of the Coulomb type. This can be expressed as one of the usual procedures, due to Reitler and London, is to solve the Schrödinger equation for this case approximately, beginning with functions that are solutions when the nuclei are very far apart. We then have two separate hydrogen atoms, each in an S state. Because the protons are so heavy we can, in the first approximation, regard them as fixed in specified positions. One approximate solution of the combined system is then 4,6. This represents two separated hydrogen atoms A and B in their lowest s states in which the phi-rst electron is in atom A, while the second is in atom B. Another solution is 4-7, in which the first electron is in atom B, while the second is in atom A. These two states evidently have the same energy, and as is well known. From standard perturbation theory, one has to start from a suitable linear combination of W1 and WLL in order to obtain a series of approximations to the wave function when the particles come closer together. Because of the symmetry of 6 between R1 and R2, it follows, as can easily be shown, that the appropriate linear combinations are 4.8. From this we obtain 4.9. And noting that TJJ1 and 1/J11 are real because 2 represents the lowest s state. The energy of these states comes out as a function of the separations T/equals LZA, ZBI. They are shown in figure 4.1. Evidently the state corresponding to E plus gives rise to an attraction BE between the protons at medium distances, which turns into a repel ion at short distances. On the other hand, the state corresponding to E leads everywhere to a repulsion. There is no way to understand this energy difference solely in terms of a preassigned interaction of the particles constituting the molecule E. For, since the wave function is real, the momenta of all the particles are zero and the energy is just sum of the classical interaction energy 6 and the quantum potential 410. To obtain the quantum potential we must first obtain an expression for R from 4.9, 4.6, and 4.7, we see that R2 equals P2, R1, ZB, cent I2, R2, ZA, plus 2 cent I, R1, ZA, cent I, R2, ZB, cent I, R2, ZA, cent I, R1, ZB. The many-body item 65. This shows the quantum potential will be a function of all the particle coordinates, implying a non-local interaction with the kind of quantum wholeness that we have described in the previous section. This latter means that even if all the particles are in the same positions and have the same velocity, v equals 0 for the two solutions, their energies will be different. This difference evidently has to be attributed to the quantum potential, which is differ. And for the two cases, as we have already seen, for the case of W+, the molecule will be stable, while for W_, it is not. The force that holds the molecule together and that determines the specificity of the chemical properties is thus a particular case of the non-locality and wholeness, which is, as we have pointed out earlier, the most essentially new feature implied by the quantum mechanics. In terms of the usual interpretation of the quantum theory, we have no intuitive notion of the difference between the states 11 plus and W_, nor indeed what it means to form a linear combination of states. Yet it is just this which is responsible for a vast range of chemical properties. In our interpretation, these properties are understood through the notion that the wave function of a molecule constitutes a common pool of information that guides the activity of all its particles in related ways along the lines discussed at the end of the previous section. Different wave functions, constituting different pools of information, will then give rise to well-defined differences in the behavior of the system. 4.3.2 Superfluidity and sub-ERC conductivity. Superfluidity and superconductivity provide a very good illustration of how a common pool of information can give rise to strikingly new properties of a many-body system. It is well known that at low temperature many substances can go into a new state in which currents, either of atoms or electrons, can flow in infinitely without viscosity or resistance. This state is stable only up to a certain temperature. At WHH the property disappears. These super flow properties have been explained as a consequence of the many-body Schrödinger equation, but this explanation is very abstract and gives little intuitive understanding of how the phenomena in question come about. Our discussion is aimed at illustrating how the quantum potential makes superfeto possible in its more common forms such as ordinary low temperature superconductivity and superfluidity in He. 4. It is not, however, intended to be a detailed treatment of all the complexities involved in the above, nor will we consider the less common forms of superfeto such as high temperature and gapless superconductivity and superfeto in He. 3. We begin by discussing the case of superfluidity because this is easier. 66. The undivided universe. Both conceptually and mathematically, but, as we shall see later, basically the same considerations apply to superconductivity as we have restricted this term above. What is essential here is that helium nuclei are bosons, and that the electron pairs that are responsible for superconductivity are also effectively bosons. At first sight, the problem of superflow in He. 4. Seems to be almost impossibly difficult because the helium nuclei repel each other with such strong forces that it would appear that no reasonable approximation could be made. However, it has been shown by Pines 3 THAT, as a consequence of the short-range particle correlations, the system could be described as a collection of quasi-particles with only weak soft core repulsions between them. In the first approximation we can neglect these latter, so that a good start point for the condensate wave function is one in which all the particulae are moving at the same velocity t equals k/m. This wave function, which is evidently symmetric, is 411, where Ri represents the coordinate of the J1H particle and where we are assuming units in which h equals 1. However, the fact that all the particles are moving at the same speed is not sufficient by itself to account for the properties of superfluidity. What is required, in addition, is that this state be stable under external perturbation. That is to say, under an external disturbance, a particle should not be able to drop out of the common velocity v equals k/m, by giving up energy and going to a lower velocity v equals k q0/m. To account for this we follow along the lines of the explanation given by Landau 4, Bogoliubov 5, and Feynman 6. A key point for such stability is that it should not be possible to change the momentum of a single particle in this system from k to k, q0 without affecting the others in such a way as to bring about a net increase in energy of the whole system. Basically, this stability arises because of the symmetry of the wave function. Indeed, it is easily seen that without this symmetry, there can be no such stability. Thus consider, for example, what would happen if the wave function had no particular symmetry. We could then obtain an excited wave function by giving momentum to a single particle, say the ith, which would give rise to a wave function phi equals expiq0 Ri 1110. The many BOD item 67, or L I equals expi k percent Ri j cent I 412. Clearly this will be a possible solution of Schrödinger's equation, and 80. There is no thing to prevent this loss of momentum by slowing down one of the particles independently of others. However, for bosons, the wave function has to be symmetric. The lowest state of excitation corresponding to a loss of momentum, q0, will be it equals L exp iq0 RILLF0 413 J. If we neglect interactions, this too would permit the same kind of loss of momentum we described above. However, as shown by Bogolubov and by Feynman, when interactions are taken into account, the system is capable of supporting sound waves with frequency W equals W, Q. The term P, Q0 equals Lj exp Q0. Rij is well Kn known to be the Fourier coefficient of the particle density. In such a case it is P, x, equals I. 8, z, Rj. 414. Therefore The wave Fu and Cetian, 413, represents The excitation of a sound wave, while the equation, 412, which is a wave function of no particular symmetry, represents no change of particle density and does not represent such a wave. P, Q0, thus describes a collective deviation from equilibrium, whose energy is E equals W, Q0. At low frequencies, W, Q0, will satisfy the linear relationship W, Q0 equals QV, where V is the velocity of sound, while at higher frequencies it deviates from this relation. As explained by Feynman, 6, these deviations are associated with roto ns stability WILL be achieved if the energy required to create a wave of excitation is greater than the kinetic energy given off by the P article for all Q0. This requires that E, EO, K, QO, 2K2. O underscore 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 plus WQ0 2M2M KQOQG O plus WQO M2M 415. The above will follow if W, Q0, K, Q0 slash MORIF, V equals K, slash M, W, QO, slash QO, where V is THE velocity of flow W. This is, of course, just the well-known condition obtained by Landau, 4. 68 Undivided Univtrist. It has to be pointed out that the Landau condition does not determine the actual maximum velocity in typical experimental situations such as flow in 2BES. Indeed, this is in general considerably less than that given by the Landau condition and is determined by Fu. Other factors such as the existence of rodents and vortex structures of various kinds, Feynman 6. However, the Landau condition is evidently still satisfied in such cases. Moreover, it is relevant to understanding the existence of superflow because if it is not satisfied, the particles can be scattered out of the common velocity, thus making superflow impossible. Clearly, no matter what the detailed structure of the vortices may be, the understanding of superflow depends basically on this sort of explanation of why the particles move stably together with a common velocity. To explain this stability intuitively, we shall have to show how the quantum potential implied by the wave function, 413, ACTUALLY constitutes AC tiv information that keeps all the p particles moving together in spite of perturbations that would otherwise scatter them. To do this we shall have to calculate how the wave function, 413, changes when a perturbation is introduced. To simplify the problem we assume a small perturbing potential, V, which, of course, has TOBE a symmetric function of all the particles. We therefore write V equals LV, Rj, J. With the aid of perturbation theory, we find that where W equals LL, V, Q, X, Q, RJWO, J, QTO, Q, 416, 417. In computing E9IT will be sufficient for the illustrative purposes of this discussion to restrict ourselves to values of Q small enough so that the collective excitations will have the linear frequency relation W, Q, equals QV, where V is the velocity of sound. This gives us E equals E0, E equals QV, plus Q2K, Q, 9, 2 Rn 418. Evidently, as long as V, K/M, this denominator will never vanish, and so there will be no real transitions, i.e. the perturbation involves only what a.re, in the usual interpretation, called virtual states. When rotons are taken into account, the limiting velocity of superflow will in general be less. The manra 6OD11 1R1 Tem 69. Then V, but the above condition will still be satisfied. Evidently we may reasonably assume that V, Q, becomes negligible for Q/MV. This means that the potential is soft, which is implied by the fact that its high Fourier coefficients are small. We then obtain LT equals L, L, V, Q, EXP, IQR. It QV, 1, K, Q/MV, O, IQ, 419. Once again, for the purposes of illustration, we may assume that K/MV. This gives V, Q, KQ. It equals L, L, EXP-1 QRI1 plus it O, QV, MV, IQ, 420. To further simplify the calculation, we assume a V, R, that gives a FOUR ear coefficient V, Q, equals QXP, Q. Dot X. This implies that writing V, R, X2, underscore X2 R2, 1, X, dot X2 plus R2, 3, A, M, P2, plus R, 2V, and B, N, dot X2 plus R, MVI, 4.21. WH air A and dB are suitable constants, we obtain N. 422. The probability density is, in the first approximation, P equals L1 TA L2, 1 to 2, M, L, 4.23, and the courant density of the I1 HP article in the direction Q will be Qj, equals L1 tol 2, K, Q, colon dot, 2Q backslash 7, dot XL, 2, 4.24. The veloc ITY in the direction QWILL be given by Q, J, QI, VE, equals P, L1 to L2, 1 to 2L, M, 4.25. According to equation 423, the distribution is altered in the neighborhood of the perturbation. If the perturbation is repulsive, the PA radicals will on the whole be pushed away, and vice versa if it is attractive. According to equation 424, the current will change in a corresponding way. This implies that for a repulsive potential, the particle will first move away from the PE perturbing obstacle. But because the perturbed wave function vanishes at infinity, the particle will eventually move back and will be left with its original velocity, thus implying there is no scattering, as shown in figure 4.2. In ordinary scattering processes, the energy conservation condition between initial and phi-NAL states can be satisfied, and we therefore get a real transition into a scattered wave. In the C as E of a superfluid HO Weaver energy conservation CANNOT be satisfied, so we get only virtual contributions to the wave func DON. If we evaluated the quantum potential, it would be seen that these latter contributions imply an additional force on the particle, which accounts for why it is first accelerated away from the obstacle and then brought back to its original velocity. Since every particle will behave in essentially the same way, it follows that the liquid as a whole will flow around the obstacle and then reconstitute its flow in its original direction. This is basically our intuitive explanation of why the state of superflow is stable. This is evidently a purely quantum mechanical response of the whole system. It involves not only non-local interactions due to the quantum potential, but also the irreducible quantum wholeness implied by the fact that this interaction cannot be expressed in terms of a pre-assigned Funcition of the particle coordinates. All that we have said here also applies to superconductivity in WHH. The charge carriers are electron pairs that act like bosons. The details can be found elsewhere 7, but the essential point is THAT, as with He4, there is the Man 11 Bodraridum 71. A gap representing the energy needed to remove an electron pair from the common velocity. It will follow then that if there is an obstacle, the charge carrier will go round it and reform without scattering in the same way as happens for He4. In both cases The stability of the state of superflow can be understood further with the ID of the notion of the active information that we have discussed earlier in section 4.2 of this chapter. Here we pointed out that EA.ch particle is guided according to the relation V equals Vs, R1, Rn. It may then be regarded as part of the common pool of information accord ding. To WHEA.ch particle determines its velocity. One can say that in the state of superflow, this information brings about a coordinated movement of a point to the particles that can be thought of as resembling a ballet dance, in which a point to the dancers separate in a systematic way to go round an obstacle and then reform THEIR original pattern. As the temperature TURE goes up, THE property of superfluidity disappears. In terms of our approach, this is because the wave function breaks up into a set of independent factors which can, as pointed out earlier, be thought of as representing independent pools of information. The electrons will then no longer be guided by a common pool of information and WILL, therefore scatter off obstacles RATHER then go round them and return to their original movement. In this way they begin to behave like an unorganized crowd of people who are acting independently and get in EA.ch others' way, so that the property of superflow disappears. This means that the guidance condition and the quantum potential implied by it can, under certain conditions, have the novel quality of being able to organize THE activity of an entire set of particles, in a way that depends on a pool of information common to the whole set. This behavior is reminiscent of OH and is found in living beings which are similarly organized by a common pool of information that is now thought to reside in the genes, and also society which is evidently organized by common pools of information of yet another key and D. Thus a considerable similarity is seen between the micro level and other levels, which we shall discuss in more detail in Chapter 1.5. Chapter 5. Transition processes considered as independent of observation. In the usual interpretation, it is an essential feature that transition processes can only be discussed in a context in which they are observed in a measurement process. In an ontological approach such as ours, it is, of course, necessary to discuss transition processes taking place on their own, independently of their being observed. In this chapter we shall show how this can be done. We shall begin with the simple example of barrier penetration and then go on to consider transitions of electrons in atoms from one level to another. In developing our ideas, we shall also show that in our interpretation, the quantum theory implies two general tendencies that oppose each other. 1. A tendency for wave functions to spread and become less well defined in space when the system is isolated. 2. A tendency for these functions to narrow down the range in which they have an appreciable effect when interaction with a background takes place. We shall call this latter tendency self-definition. It is essential to take this into account if we are to understand how the universe can be in a fairly well-defined state at any given moment, in spite of the tendency to become less well-defined because of the general spreading of wave functions. On this basis, we are able to discuss the states of things without any need to refer to a measuring apparatus which, in the usual interpretation, would cause the wave function to elapse to a more definite state. 2. Figure 5. 1. Square potential barrier of height v. 5. 1. Example of barrier penetration. Let us consider a one-dimensional square barrier of height v and thick kns. Located between x equals 0 and x equals a, as shown in figure 5. 1. We assume a particle of momentum pi in region I incident from the left with energy ev. In accordance with standard procedure, we also assume a reflected wave in region I with the same moment For region 3 we assume only an outgoing wave, which evidently will also have the moment ump. If we write the wave function in region 3 as iln 1 equals aexp ips, 5 1. Again setting h equals 1, then the sola ti on in region I will be the linear combi nation. 3 2 equals b expqx plus c expqx, where q equals j2m, v, e. In region I the solution will be il1 equals dexp ips plus eexp ips. 5 2. 5 3. It is necessary then to provide for the continuity of the wave function and its derivative at x equals 0 and x equals a. This will determine the ratios of the coefficients and therefore the transmissivity and the reflectivity 1. If the barrier is high and thick k, the transmitted wave will be small and the reflected wave very nearly equal in intensity to the incident wave. We then form a wave packet by integrating t slash over asm all range of p. This packet will be incident from x equals 00 and will come up to the barrier where some of it will be transmitted, but, in general, most will be reflected. There will be a pe riad du ring which the incident and the reflected transition processes considered as indep and end of absem jashin 75. Wave packets overlap. If the transmissivity were 0, as it would be for an infinite barrier, the incident and reflected packets would form summit hing. Very close to a standing wave which would have essentially a real wave function. The velocity would therefore be 0. But if the reflected wave is Not quite as strong as the transmitted wave, there will be a net, in general. Small velocity in the region in which incident and reflected waves overlap, and as can indeed be verified from the formula. V equals _1 _ T slash VT slash T slash VT slash 2 miles TJ, T slash J. 5.4. When the incident wave packet disappears and only the reflected wave packet remains, the speed will once again be p slash m, but of course in the negative direction. There is a complicated variation of velocity inside the barrier, but for the wave packet that has passed through, the speed will once again be p slash m. But this time in the positive direction. The trajectories for the C as E of a Gaussian wave packet with E equals v slash 2 have been calculated for a range of initial positions of the particle within the wave packet too. Clearly their behavior will depend on the quantum potential. This is shown as a function of x and t in figure 5. 2. As the packet comes up against the barrier, we can see the quantum potential developing as a function of time in the region of overlap of the incident and reflected wave packets. We see and also see how the quantum potential modifies the potential inside the barrier in a rather complicated way. In general, the quantum potential will lower the barrier height, thus permitting particles to enter it. This of course removes the mystery as to how barrier penetration is possible. For such penetration depends on the total potential V plus Q and not just the classical potent IALV alone. But it also depends on whether the net potent IALV plus Q is greater than E for the whole period in which the particle is inside the barrier. It is clear from the figure that this will in turn depend crucially on the initial location of the particle, because the quantum potential remains low only for certain periods of time and indeed may have spikes in certain places that would tend to reflect back a particle positioned there. All of this can be brought out clearly by considering the trajectories shown in figure 5. 3. We can see that only the particles that happen to be at the front of the wave it can even enter the barrier. But even most of these will be turned around before they are able to go through. There is, however, a critical trajectory, which divides the trajectories that go through from those that do not. This evidently resembles a bifurcation point of a kind which is typical of the nonlinear equations describing unstable SYS TEMS. Indeed, it is clear that even though THE equation for the wave function is linear, the quantum potential can be a highly nonlinear function of the coordinates of the particle. Therefore, we actually have here an example of such a bifurcation point. Of course, we have here only a very simplified and abstracted system. In real systems with many particles and complicated potentials, there will be many such bifurcation points, implying something CL08E to chaotic motion. 3. But even in this simple system we can see the germ of the process by which quantum transitions can take place. The particle may go either one way or another, thus having an LL or nothing character. When we discuss the transitions in atoms, we will see this character coming out in a more complex context. All the basic concepts required to understand quantum transitions from a purely ontological point of view are already implicit in the simple example of barrier penetration given above. The essential point is that the wave packet H is split into two distinct parts, which, in this case, will never meet again. As one goes to plus OO and the other goes to OO, the particle must enter one of these packets, because there is no probability of being in between where the wave function is 0. We may conveniently describe this process by thinking that the two Wave packets correspond to two distinct channels. Which channel the particle will actually enter is determined by its initial position in the incident wave packet. Once the channels are formed, they remain separate. The probability of being in a given channel is found by integrating LT/IL2 over all the particle positions corresponding to that channel, and it is easy to show that this is just what would be obtained in the usual interpretation, e.g. in computing the probability of transition. Since the channels do not overlap, the quantum potential in each can be calculated as if the other were not present. The same also holds for the guidance condition. Therefore, in effect, the system behaves as if it is in one of the channels only, with the appropriate probability that this is the case. We have, in this way, explained how a quantum transition takes place on its own, without the need to bring in a process of observation. But this raises an important question. Suppository E, for example, that the particle is in the transmitted channel, corresponding to a wave function of very low intensity. Its physical properties are determined by this very weak quantum field, while the much stronger field corresponding to the reflected channel H has no effect. Of course, as long as the channels do not overlap, we can understand THIS, because the quantum field does not act mechanically, but rather, as we have already discussed, it acts as information that guides the particle in its self-movement, and in such action T.E intensity of the field does not matter. Nevertheless, one may raise the question of what would happen if the channels were made to overlap again. For example, in 2 or 3 dimensions, The experiment could be arranged to reflect both of the quantum fields into The same region of space. And this happened, the larger field would overwhelm The smaller one, and the behavior of the particle would be radically altered. In other words, while the information in an empty channel may not actually be active on the particle at a given moment t, it may have the potentiality to become active later. Therefore, one cannot say that the transmit particle is in a state that is entirely independent of the reflected channel. This would, at first sight, seem to put in doubt our claim of having explained the transition process without the aid of an observation which would cause the wave function to collapse irreversibly and finally, for example, to The transmitted state. In this connection, however, it must at first be pointed out that the possibility of interference of the two channels that we have described is an inevitable consequence of the quantum theory, whether in our interpretation or in the usual one. As long as we restrict ourselves to The abstraction of a one-body system, this implication neither can nor should be avoided. It is our thesis that only when we take into account the interaction of this system with a background containing many particles that the transition becomes, in effect, irrevocable. The reason for this is that the information in the unoccupied channel will lose all its potentiality for becoming active, so that it will remain permanently inactive after interaction with a sufficiently complex background D. The simplest case in which this happens arises when the particle in question collides with another one and scattering takes place through a short-range interaction. To discuss this process, let us consider a three-dimensional system, but assume a barrier of finite width that is uniform in the x and y directions, with a plane wave ijj equals exp, x0z, incident in the z direction. The calculation of transmission coefficient will go through as in the one-dimensional case. But let us assume now that an atom with coordinates y is PLA set in the transmitted beam. To simplify the problem, we suppose that its wave packet has average velocity 0. This packet is given by 4O, y, equals LF, k, exp ik, y. 5. Let us further assume that the incident particle is represented by a wave packet bounded in all three directions but traveling only in the z direction. Then The transmitted wave can be represented by the packet T/O, z, equals Lg, k, exp, ik, z, 5-6. Where k represents a vector in the direction of z and the packet is centered at k equals k. Before the particles interact, the combined wave function will be O equals O, z. The particles will begin to scatter each other when their wave packets over La p. We postulate conservation of momentum and energy in this process. Because of the linearity of Schrödinger's equation, we can deal separately with each of the terms that make up the wave packet. Thus a term that was initially exp, ik z exp, ik y will, because of conservation of momentum, go over into exp, I, k plus k. Z exp I, k, y. The equation for conservation of energy then takes the form K2, k plus k, 2, k, 2, plus, equals plus 2m. 5-7. And this introduces a relationship between k and the initial momenta. B. Cause the wave packets in k and k are fairly narrow, the above condition can be approximated by satisfying it for the values of k and k corresponding to maximum intensity, which are respectively k equals 0 and k equals k. Thus, to a good approximation, k can be obtained from The equation. K equals K2 plus K plus K, 2. 2m. 5.8. Therefore K is related only to K and not to The precise values of K and K. This will simplify the subsequent discussion in an important way. We now return to the calculation of the wave function after interaction. This will be, as a function of time, where a, k, t, b, k, t, z, y, t, equals lh, k, a, k, t, b, k, t, k. 5-9. Lg, k, exp k plus k, z exp I, k plus k, 2t, k, 2m, lf, k, exp k, y exp, equals, underscore, k, 2t, k21n. Transition processes considered as independent of observation 81. Nh, k, represents the amplitude that finally results from the process of interaction, which will depend on the potential V, Z, 11, of interaction between two particles. The sum over K must, of course, be restricted by the condition of conservation of energy. To show what the above means, let us consider the factor B, K, T, which we rewrite as this corresponds to a wave packet moving with a velocity k/m. The term xp, ik, 2, t/2m, which we have neglected, describes the spread of the wave packet, which may be taken to be small during the period of interest. A similar treatment could be given for a, k, t. This will also correspond to a wave packet, but moving with velocity k/m. What this all implies is that after interaction, the two particles are separating with a relative speed proportional to I. If the interaction is such that I is considerably greater than the initial spread of momenta in the wave pa its dk and dk, then after a suitable time, the distances moved by the PA radicals. dz equals kt/m and dy equals kt/m, 510, will be greater than the widths fjz and fj of the wave packet ts. When this happens, the final wave function of the combined system, z, y, t, will cease to overlap with the initial wave function o, z, y, t. Moreover, for different values of k, the particles will go in different directions so that the contributions of these different values of k to the total wave function will also cease to overlap. This means that the original transmit channel will now break into many parts. First, there will be an unmodified transmitted channel in the regions far from the wave packet po, y, and a weaker one close to this wave packet. Secondly, there will be modified channels in which both the scattering particle y and the transmitted particle z will be going in various directions. Since all THSA channels do not overlap, the quantum potential and d guidance condition for the combined system will be determined only by the channel I into which the particle actually enters. All the other channels will THN correspond to inactive information. 82 The undivided universe. Because there is such a process of the multiplication of non-overlapping channels corresponding to transmission of the particle, the possibility of bringing about overlap of transmitted and reflected channels in the way described earlier H has effectively been eliminated. For in order to have such overlap, it is necessary that this overlap takes place in the configuration space of all systems which have INTER acted. Therefore, if we merely have an arrangement that brings reflected and transmitted waves into the same region of space, there will still be no effect on the quantum potential. To have such an effect, we would also have to bring together all the scattered channels. If this is not done, the information in the reflected channel remains inactive, even though it corresponds to a much more intense quantum field than does the transmitted channel. Of course, one could consider trying to bring back into the same region of space all the channels that resulted from the various scattering processes. Evidently, this would be immensely difficult, almost certainly beyond our present technical capacity. Nevertheless, it is still a logical possibility. But we can see that this possibility is not relevant here because all the particles concerned will keep on encountering further systems with which they interact, and these will bring about a further multiplication of channels. Ultimately, this process will lead to chaotic motions which are characteristic of thermodynamic equilibrium. As long as we accept the current explanations of the irreversibility of thermodynamic processes in terms of the notion of an approach to statistical equilibrium, for example through scattering, then we must also accept that the interactions that we have described here will similarly be irreversible. Therefore, the channels to which we have alluded earlier will be irrevocably distinct. The quantum potential and the guidance condition will be determined only by the channel actually occupied by the system. The remaining channels will then correspond to what we have been calling inactive information, i.e. information not only actually inactive, but also having no potential for becoming active. All this implies that the channels corresponding to actually or potentially active information are constantly narrowing down as the system in question interacts with its surroundings. But it is implied by Schrödinger's equation that the wave function of a system is constantly spreading, e.g. as shown in detail in Chapter 3 for Gaussian wave packet. These two processes evidently oppose each other as we have already indicated earlier, and the net result comes out of the balance between the tendency to spread and the tendency to narrow down to a more definite form. The narrowing down process produces a net effect that is essentially the same as that produced by the C-elapse of the wave function in the usual interpretation. Yet there is no collapse here. At no stage do we need to violate our basic postulates in order to obtain the self-definition of THE. Transition processes considered as independent of absurd 183 system. We shall discuss the full implications of this in more detail later, but for the present we shall emphasize only that this means that measurement does not have to play a fundamental role in our interpretation. Rather, the universe is constantly defining itself and measurement is only a special case of this. We now go on to discuss the process of transition of an electron in an atom. If such an atom is to jump from one stationary state to another, it is necessary that there be an additional system available that can take up the energy given off. This is usually the electromagnetic field within which, for example, a photon can be created. However, to avoid the complexities arising in our interpretation of the electromagnetic field, which we discuss in Chapter 1.1, we shall suppose that the energy is taken up in an auger-like effect by an additional particle that was originally also in a bound state in the atom in question. To make possible a comparatively short mathematical treatment, we shall use here a simplified model of this process in which both particles are initially in bound states within a localized potential well. We shall suppose that they are in S states and that all the transitions can be restricted to S states, i.e. there is negligible probability of going to states of higher angular momentum. To further simplify the model, we will suppose that initially the two particles do not interact and that at t equals 0 a small perturbing potential V, Z, 11, is suddenly tur net on, W here Z is the coordinate of the electron and 11 that of the particle which carries off the energy. We shall then apply the standard perturbation theory to calculate the changes of the wave function with THE. The initial conditions will be determined by the requirement that the Z particle is in a stationary state with energy ET and with wave function 1/io, Z, expiet where we continue our notation in which h equals 1. The 11 particle will be in a stationary state with energy EFJ. And with wave function 4io, 11, expifjt. The net initial wave function will then be equals 1/io, Z, 4io, y, expieo, 511. Where E0 equals E plus Fj. After t equals O, the Schrödinger equation for the combined system will be A Z equals at 512. Since we can restrict ourselves to A states, it will be convenient to introduce the function x equals RA/RB, Li, where RA and RB are the radius vectors of the respective particles. In terms of x, Schrödinger's equation becomes 8x 182102 I equals plus V, RA, RB, x, and T2 Ma 8 R2 MB 8 R 513, with the boundary condition that x equals 0 at RA equals 0 and RB equals 0. The initial wave function is, of course, where XO equals RAVO, RA, and .AO equals RBFEO, RB. For T0 we then write x equals XO plus AX. AX will contain the wave function components in which the Z particle H has made a transition TOX. J. EXPIE1TJ, while the Y particle has become free with absolute value of the momentum P. Since both particles were initially in A states and since the Z particle is finally in an S state, it follows that the final angular momentum of the Y particle is 0, so that it too is in an S state. Recalling that x equals 0 at rb equals 0, the wave function of the latter will th and bp are proportional to ip2 sin prb exp t 2mb. The typical contribution to the net wave function after transition will therefore be proportional to x1 ra sin prb exp I e1 plus 2b t. We then obtain perturbation theory then yields underscore v10 po I p 2 cp ae plus p2/2 mb exp minus 1 times 10 to the power of first plus 2 mb t. 514 515. Transition process considered as independent of OB1 EM Jashan. 85. Where dE E1, EO, which is the net increase of binding energy resulting from trans 1 T10N, and where the corresponding matrix element is V10 PO equals 1, 1. TF J, Z, sin, PRB, V, Z, Y, LF, O, Z, cent 0, Y, DZ dy. 516. We will be interested in finding the form of dx for moderately long periods of time, i.e. 4 times long enough so that the factor 1, expi, de plus, p 2/2 m8, t, de plus, p2/2 mb becomes a sharply peaked function with a maximum at that value of p, for which the denominator vanishes. This function evidently has a width inversely proportional to the time t. Let us denote the value for which this function is a maximum by p equals po. In evaluating dx we can then replace p by p0 in all the terms in dx that multiply this factor. Also, in evaluating th's factor we may write p equals p0 plus dp and neglect terms of the order of dp 2. Because we are considering t great enough so that the factor is large only for very small l values of dp. We then obtain de plus p 2/2 m8 p0 dp/mb equals v0 dp, where v0 is the speed of the outgoing particle. With these approximations we find that 1 exp evo dpt dx equals x1 ra v10 po vdp sm prb p 0. 517. For an undivided system, this sum becomes an integral, which can be evaluated by means of contour integration. The wave intensity will be proportional to J 1 exp evo dpt expi p0 plus dp rb expi po plus dp rb vd ddp 0p. The integral is finite everywhere including dp equals 0, even though the separ a te terms are singular there. We may therefore evaluate it by choosing, in the well-known way, a contour in the complex plane that goes around dp equals 0. In an infinitesimal semicircle which is chosen so that only outgoing waves will appear for t0. A typical term in the integral is proportional to Ju expi dprb ddp oovo dp. If we choose the contour in the upper half of the complex plane as shown in figure 5.4, it can be seen that the integral vanishes. Figure 5. 4. Contour to evaluate integral. On the other hand, if we take a term like J exp-2 iprb dii AP underscore 00 VOU dot P. Then by completing the contour in the lower HALF of the complex plane, we see THAT it does not vanish, but is equal to THE residue at the singularity. By applying this method, we can see THAT all the terms containing the factor EXPI, P0 plus IIP, RB will vanish SH. The remaining two terms will be proportional to, where S is the step function which goes to 0 for negative VE values of its argument and D is unity for positive values. This will imply a step-shaped wave that is spreading out at the speed V0. TH E. Total wave function, for large T, is then x equals RBEXPEOXO, RA, dot AO, RB, plus VI0, 0. X1, RA, EXPIPO RB, G, RB, T. 518. In the above equation, THE term XO, RA, dot AO, RB, represents THE initial wave function of the combined system, while the term transition process is considered as independent of observation 87, represents the contribution of the perturbation to this wave function. We shall show presently that if THERB particle enters the region COR, responding to the perturbed wave function, the effect of the initial wave function on THE particles becomes negligible, so that the system can be said to have undergone a transition to the final state. The total probability of this transition can be found by integrating the square of the second term divided by R1 over dRB. It is clear that this will be proportional to T, as it is in the conventional interpretations. However, as also holds in THE conventional interpretations, this result will follow only for times much larger than 1/FLE. For as we rec ALL, this approximation, which arises from simplifying our various contour integrals, will not hold for times shorter than this. Indeed, it is evident that at the very shortest times, the contribution of the perturbed wave function must be proportional to T itself, so that the probability of transition is proportional to T2. To see the meaning of THE above equation in more detail, it is instructive to take the ratio of the perturbed contribution to the wave function to the unperturbed contribution. This is R V10P00X1, RA, EXPI per BG, RB, T. VXO, RA, dot XO, RB. 519. Because the matrix element V10P00 is, by hypothesis, SMALL, this ratio will also generally be SMALL. Where this is the KI, the initial wave function will overwhelm the perturbation, which latter will then at most introduce a very small change in THE overall wave function. In such a situation, the state of the particle would undergo negligible change. However, where the denominator in the above ratio is small, the situation can be quite different. Since .x0, R8, represents a bound state, the ratio will indeed become as small as we please for values of RB appreciably greater than the mean spread of this wave function. For THSA values of RB, the initial wave function will be negligible compared with the perturbed wave function. This latter will now dominate, and the motion of the particle will no longer be affected significantly by the initial wave function n. The motion implied by this wave function will carry the particle further and further from the atom at the speed v0. The effective wave function of the system will then be proportional to xj, Ra, expi per bg, Rb, T. This means that the outgoing particle is free, and that the bound electron now has a wave function xj, Ra, in other words, a transition has taken place from a state in which the electron was bound with the wave function xo, Ra, and the y particle with .xo, Rb, to one in which the electron is bound with the wave function xj, Ra, while the 11 particle effectively has the free particle wave function expip, Rb. It is evident then that this kind of transition can take place when the 11 particle is initially located at values of Rb large enough so that .xa, Rb, is 88 the time-divided universe. Negligible. Clearly such locations are highly improbable, and this explains why only a few members of the ensemble will undergo transition. To see what happens to particles starting at small values of R8, let us compute the velocity from the guidance condition, wh, as we have seen in Chapter 3, implies the quantum potential. We find 1 x j slash v equals x 2 im b arb 520. For values of RBSMLL enough so that the perturbed wave function has a much lower intensity than the unperturbed one, this will be approximately proportional to Po/MB RB, AO, RB. It is clear that such particles start to move outward at a very low velocity, especially those initially at small radii. They will speed up as they go outward and will eventually enter the region in which the perturbed wave function is dominant. The effective physical state will then be one in which a transition has taken place along the lines THATWHAVE described. Ultimately all the particles in the ensemble will be able to undergo transitions in this way. However, in such an ensemble, the times of transition will be statistically distributed, and it is easy to show that this distribution is exactly what is predicted by the usual interpretation of the quantum theory. The above holds only in the approximation in which the perturbation theory is valid. In a more exact treatment, e.g. the Wigner-Weisskopf method for the initial wave function is found to decay exponentially with some mean lifetime r. It is clear that, depending on the initial conditions, some particles will be emitted in times much shorter than r. This means that the wave function does not give a complete description of the reality of the transition, because it has no terms in it to discuss the actual and often short time in which a particle approaching the edge of the atom is suddenly swept out to become free in an interval of time that has no essential relationship to t. Clearly the additional concept of a particle is needed, alongside that of the wave function, to allow this process to be considered ontologically, i.e. as essentially independent of being measured or observed. A similar situation arises with radioactive decay brought about by barrier penetration. For example, the mean life of the uranium atom is 2x109 years, but once a particle enters the barrier, it may go through in a time of the order of 10 to 22 secs. This speed of the actual process is also some thing that cannot be described solely in terms of the wave function and its associated concept of mean lifetime. Finally, it should be noted that, as in the example of barrier penetration discussed in section 5.1, there is still, in principle, the possibility of interference between the initial wave function and that representing particles. Transition processes consider D as independent of observation 89 that have undergone transition. This is, of course, as valid in the usual interpretation as it is in our interpretation. If the outgoing particle u undergoes collisions, however, then it becomes steadily more difficult to obta in interference because more and more particles would have to be made to participate in just the right way. As in the case of barrier penetration, this would ultimately become impossible in practice. Simultaneously, the domain of active information would narrow down so that the outgoing particle would be affected only by a relatively narrow wave packet, while the information in the remaining parts of the wave function would become inactive. 5. 4. On the possibility of bifurcation points in more complex cases. In the simple example of the auger-like transition discussed in the previous session, there are no bifurcation points such as were found in the example discussed in section 5. 1. However, if we introduce a number of final states, bifurcation points can be obtained. To illustrate this, let us consider two possible final wave functions of the electron xi, Ra, and x2, Ra. These will be assumed to have different energies so that the energies transferred to the y particle will be correspondingly different. We will assume that for the wave function x1, Ra, the y particle will have momentum p1 and velocity v1, and for x2, Ra, these will be respectively p2 and v2. The perturbed wave function will then be xRa-Rb-exp, i.e. O tv1io, p, ox1, Ra, exp ip1 rbg1, rb, t, v1, where, and, plus vj, opox2, Ra, exp ip2 rbc2, rb, t, v2, 521, g2, rb, t, equals s, rb, s, rb, v2t. If the particle is in a region beyond that in which the initial wave function is appreciable thn, as we have seen earlier, its motion can be treated solely in terms of the perturbed wave function. This later describes what are effectively two wave packets in Rb space which are multiplied respectively by xi, Ra, and x2, Ra, as shown in figure 5. 5. The first packet will have R8, V2T. I lily FII thuria enalil dash plus dash. Figur 5. 5. Overlap of wave packets. Reached Rb equals V1T, while the second will have reached Rb equals V2T. Assuming V1 V2, it follows that the second packet will be contained in the phi rst. Which later h as an advancing region of width tlrb equals v1, v2, t, that does not overlap the first pack et. If the particle is in this region, then the second wave pa conta ining x2, rb, as a factor, will not affect its motio n. Therefore it can be treated as if the wave fu n setion had collapsed to x1, Ra, exp, ip1 rb. However, if it is in the region of the second packet, there will still be interference between the two terms and we will not yet have a collapse to one term or the other. How is it possible to obtain a defy nite result? To answer THIS, we first note that this state of affairs is a consequence of our approximate ion in terms of perturbation theory in which the decay of the original wave fu n setion is not taken into account. Therefore an indefinite stream of outgoing waves is implied. However, when this decay is taken into account, e.g. by the Wigena vice Kopf approximate ion, it is found that the wave packets will have durations of the order of the mean Li Fe time, t, of the original wave fu nct ion. It is clear that when T is great enough, the separation ion of the PA-CKETS, V1, V2, T, will be greater than their respective widths V1T and V2R, and therefore, the packets will separate. Where they HAVE separate D, the particle WILL. VEIN10F these packets, INWHICHC as EITS motion can be treated WITH. Out ref ER ins to the other, as we HAVE done in the examples already given. Here. The effective wave function will then be either x1, RA, EXP, IP1RB or x2, RA, XP, IP2RB. In other words, we have shown that there are two mutually exclusive channels into one of which the P article must enter. A and D. As a simple calculation shows, THE probabilities OF either CH_ANL WILL come out the same as those given by the usual I interpretation. Transition processes considered as INDUP E and D and of obsangation 9.1. Although the consideration of the finite lifetime shows that the outgoing wave function will ultimately give rise to two separate channels, when T considerably exceeds the mean LI-FETM, it is necessary to point out here that this can happen in much shorter times if the outgoing particle can undergo collisions with other atoms. As an example, suppose that the energy of the outgoing particle, E1, corresponding to velocity v1, is great enough to ionize an atom, while that of a particle of energy E2 and correspond ding to velocity v2 is not. After the collision, the PRT of the wave function COR responding to x1, RA, will then be multiplied by a factor g, z, describing the free state of the P article with coordinate z liberated from the atom in which it was originally held, while x2, RA, is multiplied by g0, z, corresponding to the original bound stat.E of this particle. Clearly, in a relatively short time these wave functions cease to overlap, and subsequent collisions with them bring about a multiplication of channels in the way described in section 5. 2. In principle the CAN happen in times of the order of that required for collisions, perhaps something like 10 to 12 SECS. Therefore even if the period of decay is long, we will still generally obtain a separation of chan ELS. However, if no collisions take place, the CHA-NNLs will not separate and we will have interference between the two components of the wave function x1, RA, EXP IP1RB and x2, RA, XP IP2RB. This interference is indeed an example of the EPR correlation, which we shall discuss in detail in CHA-PTER 7. It is an unavoidable prediction of the quantum theory, both in the usual interpretation and in ours. Whether the channels are formed by separation of wave packets over times of the order of t or by collision s, it seems evident that there must be some limiting points or curves which divide the initial conditions of the particles that will enter one channel from those that will enter the other, as happened in the case of barrier penetration. Narrowly speaking, however, these will be in the overall configurative space and may be quite complex in form. The possible complexity will increase rapidly as we consider more and more stationary states, especially if we go to wave functions of higher angular moment In the latter case the stationary states will be characterized, as we have seen in chapter 3, by a set of circular motion S, in contrast to the S state which is characterized by a set of points at which the P article is at rest. The general behavior described above is similar to that obtained in the study of nonlinear equations whose sole ion contain what are called stable limit cycles 3. As we have pointed out earlier, the equations for the particle Motion in our interpretation are likewise clearly nonlinear. It is implied by the discussion above that the solutions also have something like stable limit cycles, except that a certain generalization of this concept is needed here. Thus, as we have already indicated, for p states, T stable limit cycles 92 the undivided universe would be a set of circles. The difference from the usual kind of nonlinear equation is that for each stable motion we have a whole set of possible limit cycles rather than just a single cycle. Each quantum state thus corresponds to a different set of limit cycles, and a transition corresponds to an orbit going from one of these to another. In this discussion, the S states should be regarded as degenerate cases of limit cycles which reduce to single points in Ra space and simultaneously to outgoing orbits in Rb space. Finally, it must be emphasized that our equations for the particle motions differ from the nonlinear equations that have commonly been conceived thus far, in that the forces, as determined by the quantum potential, are not pre-signed functions either of external variables or of the particle coordinates. Rather, as was brought out in Chapter 4, they depend on a quantum field of active information ordered in the configuration space, which involves the whole system in a way that cannot be analyzed solely in terms of relationships between the particles. It is this feature which makes it possible for such dramatically different limit cycles to emerge as a result of the evolution of the wave function even for simple systems. The fact that the activity of the quantum field does not necessarily fall off with the intensity of the wave is also crucial for this behavior, since without it we could not have had some transitions taking place almost immediately even when the perturbed wave function was very weak. It is clear then that the new features of the quantum potential described above are principally what are behind the ability of our extension of Newton's equations of motion to comprehend the new quantum properties of matter. This brings out in further detail the point that we made in Chapter 3, Section 3. 1. i.e. that classical physics does not follow from the form of Newton's equations alone, but also requires certain restrictions on the forces that appear in these equations. When, as is the case of the quantum potential, we go beyond such restrictions, an entirely new kind of physical law is implied. 5. The quantum process capture of particles. Fusion fission. We now go on to extend the results of the previous section to the case of capture of an electron by an atom. This, combined with the discussion of ionization that we have just given, will enable us to bring out how quantum mechanics implies the possibility of the formation of objective wholes as well as their dissolution into relatively independent parts and subwholes. As we saw in Chapter 4, this is one of the principal new properties of matter implied by quantum theory. Transition processes considered as independent of observation 93. We shall discuss this process as a kind of inverse of the one that was treated in the previous section. We consider an atom on which is incident a particle with a plane wave function exp, ikz, implying motion in the z direction only. In order to enable the atom to see order this part ICLEAD as to form a new combined system, it is necessary that there be something to carry away the energy that is given off. As happened in the case of ionization, this will be done by an additional particle with coordinate y. Let us suppose there are further particles in the atom with coordinates designated by I. The initial state of the atom will then be represented by FEO, TL, EXP IEOT. The combined initial wave function for the entire System is therefore wo equals z, y, t, equals 4 feet 0 inches, 11, I, exp ikz exp I, ea, t. 5.22. Because of the interaction between these particles, this combined wave function will change. We shall assume that the main possibility for change is the introduction of a ground state, in which the z particle has been ca-uttered. While the y particle h has been released. This wave function will thus be sent I1, z, I, exp ie1 tj. The y particle will then have a wave function whose typical component is xp ip y, ip2/2m, t. The net change of the overall wave function ca and then be written as 0.1.1/j equals lcp, t, exp I, p. 11. p1, z, I, xp ie1 t. p. 5.23. We assume that this process can be treated by perturbation theory in a way similar to what was done with ionization in the previous section. Of course, the details will be considerably more complex because the outgoing wave cannot in this case be restricted to a spherically symmetric form. We shall however give only the general results here. The essential point is that after some time e, the outgoing wave takes the form 524, where 88 is the azimuthal angle of the outgoing particle relative to the direction of the incident particle. If the initial co-ndit ions are such that the particle enters this outgoing wave, then there is no overlap with the incident wave function. The quantum potential acting on the particle will then be the same as if the incident wave function were not present and 0.1.lfj were the whole wave function. It is clear that in this case the incident particle will have been captured into a state with wave function pj, z, t. 94 the undivided universe, corresponding to a stable limit cycle of the kind discussed in the previous section. At the same time the y particle will be moving outward carrying away the excess energy. The probability of capture can be calculated by averaging with the probability density p equals 1.12, and this will give the same result as is obtained in the usual interpretation. Initially the combined system has a product wave foo and Cetian implying, as we have seen in chapter 4, that the two subsystems represented by z and y, respectively behave independently. If the initial conditions were such that the y particle did not enter the outgoing wave, the effective wave function would have ended up as essentially unchanged so that the subsystems would remain independent after collision. However, if the y particle did enter the outgoing wave, then we will have formed a new hole with wave function sent 1, z, exp ie1 t along with the y particle, which is now a new independent part. So what happened is we began with one hole which included the particle and the y particle, and along with it was an independent particle represented by z. This hole broke up, but at the same time a new hole was formed with different constituents. This process could be described picturesquely by saying that the origin Al hole had undergone fission, while the product atom had undergone fusion with the z and particles. Through the fission-fusion process we have been able to describe objective changes in the holes that are present 5. To come back to our description in terms of active information, we could also say that the original atom was characterized by a certain common pool of such information which broke up and reformed into a new pool that included the z particle instead of the y particle. We emphasize once again that this process of forming and dissolving holes is essentially quantum. Mechanica L. For it is only through the existence of such pools of information which are not expressible solely in terms of relationships of the actual particles that the notion of an objective whole can be given meaning. In contrast, as we have said earlier in classical physics, there is no such objective significance to the whole. The latter can at best be regarded as a convenient way of thinking about what is considered to be in reality a set of parts. Quantum mechanics thus implies a new kind of process, i.e., the collection and dissolution of wholes. The language of ordinary quantum mechanics already tends to suggest this, insofar as it treats the quantum state as an unanalyzable whole. However, as we have already suggested in earlier chapters, in our interpretation this wholeness becomes more intuitively intelligible because this interpretation highlights the new features of the quantum theory that bring it about. Transition process considered as independent of observation 95. 5.6 Summary and Conclusions. The essential point of this chapter was to demonstrate with the aid of a number of typical examples that the transition process can be treated ontologically, i.e., as having no essential relationship to measurement or observation. We showed that in such a transition the wave function effectively splits so as to define a number of separate channels. The quantum potential was determined only by the channel Th at the particle actually enters. The channel entered by the particle depends on the initial conditions which are distributed statistically in an ensemble with P equals Lt plus W. From this it follows that the probability of obtaining a certain result is the same as in the usual interpretation. In effect, everything happens as if the wave function collapses to the final result, while no collapse actually takes place. The channels not occupied by the particles correspond to inactive ion formation. We showed that if the particles make Cali s ions with additional systems, there is a constant narrowing down of the domain in which the wave function can significantly affect the quantum potential at the location of the particles. From this it follows that the channel entered by the particles eventually becomes irreversibly fixed, so that it cannot be undone. An analysis of the behavior of the particle orbits shows that there are bifurcation points dividing those orbits entering one channel from those entering another. Near these points, the motion is highly unstable and indeed, chaotic in the sense of modern chaos theory. Stationary states then correspond to an extension of the concept of stable limit cycles which is found in the theory of nonlinear differential equations. Finally, we discuss the process of formation and dissolution of wholes. Fission fusion. This brings out the possibility of an objective ontological wholeness and of a distinction between states of such wholeness and states in which THEPARTS or subwholes behave independently. We understand this through the formation of common pools of information. This information brings about non-local interaction, but quantum wholeness implies EVN. More than this. For it arises OUTOFTHE quantum phi ELD which cannot be understood solely in terms of pre-signed properties and interrelationships of the particles alone. Rather, the whole is presupposed in the quantum wave function, and it is the active information in this wave function that forms and dissolves wholes. Chapter 6. Measurement as a special case of quantum process. As point out in CHA-PTER2, in the conventional interpretation of the quantum theory, which is basically epistemological in nature, measurement plays a key role in the sense that without it the mathematical equations would have no physical meaning. In our ontological interpretation, however, we have started with a treatment of the individual, actual process, e.g. a particle penetrating a barrier, undergoing transition between stationary states etc. Evidently it is necessary to deal with the measurement process in essentially the same way, i.e. as a special case of quantum processes in general. What is particularly significant in a measurement process is that, from a large scale result that is observable in a piece of measuring apparatus, one can infer the state of the observed system, or at least the state in which it has been left after the measurement process is over. In this chapter we shall treat the measurement process in some detail, and show how it is to be understood ontologically. We shall first discuss the general principles of this process. We shall show that the essential new feature of quantum measurement is THATTHR is mutual and irreducible participation of the measuring instrument and the observed object in each other. As a result, any attempt to discuss this process as measuring a property of the observed object alone will not be consistent with our interpretation. Rather we say that the result of a measurement is a potentiality of the combined system and can be determined only in terms of the properties of the particles, along with the wave function of the combined system as a whole. On the basis of this notion, we shall go into several examples that help illustrate the principles involved and clarify some of the puzzles to which these examples give rise in the conventional treatment. In treating measurements ontologically we shall, for the sake of convenience, divide the overall process into two stages. In the first stage the measuring apparatus and the observed system interact in such a way that the wave function of the combined system breaks into a sum of non-overlapping packets, each corresponding to a possible distinct result of the measurement. In the second stage this distinction is magnified by some detecting device, so that it is directly observable at the large-scale level. In the first of THSA stages, the wave function Ca and Bt are treated in the same way as was done in the discussion of von Neumann's approach given in Chapter 2, Section 2. 4. As was done THR, we let the initial wave function be represented by 6(1) n, where /jn, z, are the possible eigenfunctions of the operator 0 that is being measured. We also let the initial wave function of the measuring apparatus be represented by cent0, y, which corresponds to a suitable wave packet, describing, for example, the position of a pointer. The initial wave function of the combined system is then w, z, y, equals po, y, lcnipn, z. 6.2 n. As a result of the interactions, this wave function is modified and it becomes 6.3 n, where the on are the eigenvalues of the operator 0. After the time LLT, when the interaction is over, we obtain 6.4 n. If the interaction is strong enough to satisfy equation 2.5, then the po, y, dot x on L / t, will represent distinct and non-overlapping packets that correspond to the various possible results of the measurement. It is clear from 6.3 that during the period of interaction, the various components of the wave function will overlap and interfere. The amplitude of the wave function will then become a very complex and rapidly fluctuating function of z and y and, of course, the time as well. The quantum potential will evidently be correspondingly complicated so that the MO of The particle becomes difficult to predict in much the same way as happened in the case of transitions between stationary states discussed in Chapter 5. However, when the wave packets have definitely separated, the apparatus particle 11 must have entered one of them, say M, in which it remains indefinitely, since the probability of being between packets is 0. From then on, the action of The quantum potential, and d, of course, the guidance condition, on The particles will be determined only by the packet TPM, Z, for M, 11, because all the other packets, WH do not overlap this one. Will not contribute to it. So at least as far as the particles are concerned, we may ignore all the other packets and regard them as constituting inactive or physically ineffective information in the sense discussed in Chapter 5. Here it must be emphasized THAT, as was shown for the transition processes. For example, this will still happen even when there is some spatial overlap between T/im, Z, and the remaining packets T/in, Z. This is because of the multidimensional nature of the wave function of The combined system, which implies that the produce T, TPM, Z, cent Rn, 11, and any other product, say T/I, 2, cent, 11, will fail to overlap as long as ONE of its factors fails to overlap. Even though the other factor will still have some overlap. It is clear that measurement H has in effect been treated as a particular case of quant-UM transition even though one of the systems concerned, i.e. the apparatus, is considered to be macroscopy C. Indeed the combined SYS TEM makes a transition from an initial state cent 0, 11, LNCNV.in, Z, to one of a set of final states, cent M, 11, 1 Gim, Z. A simple calculation will show that the probability of this transition is just CNL2, as it would be also in the conventional interpretations. We may indeed use the language of Chapter 5. And say that each of the possibilities Gfim, 11, V.im, Z, constitutes a kind of channel. During The period of interaction the quantum potential develops a structure of bifurcation points, such that apparatus particles initially on trajectories leading to one side of these points enter, for example, the M1H channel, while the others do not. Eventually each particle enters one of the channels to the exclusion of all the others and thereafter stays in this channel. When this has happened the observed particle will behave from then on as if its wave function were just TPM, Z, even if V.im, Z, and the rest of the cent N, Z, should still overlap. The fact that the apparatus particle must enter one of the possible channels and stay THR is thus what is behind the possibility of a set of clearly distinct results of a quantum measurement. Nevertheless, as was brought out in Chapter 5, the inactive packets not containing the particles need not at this stage remain permanently inactive. Rather it is still possible, in principle, to bring the apparatus packet, say, cent Im, 11, and Gfin, 11, together so they will interfere. In this case the quantum potential may now be affected by the previously inactive packets and so the production of distinct and separate results of the measurement process is not yet irrevocable. As shown in Chapter 5, the irrevocability of such a process is established only when the apparatus particle interacts with a macroscopic system of particles. In the case of a measurement, this will be the detecting device, which amplifies the results to a scale large enough to be directly observed. Such a detecting device will of course contain a very large number n of particles with coordinates zi. When this interacts with the apparatus particle, 11, its wave function a, z1, zn, will cha nge. To each distinct state, n, of the apparatus variable, there will be a corresponding state. xn, 11, z1, zn, of the combined system of the apparatus and the detector. This wave function will then be e, n. We have assumed that the effect of this interaction on the observed particle is negligible. In general, however, some correlation of the 11 and the set zi is to be expected. But within the context under discussion, this will have no appreciable effect on the meaning of the experimental results. For most purposes, we can therefore simplify the treatment by writing wherein z1, zn, represents the wave function of the detector corresponding to cent. 11, for the apparatus variable. In the above, we have allowed scope for the apparatus packet cent n, 11, to change to some other form cent. 11, as a result of interaction with the detector. In general, conditions can evidently be arranged so that this change will not produce any overlap between the cent. 11, corresponding to different values of n. Even if it were possible, either naturally or by some special experimental arrangement for these to come to overlap, any given a will not overlap with the other n in the configuration space of the detecting device. Therefore, such overlap of the cent will not alter the quantum potential acting on the z and 11 particles. This is because the particles of the detecting device will now be in distinct channels in the overall configuration space of the detector. Moreover, since these channels will be so complex and multiple in nature, it will not be possible to arrange them to overlap in the future, while the probability for this to happen spontaneously will be negligible. The channels corresponding to distinct possible results of a measurement are in this way established essentially irrevocably. The above treatment discusses measurement in terms of von Neumann's analysis, in which one introduces an interaction between measuring apparatus and observed system that correlates the value of the observed result directly to the position of a suitable apparatus variable e. However, their measurement as a special case of quantum PROCEAA 101 is a wide class OF measurement in which the observed result IA, in the first instant, correlated to the momentum of such an apparatus variable. With the passage of time, the resulting motion of the apparatus variable then leads to a separation of the apparatus packets corresponding to different values of the phi NAL state of the observed system. A typical example of this sort of measurement is the Stern-Gerlach experiment. Suppose we have a beam of atoms with coordinate y, each containing an electron with coordinate z. Let the orbital angular momentum of the atoms be h. Relative to any convenient z-axis, there are three possible quantum fields t/j, z, where j equals 0, 1, 1 correspond ing to the different values of the z component of the angular momentum. The first stage of the measurement is achieved by letting the atoms pass through an inhomogeneous magnetic field in the z direction. Before the atoms reach this field, The wave function of the combined system is 6.5, where 0 colones, y, represents the initial packet corresponding to the location of the atom. While the atoms are passing through the magnetic field, the interaction Hamiltonian is going to be approximately AB H1 equals OZOL 6.6, where 8B/8Z 0 ISTHE value OFTHE gradient OFTHE magnetic field AT. The center of the beam and L is the Z component of the angular momentum operator. Recalling that the interaction is impulsive, so that all changes of the wave function du to the rest of the Hamiltonian can be neglected. Du ring the interact T ion, we obtain for the wave function immediately after passing through the inhomogeneous magnetic field. Il11 equals Lc, T/J, Z, cento, Y, E, Ij, 8b/8z, at T1j, J. 6.7, where tit is the time spent in this field. Thus the apparatus POC KET obtains a momentum proportio NAL to the angular momentum of the atom. 2. Make a measurement possible, the momentum transferred to the atom. 8b/8z, 0 tit must evidently be much greater than the width THBP of the packet. After this interaction takes place, the packets will begin to separate. With the approximations made here, the spread of the packet can be E10 to the undivided universe. Neglected. We then up to In, after a suitable time t. 6.8. Where P0 equals 8b/8z, 0t. Clearly the three packets will event UALLY SEPA RATE. After which they may be detected, for example, at a screen. From here on the treatment goes through in essentially the same way as with the von Neumann type of measurement interaction. Thus, while the packets are separating but still overlapping, there will be a complicated and rapidly varying quantum potential containing bifurcation points of more or less the same kind that has been discussed in earlier examples. According to the initial position of the Z and G particles, the system will enter one of these packets and, as explained earlier, this will determine a channel in which it remains from then on. The other two channels will then have no effect on the quantum potential, or on the guidance conditions, acting on the particle. They can therefore be ignored. However, as we have already pointed out in several contexts, it is still possible for the atomic quantum fields for I, Ti, to be made to overlap, for example, with the aid of suitable magnetic fields. The corresponding channels are thus not yet irrevocably determined. The next stage is to allow the atoms to enter a detecting device. For example, this may be done by having each beam enter an ion chamber. As the atom goes through the chamber, it will ionise molecules of the gas that are present there. Let the relevant coordinates of these molecules be denoted by Z, Zn, where Z represents the S molecule in the N1H chamber. If an electron is liberated, it will be accelerated by the applied field of the ion chamber as shown in figure 6. 1. This will initiate a cascade giving rise ultimately to a pulse containing so many electrons that it can be observed by ordinary means, e.g. a perceptible deflection of a galvanometer. To discuss the behavior of the wave foo and il of the total system, let x O equals itn a z zj represent the state in which all the counters are unfired, and let xj equals .j z zn represent the state in which the n1h counter has fired and the others have not. The total wave foo enchen just before the particle enters a counter is wh air xo z1 zn lcjl j z fh y j. Measurement as a special case of quantum process 103 plus figure 6. 1. Discharging ion chamber. After one of the counters H as function THIS becomes, it is clear that in order to obtain interference of the various states of the Z particle, it will be necessary that the quantum fields of the total system of Z particles in the fired state overlap those in the unfired state, even while The cascade is developing, it is evident that there will be no such overlap. And after all the cascade particles HAVE reached the electrodes and flowed along the wire to a very different place, the possibility of establishing an overlap becomes even less likely than during the cascade. Along the lines that we HAVE described above, we can see that it is in principle possible to follow the measurement process from the original atom through the cascade, and to show how what was an essentially quantum mechanical process gradually turns into a directly observable pool Z. We may here anticipate the results of Chapter 8, where it is shown THATLARGE scale movements such as that of the pulse which reaches the electrodes of the ion chamber can be described by collective coordinates for which the WKB approximation is valid. This is what justifies us in saying a quantum distinction OF states OF different angular moment is eventually made classically manifest and therefore observable in the usual way, which requires no further special analysis. At this stage we can say THAT everything has happened if the all wave function had elapsed to 1 corresponding to the actual result obtained in the measurement. We emphasize, however, that in our treatment there is no actual collapse, there is merely a process in which the information represented by the unoccupied packets effectively loses all potential for activity. Or as we have put it in Chapter 5, the range of potent IAL activity of this information is spontaneously narrowed down in essentially the same way as happened with transition processes. It follows that in this regard measurement is indeed just a special case of a transition process in which the two systems interact and then come out in correlated states. It is this correlation that enables us, from the observed result, to attribute a corresponding property to the phi-NAL state of the observed system. In the transition process that takes place in a measurement, it is clear that, as happens indeed in all transition processes, there is no need to place any cuts or arbitrary breaks in the description of reality, such as THAT, for example, introduced by von Neumann between the quantum and classical levels, see Chapter 2. In fact, we have given what is, in principle, a detailed account of the whole process of measurement which is not restricted to the phenomena alone as Bohr requires, WHILE nevertheless retaining a wholeness similar to that of Bohr in certain ways which will be discussed in more detail later. For those who are accustomed to the conventional interpretation of the quantum theory, the notion of empty wave packets arising naturally in transition processes and artificially in measurement processes may not seem to be acceptable, even though we have shown that they constitute inactive information that will never have any subsequent effect on the particles. This objection probably arises mainly because the conventional interpretation assumes either tacitly or explicitly that the wave function corresponds to the actual state of the system and as such constitutes the basic description of reality, at least in so far as this latter can be described in any way at all. Therefore it could be felt that the empty packets, WHH, also satisfy Schrödinger's equation, constitute a vast mass of bits of reality that are, as it were, floating around interpenetrating that part of reality, which corresponds to the occupied packets. In our interpretation, however, we do not assume that the basic reality is measurement as a special case of quantum process 105, thus described primarily by the wave function. Rather, as we have stated in Chapter 3, we begin with the assumption that there are particles following definite trajectories, and as we shall see in Chapter 1 we can also incorporate ordinary fields such as the electromagnetic in this general approach. We then assume that the wave function T/J describes a qualitatively new kind of quantum field which determines the guidance conditions and the quantum potential act ing on the particle. We are not denying the reality of this field, but we are saying that its significance is relatively subtle in the sense that it contains active information that guides the particle in its self-movement under its own energy. The behavior of the particles is profoundly affected by this field so that it has fundamentally new features relative to those of classical physics. The effects of the quantum field will, however, become manifest only at the classical level in the collective movement of large numbers of particles. In the later, the WKB approximation will generally hold and the quantum fields can be neglected. So ultimately, all manifestations of the quantum fields are through the particles. We may make an analogy here to human relationships in society. The most immediate and concrete reality is the collection of individual human beings. Insofar as these are related by pools of information, this latter will become manifest in the behavior of the human beings. The behavior both of the individual and of the society depend crucially on this information. Rather, as happens with the particles of physics, the information itself is held at some very subtle level which does not show directly and which has negligible energy compared with that involved in the physical movements of the people. To complete the analogy, we might surmise that perhaps the information in the wave function is likewise contained at a more subtle level of negligible energy in a way THATH has not shown yet and that we have not thus far been able to study. In this analogy we can see that information is constantly losing its potential for activity. For example, people may see that some of it is irrelevant or wrong, while a great deal may simply be forgotten. Even if the information is preserved in books or on discs, most of these latter eventually become more and more difficult to access, for example, by being sent to deposito RIES and ultimately by being shredded. Other information is simply lost by dispersal, for example, by the spread of sound waves and radio waves. Insofar as this information can no longer affect human beings, or their proxies in the form of computers, it has lost its potential for activity. It is clear then that nothing is more common in ordinary experience than for information to lose its potential for activity. If we accept that THE particle is what responds to information at THE quantum mechanical level, it is clear that there is no serious problem with the empty wave packets. The essential point is that information is immensely more subtle and less substantial than the systems on which it acts. If we give up the idea that the wave function is what comes closest to describing that which may be called the substance of reality, then the loss of potential for activity will be quite a natural and, indeed, even an expected feature. Another reason why many may have found it difficult to accept our ontological interpretation is that the wave function is all that is used in statistical calculations, which indeed makes no mention of the particles, except to say that the statistics yield the frequency with which they may be registered in specified experiments. Since particles seem to play no part in the calculations, and since the latter are what occupy the major part of the attention of physicists, it may be felt that the wave function which corresponds to the quantum state, is in essence what THE theory is. All about. Therefore to have inactive parts of the wave function may seem unacceptable. However, if we think further about our analogy to the behavior of human beings, we may note, for example, that in the statistical behavior of people moving on roads with signs that inform them, their behavior could, in certain cases, be calculated from the information implied by the signs. without the need for a detailed description of the movement and activity of the human being as a whole, e.g., including his muscles, his senses, his brain, and nervous system, etc. Similarly, it need not be surprising to discover that the statistical behavior of the particles of physics can be calculated from the information in the wave function without knowledge of the detailed constitution of the particles themselves. In both cases, the fact that a quantity provides a complete basis for statistical calculations does not imply that it also provides a complete basis for an ontology. 6.3 Quantum properties not generally attributable to the observed system alone. The very notion of a measurement implies, as has been explained earlier, that we are using the macroscopic observable results of the operation of a measuring instrument to attribute some property to the object itself. However, it can easily be seen that in what is called a quantum measurement, such an attribution is not in general possible. For during the interaction between object and measuring instrument, there is the linear combination 6.4 of wave function s. It follows that through this period, the two systems are guided by a common pool of information implying a quantum potential that connects them in a non-local way. As pointed out section 6.2, the orbits of both particles are then strongly correlated and yet highly measurement as a special case of quantum process 107. Unstable. Given we always start with a statistical ensemble P equals 1 cent 1 2, which fluctuates at random from one experiment to the next. There will evidently be no way to predict or control in each individual case which channel the particle will enter, even though this motion is determinate in itself. When the interaction is over, the channels will be separate and the information in the unoccupied channel will, as we have already seen, become inactive, leaving only the occupied channel with its quantum potential. The wave function, and therefore the effective quantum potent IAL, will then be profoundly altered, e.g. from a z component of angular momentum 0 to a z component of h. The apparatus particles will also have been correspondingly altered, e.g. one of the counters going from the unfired to fired stat E. It is clear then that we are not measuring a state that has already been in existence. Rather, the apparatus and the observed system have participated in each other, and in this process they have deeply affected each other. After the interaction is over, we are left, as already pointed out in the previous section, with a situation in which the states of the two are correlated, in accordance with the channel THAT the particles have actually entered. In certain ways the above behavior is strongly reminiscent of Heisenberg's notion of quantum properties as potentialities belonging both to the observed system and the observing apparatus, RATHER then being just intrinsic properties of the observed system alone. Which potentiality is actualized depends on the observing apparatus as well as on the observed system. For example, if the Stern-Gerlach apparatus is oriented in the z direction, we actualize the potentiality of the atom to come into a state of well-defined angular momentum in this direction. On the other hand, if the apparatus is oriented in the x direction, we actualize a different set of potentialities for the angular momentum now to be well defined in the x direction. Evidently, the simultaneous actualization of the two sets of potentialities is mathematically impossible, and this corresponds to the physical impossibility of simultaneously orienting the Stern-Gerlach apparatus in both of these directions. One can here make use of the analogy of the seed discussed in Chapter 2, Section 2. 3. The different possible orientations of the apparatus correspond to different environments of the seed, which in turn lead to different forms of the plant. In the case of particles, we can see how changing the orientation of the apparatus changes the quantum potential and how this in turn changes the possible states in which the system can be actualized. In this way we obtain an explanation of Bohr's principle of complementarity, which states that the experimental conditions needed for measuring a given physical quantity are incompatible with those needed to measure another one, when the operators corresponding to these quantities do not commute. Y.T this A.2 Maya.ns is Tha.T quantum properties Ca not B Sa.id to belong to the observed system A.lone A and D, more generally, Tha.T such properties Ha.ve. No meaning A.pa. RT from the to Ta.L context WHH is relevant in any Pa reticula.R situation. In this case, this includes the overall experimental A.redoutangement. So Tha.T we see ANSA.Y Tha.T measurement is context dependent. The A.hove is indeed a co-n sequence of the fact Tha.T quantum processes A.re irreducibly. Pa reticipa.tori in the Wa.Y we Ha.ve explained her E. Even in classical physical ICS, measurement Ma.Y strongly disturb THEOB. Served system A.ND introduce LARGE changes in its conditions. Moreover, it is possible to Ha.ve situations in which this disturbance is unpredictable A.ND. Uncontrollably, for example, if the interactions A.re such as to bring A.bout chaotically unstable motions. Since the initial conditions of the observing A.pp A.ra thus can never be determined exactly we ma.yhave A.n unpredictable A.nd uncontrollable disturbance of a significant magnitude even in these classical situations. Therefore we see an evidently Ha.vec classical conditions in which faithful measurements A.re not possible because there is no Wa.y to correct for, or otherwise take into account, the effects of the disturbance A. Rising in the measurement process. However, A.T the quantum level something much more radical is involved in this. For the interactions which now depend on the quantum potential, CAN introduce LARGE non-Lika.L connections between A.2 the constituents of the Tota.L system which A.re not pre-signed functions of the properties of this system. This is as if the basic LAW of interaction of A.2 the PARTS were Chang in the process in which the observed system and observing A.pp A.ra thus come into contact. The result is therefore in effect, a transformation of the very nature of the system as a whole.nd of A.2 its constituents. In the quantum case, the Pa reticipation therefore is of a deeper A.nd more funda. Menta.L and A.tour Tha.N it is classically. Indeed in classical physics no ma.ter. How much the observed particle is disturbed funda.menta.lly, its basic La.ws of interaction rema.I and the sa.me, being expressible, for example, as pre-signed functions of A.2 the particle Virginia.bless. Therefore the basic properties of the particles may be regarded as intrinsic, no matter how strong the interaction ma.y But in the quantum theory such properties can, as we Ha.ve pointed out, Ha.ve meaning only in the tot.a.i relevant context. The nearest classical A.na logi to the A.hove situation arises in connection with the free energy of a thermodynamic system. F equals E, Ts. In the above, E is the intrinsic energy of the SYSTEM, but the A.til energy available in an isothermal process is 6F equals 6E, T6S, where 65 is the charge of entropy. But T6S is equa.L to the heat which flows into the bath in an MEnt as a special case of quantum process 109. Isothermal process. The free energy is therefore not an intrinsic property of the system, but one that H as meaning only I in the context of a thermal bath, with which the system interacts. The analogy to the quantum theory is clear, but it must be emphasized that the context dependence of properties in quantum mechanics is much more radical and far-reaching than it is in thermodynamics. However, apart from the field of thermodynamics, the notion of properties that are not intrinsic but are inherently dependent on a total context has actually been suggested to play a fundamental role in cosmology through the MACH principle. This states that basic properties of a particle, such as mass, depend on some form of collective feature of the general distribution of matter which includes indefinitely far-off systems. And as we have SEN, the quantum properties imply something similar, but far more widespread and pervasive, in the sense that measured properties are not intrinsic but are inseparably related to the apparatus. It follows then that the customary language that attributes the results of measurements, e.g., momentum and angular momentum, to the observed system alone can cause confusion, unless it is understood that these properties are actually dependent on the total relevant context. For example, the actual momentum of the particle is given by p equals \7s. But this evidently depends on the wave function and as we have seen earlier. The latter may either correspond to a pool of information common to many particles or may depend on distant features of the environment, such as a slit system. It is clear then that, as we shall bring out in more detail presently, the momentum of the N111 particle pin equals 85/ox, n is not an intrinsic property of that particle ln e, but can only be understood in relationship to other particles and to all the relevant features of the environment. In this interpretation there is one property that is intrinsic and not inherently dependent in this way on the overall context. This is the particle position, z. It is evidently intrinsic because we have defined it in a way that is conceptually independent of the wave function. Moreover, it is intrinsic also in the sense that it can be measured without being altered. This can be done, for example, by introducing an interaction between the particle and the observing apparatus in which the interaction Hamiltonian is a function that is proportional to the position, x, itself. In equation 2-3, we may therefore write 0 equals z. Because z is a continuous variable, we can write the initial wave function as il equals j c 06 z of o y d 69 110. The undivided universe. The final wa.ve function is 111j equals j c e b z o o y a1zt d 610. If bi is the width of the packet o, this measurement will ma.ke possible. A.n observable distinction between values of e differing by 6z equals by iait. Recalling tha.t, this is A.n impulsive measurement t, the change of z resulting from the original momentum possessed by the particle can be neglected. Moreover, the wa.ve equation during the interaction is al/ equals a1z a l/ at I 611 implying tha.t the only cha.nge is to shift cent 0, y, to cent 0, y, a1zt. It ma.y. Be assumed with sufficient generality tha.t cent 0 is rea.I, so tha.t this term will not introduce a.New York cha.nge in the momentum of the z-radical, p, equals 85/x. It follows tha.t the position of the z-radical does not cha.nge in this mea. Schurman t. It is therefore possible to attribute this position Virginia-Rea.Bli to the particle itself. However, while the position has not been changed in the measurement, the wa.ve function h has in general been changed because the interaction with the measuring a.pp a.ra+can bring a.bout a new wa.ve function tha.tcanb. Much more localized in z-space than the original one was. Since all other properties of the electron depend as much on the wave function as they do on the position of the particle, the measurement is still pa-rticipa.ting in an essential wa.y. Therefore, even though the particle position h has been determined faithful ly, that is without changing it, this is not true of the other properties. With rega.rd to the later we still cannot in genera.I talk of a measurement as something which simply establishes y.t the state of the observed system is. Therefore, while the position of the particle considered as a.n.a.bstra.ct concept is a.n intrinsic property, the other properties a.re, in genera.I, still context dependent. If we try to measure properties other than position, we find dtha.t, as we ha.ve already pointed out, the result is affected by the process of interaction. In awa.y tha.t depends, not only on the tota.iwa.ve function, but a.lso on the details of the initial conditions of both the particle and the a.ppa.ra+. To illustrate this we consider a measurement of the momentum p. In equation 2.3, we introduce the opera.tor 0 equals p. We then write the initial wave function as 111 equals j c p e pz dp o y 612. The phena.iwa.ve function is il j equals j c p e pz o y a 2 pt dp 613. Measurement as a special case of quantum process 111. This measurement will make possible an observable distinction between values of p differing by 6p equals, y/2, t. In effect, this process turns the inal wave function into wave packets of width in momentum space 6p and in position space 6z equals 1/6 p equals 2, t/y. These wave packets do not interfere because they correspond to non-overlapping states of the apparatus variable. It is especially clear in this example how a measurement transforms the whole system in a radical way. To illustrate this in more detail, suppose we originally had a narrow wave packet in z space of width 6z0. After interacting with the momentum measuring device we would have a set of wave packets of width 6z equals 1/6p, where 6p is the accuracy of the momentum measurement. If 6p is very small, it is clear that the effect of the measurement is to use the origin al packet to spread a great deal in position space, in the same operation in which it narrows in momentum space. On the other hand, if we had origin ally a broad packet in z space, and then measured z to a great accuracy, the effect would be, of course, to cause the packet to become very narrow in position space, while it spread out over momentum m space. To bring out yet further how the act UAL particle momentum m is generally changed in a moment measurement, let us consider an initial state in which c, p, is chosen so that the overall wave function is real, i.e. c, p, equals c, p. The original particle momentum is p equals vs equals 0. After the measurement the particle W'll end up in one of the packets corresponding to the mean value of the momentum, pm. The momentum has thus changed from 0 to something close to pm. In the ordinary quantum mechanical language of the conventional interpretation, the momentum m operator commutes with the Hamiltonian for the measurement process, so that one would have expected it to be a constant of the motion. How then is a change in this momentum possible? The answer is that, in our interpretation, the momentum operator is definitely related to the particle momentum only when the wave function is an eigenfunction exp z of this operator. More generally, as has already been indicated in chapter 3, the actual particle momentum and the corresponding operator are not necessarily so closely connected. In such a measurement the interaction can be described by replacing 6.T by T in equation 613. The wave function is then I/1 equals Jc, p, exp ipz 2 pt, dp, 614. The coefficient of exp ip z becomes c, p. 0.2 pt, with c, p, equals c, p. 112 THEU undivided universe. The reality condition is no longer satisfied because c, p, cent 0, 11, a2 pt, c degree, p, cent 0, 11, a2 pt. ic, p, cent 0, 11 plus a2 pt, 615. Therefore p equals vs. Is no longer 0. ASTCHNGs, the phase will change. And this implies that the particle is steadily changing momentum, at least until the wave packets cease to overlap, when its momentum will be some constant pj, according to WH at packet the apparatus particle actually enters. If we were to work out the quantum potential, we would see that this would explain the change of momentum that takes place during the process of interaction. To bring this out in yet another way, let us consider the example of a one-dimensional particle in a box of length L. A particular initial wave function of the system may be n7rx asm L 40 y a n7rx n7rx 2i exp pound exp I L 0 colonnes y 616. The initial momentum of the X particle is evidently 0. The quantum potential is q 182/8x2 sin and 7rx/L 2m sin and 7rx/L equals c f 2 617. As pointed out in chapter 3, section 3. 5, the quantum potential now contains all the energy which, in the conventional interpretation, is attributed to the kinetic energy of the particle. In the conventional interpretation, the latter is supposed to be moving back and forth with equal probability of being in either direction. Yet if this were actually the case, we would not understand why a particle with constant speed p/m could cross the regions where the probability is 0. Evidently we should not take this pi2 or 2 literally. But it is better to think of it as a figure of speech that people have become accustom to use. On the other hand, in our interpretation we have a consistent picture because the p-particle is at rest and there is no force on it. Because the quantum potential is constant. After interacting with the measuring apparatus, this wave function splits into two non-overlapping parts, which may be writ10 as equals a 2i exp1 px cent o y a2 pt. Measurement as a special case of quantum process 113 a plus 2i exp1 px cent o y plus 2 p.1.t 618. But during the interaction there is a period throughout which these two parts overlap. In this period, the quantum potential will not be a constant. And we see that the particle will be accelerated. Ultimately we end up with the particle in one of these packets with equal probabilities for both possibilities as in the convention AL interpretation. However, there is a key difference in the language that we use to describe this process. In the conventional interpretation it is stated that we have measured the momentum without changing it, but in our interpretation, the particle's momentum h has been changed. This emphasizes that, in a measurement process, we do not in general find an intrinsic property of the observed system that was already there. Rather we have an irreducible participation of each system in the other. Therefore the momentum is no t. As Wehave already said, an intrinsic property. This will be true for all properties other than the position. We can bring out this character of the momentum further by considering the formulae for the mean values of p and of p2. These are and p j ip asterisk x x ip x dx j I x ip x dx j a 5 p x x dx. P is obtained simply by averaging the momentum of the particle of 5/ax over the probability distribution p x. But to obta in p 2, it is not enough to consider the average of a 5/x 2. We have also to add a term ar/x/r. This shows that the average value of an operator as computed quantum mechanically ca not in general be obtained by averaging the corresponding physical property of the particle over the position distribution. We understand this as a consequence of the fact that the momentum one's not 1 for the undivided universe an intrinsic property, but rather is inherently context dependent so that it involves the participation of the measuring apparatus and the quantum field as a whole. Quite generally all powers of the momentum operator higher than the first are to be understood in a similar way. See corresponding results can be obtained for the angular momentum operator, h/i8/8 cent. 6.4 The meaning of the uncertainty principle. Since our interpretation gives the same statistical distribution of experimental results as does the conventional one, it follows that the proofs usually given for the uncertainty principle will also be valid in our approach. The meaning of the uncertainty principle is, of course, that there is a limit to the precision with which properties can be attributed to the observed object on the basis of observed experimental results. Or as Bohr 1 has put it, there is an irreducible ambiguity in the meaning of these results as referring to intrinsic properties of the observed object. Because of this ambiguity, it becomes impossible to know from a mea Surement exactly what the state of the particle is and d, of course, this implies that we do not know exactly how it is going to behave after the measure. Meant. In general, the ambiguities of the actual particle's positions and momenta will be e of the order of those present in the spread of the wave packets, as we have explained in more detail in Chapter 3. But in particular cases this may not be so. For example, in a stationary state, the ambiguity in the momentum of the particle p equals \7s was seen to be 0. So if p represents the actual momentum of a particle as it moves, or is at rest, in its trajectory, Heisenberg's principle can in certain cases be violated. In our interpretation, however, what Heisenberg's principle refers to is not the actual momentum of the particle itself, but the value of the momentum that can be attributed to the particle after what is commonly called a measurement of the momentum. And because measurements are actually participatory, these two can differ. Indeed, it is misleading and even confusing to describe what happens as a measurement, rather as if, in the observation of the mature plant, we were said to be measuring the properties of the seed. Perhaps, as Bell too has suggested, we should call the whole process an experiment or even a participatory experiment revealing the potentialities of the system in question. Indeed, this participatory feature has already been noted by Wheeler 3 in a different context in WHH. However, there is no way to explain how it comes about. Another way of looking at the participatory nature of quantum experiments in which something is said to be measured can be seen by measurement as a special case of quantum Prosu 115. Sidering equations, 6.2, and 6.3. These describe a process in which the wave function is eventually transformed into a set of eigenfunctions of the operator that is being measured, and each eigenfunction is multiplied by a corresponding apparatus wave function which does not overlap the others. The function actually containing the particles of both the apparatus and the observed system then selects what will be the effective wave function, realizing one of the potentialities of the overall experimental arrangement, while the empty channels can be neglected. What we learn from the measurement is not only the value of the operator but also the final effective wave function of the observed system. From this we can locate the observed particle somewhere in the region in which the wave function of the particle is appreciable. The role of th particle is crucial here, and it makes it possible for the system to select one of the eigenfunctions which will be effective without the need for a collapse. If in the quantum domain experiments are thus mutually participatory transformations, how do we understand the ordinary classical experience, in which we definitely obtain measured results that can be unambiguously attributed to the observed system without any question of mutual participation? The answer is, of course, THAT. For measurements carried out in the classical limit, such participation is negligible, and the transformation of the wave function is unimportant because the quantum potential is negligible. We may bring out this point in more detail by considering a system with wave function t/i, z, whose Fourier coefficient is cent. P. Let 6.z be the width of the wave packet in z space and 6.p be its width in p space. We can then show THAT in measurements of z and p carried out to respective accuracies 8z and 8p, the change of the wave function will be negligible. When 8z 6, z and 8p 6.p. In THIS case, the participatory character of the interaction will not be significant, so that the net result is just to provide information, of limited accuracy, about the system. Along the lines leading to equation 6.3, we can say that in a measure meant of z, an initial wave function t/i, z, equals j t/i, 08, z, 0d, 619, goes over into 6.20, with the accuracy of measurement given by bz equals by/16, t, whereby is the width of the apparatus wave packet. If we choose bz6, z, the change of 0 colonnes y \1z6t over the region in which phi o is appreciable can be neglected. 1/16 undivided universe. And 80 we obtain to a good approximation. 621. Where z is the value of z at the center of the particle's wave packet. This gives 6.22. If the value of y is observed as y0, the value z can be inferred as z equals y0/a11 t. Thus by observing the value of y we are able to measure z to an accuracy 6z equals 6y/a1t, t without making any significant changes in the observed system. A similar argument can be made for the measurement of momentum, showing that it is also possible to measure the latter without significant participation provided that 6p/p. If we then consider the two results together, we conclude then that the ordinary idea of non-participatory measurement holds only when the measurements are much less accurate than the limits set by the uncertainty principle. But the conditions for this are the same as those for the classical limit. So it follows from our interpretation that in this limit we can ignore the participatory implications of the quantum theory in discussing the meaning of measurements. 6.5 On proofs of the impossibility of hidden variables in the quantum theory. Historically, the question of an ontological interpretation of the quantum theory was first put in the form of asking whether there could be hidden variables. These, along with the wave functions, would determine the results of individual experiments, and when treated as a statistical ensemble, they would also explain the probability distribution of the corresponding ensemble of experiments. A detailed discussion of the work up to 1973 can be found in Belinfante 4. Rather early in the developmento of the theory, work along these lines was strongly discouraged by a theorem of von Neumann 5, claiming to show that no distribution of hidden variables could account for the statistical predictions of the quantum theory. We shall not reproduce his argument in detail here, but we shall merely focus on what we regard as the essential point at issue. Measurement as a special case of quant BM process 117. According to the uncertainty principle, the quantum theory implies that there is no state in which the values of non-commuting operators are well defined. We can ask, however, whether there are not some additional hidden parameters that would select sub-ensembles in which such operators could be defined within limits that are narrower than the uncertainty principle. An extreme case would be what von Neumann called a dispersionless ensemble, in which these operators would all have definite values. Von Neumann 5 gave an argument aiming to prove that if there are such dispersionless ensembles, then quantum mechanics must be objectively false. A basic assumption underlying his proof is that if A and B are any two operators, there is an operator A plus B such that A plus B equals A plus B, 6.23. Where A, etc. denote the expectation values of the operator. This relationship does in fact hold for the ensembles treated in the quantum theory. But von Neumann assumes that it also holds for sub-ensembles. In particular, it would have to hold for a dispersion-free ensemble in which the values v, a, v, b of the quantities associated with the operators a, b were well defined and therefore equal to the corresponding eigenvalues of these operators. It is easy to see that this requirement cannot be satisfied. We shall discuss this question with the aid of an example given by Bell 6, i.e. a particle of angular momentum with the eigenvalues of the components Lr, L11, L, evidently restricted to n, 0, n. We begin with the two operators A equals Lr and B equals Li, then the angular momentum L at an angle of 45 degrees. Between these directions is L equals Lr plus Ly, 624. In the dispersion-free case this becomes V, L, equals V, Lx, plus V, Li. But there is no way to satisfy this if V, L, equals plus or minus H, and so one might conclude with von Neumann that there can be no dispersion-free state. Bell has given an answer to this. As is well known, and as von Neumann agrees, there is really no meaning to combining the results of non-commuting operators such as Lx, Li, and L. For example, to measure Lr we need a Stern-Gerlach magnet with a field in the x direction, while Li and L would require fields in their corresponding directions. These measurements are incompatible and mu2Lly exclusive. Therefore we cannot arrive at an inconsistency in this way. However, the interesting point I1 that in spite of this incompatibility, equation 623 is still true for quantum mechanical averages over the three separate series of measurements of Lr, L11, and L respectively. As we shall make clear later, the essential point is that von Neumann had in mind hidden parameters that belonged on Ly to the observed system itself and were not affected by the apparatus. The three different pieces of apparatuses discussed above constitute three different and incompatible contexts. Therefore, for an individual experiment there is no reason why Lr, L11 and L should be related in the way that operators are related. However, as we have already remarked, equation 623 is still valid for averages over statistical ensembles of experiments even though it has nothing to do with individual experiments. The above criticism of von Neumann applies to non-commuting operators. But if the operators commute, then it might seem that we can reasonably expect that even for individual cases the values of operators will have the same functional relationships as the operators themselves. There has been a continuing effort to improve on von Neumann's treatment by considering sets of commuting operators. Among the earlier discussions of this problem we may mention Gleason's work 7, on the basis of which J.A.Uke and Perrin thought that the HAD proved the impossibility of hidden variables. Bell 6 later showed that they had merely ruled out a limited class of such variables, i.e. those that are context independent. Bell did, however, point out that this proof did not apply to our interpretation because the latter implied context-dependent HID-den variables. This latter point does not seem to have taken seriously by a number of workers in the field. Thus Cochin and Specker 9 gave another independent proof which was similar in content to that of J.A.Uke and Perrin, but which had the advantage of using operators THAT be measured by known physical procedures. However, their proof was rather complicated. And later Paris 10 gave a much simpler proof for the C as E of 2 part equals of spin 1/2. Meanwhile Gr. Einberger, Horn, Shimony and Zeilinger 1 have also developed a simple proof along similar lines for the case of 3 or more particles of spin 1/2. Merriman 1 summarized these in a very Concise way. F. Or a helpful treatment of this phase of the work. C. Brown and Svetlikny 13. All these authors use the example of commuting operators and are therefore basically similar in their fundamental assumptions. We shall therefore carry out the further discussion in terms of Merriman's presentation, which is the simplest of these. Merriman begins with a set of commuting operators A, B, C. He then points out that if some fundamental relation J, A, B, C equals 0, 625, 0, 1 R0 2 R0 1 R0 2 R1, 0 feet 211 inches 0 feet 1 inch 11 0 feet 1 inch 11 0 feet 211 inches 1, 0 1 R0 2 11 0 1 Y0 2 R0 feet 1 inch Z0 2 Z1, 1 1 to 1. Table 6. 1. Spin operators. Holds as an operator identity, then since the results of the simultaneous measurements of A, B, C, W will be one of the sets of simultaneous eigen values A, B, C of the operators in question, these results must also satisfy F, A, B, C equals 0. Independently of the ST8 of the system prior to measurement T. He then assigns TOTHE observables A, B, C. FOR an individual system. THE values V, A, V, B, V, C. These values are assumed simply TOB. Revealed by measurement of the corresponding operator. Since any measurement must give rise to an eigenvalue of the corresponding operator, the value assigned to that operator must be one of its eigenvalues. And since any commuting subset of the full set of operators can be measured simultaneously if the values are to agree with the predictions of quantum mechanics, they must be constrained by the relation F, V, A, V, B, V, C equals 0. 6.26. We now go on to consider a system of two particles, each of spin half, and the 9 operators shown in table 6. 1. It is easy to see that the product of the 3 operators in each row is 1 as is indicated in the table. The product of the operators in the first 2 columns is also 1, but the product of the operators in the third column is 1. Moreover, it is also easily shown that the operators in each row commute, as do those in each column. Therefore the values of the operators satisfy the same constraints as do the operators themselves. Thus we have V, 0 feet 1 inch x 0 feet 2 inches x, V, 0 2x, V, 0 1x, V, 0 feet 111 inches 0 feet 211 inches, V, 0 feet 111 inches, V, 0 feet 211 inches, 1, V, 0 feet 1 inch x 0 2y, V, 0 1y 0 2x, V, 0 feet 1 inch z 0 2z, V, 0 1 r 0 2y, V, 0 2y, V, O, x, must, V, 0 feet 1 inch y 0 2x, V, O 1 y, V, 0 2x, 1, V, OTZ 0 feet 2 inches z, V, 0 1 y 0 2 y, V, 0 feet 1 inch x 0 2x, 1. In the above set of equations each value appears twice, once as a member of a row and once as a member of a column. The values of all 9 operators 1 to 0 tu undivided un ivory are plus or minus 1. Therefore if we multiply all these equations together, the product of the left hand side is 1. On the other hand, the product of the right hand side is 1. This contradiction implies that there is no consistent way to assign values to all the operators. This contradiction rules out the model of quantum theory that is proposed by Merriman, and, of course, all the other authors who use essentially the same model. The basic assumption in this model is that the values v, a, v, b, v, c of the set of variables specifying the individual system are equal to the results r, a, r, b, r, c of measurements of the corresponding operators. The above is equivalent to supposing that the variables are specified by v, a, v, b, v, c, and that, as we have already said, the measurement simply reveals the values of these variables, as would happen in classical physics. In our interpretation we do not assign values such as v, a, v, b, v, c to the operators. For these operators do not correspond to variables in our approach. Rather the variables are the overall wave function together with the coordinates of the particles, both of the observed system, x, and the of the observing apparatus, y. These variables determine the results r, a, r, b, r, c of each individual measurement operation. But these results are not present before the measurement operation has been completed. Rather they are then only the potentialities whose realization depends not only on x and y, but also on the overall wave function of the system and on the interaction Hamiltonian h1 between the apparatus and the observed object, the latter being determined in principle by the operator 0 that hs to be measured. Therefore, as we have already pointed out earlier, there is no pre-existing quantity that is actually revealed in this process. The above may be said to give the full meaning of the statement that the results are a, r, b, r, c are context dependent. On the other hand, in the model used by Merriman, the results are assumed to be determined solely by the values v, a, v, b, v, c, and are therefore context independent. Let us now return to a consideration of Merriman's treatment. Since we do not assign values to operators, there is, of course, no unambiguous way to apply Merriman's argument to our model. What we do instead is to show that the measurement of the operators given by Merriman do not lead to contradictory results. This is, of course, sufficient to demonstrate that our approach is consistent. Strictly speaking, we ought to describe by means of some physical arrangement how each of the operators above could give rise to the results r, a, r, b, r, c of the corresponding measurement process, with operators such as u1x and u2y. This can be done fairly easily by assuming that the particles are far apart and that the first particle undergoes a measurement as a special case of quantum process 1-to-1 Stern-Gerlach process with the magnetic field in the x direction, while the second particle undergoes a process with the field in the y direction, see Chapter 10. However, with product operators like u1, u2, no one has yet suggested any physical process that could lead to results corresponding to their measurements, which would to be of a non-local kind. Until such a procedure is suggested, we see a not demonstrate in detail how our approach leads to no contradiction with regard to operators of this kind. However, if we accept Merriman's assumption that such a measurement is somehow possible, then we see and show that its results will not lead to a contradiction with those operators that may be measured. Let us first recall with the aid of equation 6.4, and the paragraphs that follow it, that any operator 0 which can be measured will lead to a linear supposition of wave functions corresponding to its different eigenvalues on. The active part of the wave function then effectively reduces to one of these eigenfunctions determined by the channel that is actually entered by the particles concerned. In this way we show that for a general operator 0, the result of measurement is one of its eigenvalues on, and that the observed system is left with the corresponding effective wave function t/jn. We now apply these ideas to the operators in table 6. 1. It will be sufficient for our purposes to consider the operators in the phi rst column and in the last row. It will also be convenient to write ct.r equals a ct1y ct 2.r equals b ct 2y equals b ct1z ct2z equals a ct1x0 2y equals c. Together with the identities c equals ab equals ab. It is crucial to our argument to note that although a, b, c commute as do a, b and c, a and b do not commute with a and b. If we measure a, the result will be an eigenvalue and the effective wave function will be the corresponding eigenfunction 1/a. Because a and b commute, if we then measure b, the result will be a simultaneous eigenfunction of both operators, t/jan bn. It follows trivially that t/jan bn is an eigenfunction of c, corresponding to eigenvalue and bn. So if we measure c, the result will be the product and bn. Therefore the operator identity c equals ab implies the corresponding identity of the results are c equals r, a, r, b. A similar argument can be made for the commuting set of operators a, b and c. However, it is important to keep in mind that a and b do not commute with a and b. Therefore a different and incompatibly measuring apparatus is needed to measure a and b, which excludes the apparatus necessary to measure a and b. 122. The undivided universe. Let us recall here that the results depend as much on the wave function as on the apparatus variables y as it does on the variables of the observed system, x. This implies that the results obtained for c when the apparatus used to measure it can also be used to measure a and b simultaneously. Will not in general agree with the result obtained for c using an apparatus that would allow a and b to be measured simultaneously instead. It is this point that enables us to avoid the contradiction produced by Merriman. This contradiction depends on assuming that the result of c, r, c, is the same in both c/s's. As we have already pointed out, it may be said that a measurement of c is context dependent in the sense that the result obtained when a and b can be measured along with it has no necessary relationship to the result that would be obtained for c when a and b could be measured simultaneously. Because a and b do not commute with a and b, the corresponding pieces of measuring apparatus provide contexts that are mutually incompatible. It follows then that Merriman's argument makes assumptions that have no place in our interpretation, so that the contradiction to which it leads is not relevant to our approach. Cochin and Specker 9 have argued that the context dependence described above does not invalidate the kind of proof of the impossibility of hidden variables that we describe here. This is because the results of the quantum mechanical observations should be determined by the hidden variables of the combined apparatus and observed system, so that the net result for the combined system should be predictable in each case. Therefore the argument against hidden variables should still go through when applied to the combined system. Our answer to this is that when non-commuting operators are measured, different and incompatible pieces of apparatus are required. Therefore we have as many combined systems as there are rel. even sets of non-commuting operators, so that there is no single phase space for the combined system. This means that one of the basic assumptions underlying the proof of the impossibility of hidden variables is not satisfied in our approach. The context dependence of results of measurements is a further indication of how our interpretation does not imply a simple return to the basic principles of classical physics. It also embodies, in a certain sense, Bohr's notion of the indivisibility of the combined system of observing apparatus and observed object. Indeed, it may be said that our approach provides a kind of intuitive understanding of what Bohr 16 was saying. He described a measurement as a whole phenomenon not further analysable. The description of this phenomenon includes a specification of the experimental conditions, which are equivalent to the context that we have been discussing, along with a statement of the results. From the results and the conditions, one infers the values of the measured qualities, but 88 in our approach, it is not implied in Bohr's treatment that these values correspond to variables that exist independently of the overall experimental context. 6.6 No measurement is a measurement. In the conventional interpretation of the quantum theory, one obtains a certain paradoxical quality for the case of what is called negative measurement, i.e., measurements which establish a given result by showing that the only possible alternative is not present. To illustrate this sort of paradox, suppose that by means of a Stern-Gerlach apparatus, we select a beam of atoms with a definite value, 0, for the z component of the orbital angular momentum. We then do a further Stern-Gerlach experiment with the apparatus oriented in the x direction. The beam splits into two parts cor, responding to values of the x component of +1 I and h. The wave function of the atom is then I w z y equals v240 y at cent plus z plus 40 y plus at cent underscore z 627, where, as shown in equation 6440, represents the pa at defining the coordinates of the atom as a wholly, while z is the coordinate of the orbital electron, and a is a factor proportional to the strength of the interaction and to the time of its duration. Let us now suppose that a detector is placed in the beam corresponding to the h component of the angular momentum. In terms of the von Neumann interpretation of the quantum theory, we see and say that if this detector fires, the wave function collapses from its original form, 627, to 628. And as pointed out earlier, in the conventional interpretation one can regard this collapse as produced by the interaction with the apparatus. But suppose that in a certain individual case the detector does not fire. The wave function then collapses to wj, z equals 40, y, at, cent plus, z. 629. It seems difficult to accept that the failure of this apparatus to operate will produce a collapse of the other beam which, in principle, could be very far away. Or as it has been put, it seems that no measurement is a measurement. Thus the paradox arises because a non-event, i.e. the failure of TLTE, counter to phi re, precipitates an event, i.e. the collapse of THE wave function. 124 that undivided universe to a state in which the atom never even acts the counter. It is clear that the assumption that the wave function act UALLY collapses is the root of the difficulty. In the conventional interpretation this is a rather strange behavior. However, what actually happens in this experiment can be explained fairly. directly in terms of our interpretation. We begin by introducing the relevant coordinates of the detector, which may be represented by z1, zn. We have to take into account, not only the wave function aj, zi, representing the detector that has phi r ed, but also the wave function ao, zi, representing the detector that h has not phi r ed. Before interaction, the wave function for the whole system is 1. LLO, z, y, z, equals slash 2 cent io, y, at, l slash plus, z, plus cent io, y plus at, l slash, z, ao, zi, 6.30. After the interaction with the detector, the wave function is 11 feet 1 inch, z, y, z, equals cent I, y, at, l slash plus, z, a0, z, plus cent I, y plus at, 1f, underscore, z, a1, zi. 631. Where q represents the state of the particle as altered by the detector. It is clear from the above that we cannot leave out ao, zi, in equation 631, just because it describes a situation in which the apparatus has not functioned. Rather, it is evident that each part of the wave function contains some component corresponding to the detector, whether the detector has acted or not. In the above wave function, not only is there no overlap between cent I, y, at, and cent I, y plus at, but also between ao, zi, and aj, zi. For example, if the detector is an ion chamber, then as we have brought out in SEC. Shin 6. 1, ao, zi, corresponds to electrons attached to the atoms of the gas. WHILA1, zi, corresponds to electrons that have cascaded and have been col lect on the electrode to give rise to a current in a wire leading away from the electrode. Clearly the wave function for the electrons in these two Cs Es do not overlap. Taking the above into account, we can see that there are only two mutually exclusive possible configurations of the whole set of particle for which the total wave function is not zero. These are 1. The atom has angular momentum plus h and the counter h is not fired. 2. The atom h has angular momentum, h and the counter has fired. It follows then that if the counter has not fired, the atom must be in the channel corresponding to angular momentum plus h, while if it h has fired, measurement as a special cast of quantum proc to 125. It must be in the channel corresponding to angular momentum h. In this way a negative result implies that a measurement has nevertheless been made. What happens is that if the atom enters the channel that passes through the counter, the latter must fire, while if it enters the other channel, it does not. This is the sort of thing that would also happen in classical physics. We emphasize again that we do not assume the collapse of the wave function. The particle enters one channel and is only affected by the active information of that channel. Thus there is no paradox in this conclusion. As in many other examples treated in this and other chapters, we avoid a paradox in our interpretation by giving up the assumption that the wave function is a complete description of reality, which is, incidentally, what makes the further assumption of collapse necessary. By introducing the particle's position as essential for a more complete description, we turn what was a paradoxical situation in the conventional interpretation into one that is quite simple and straightforward. 6. 1. The SC Schrödinger CAT paradox. Most of the further paradoxes of the conventional interpretations of the quantum theory arise from the above described assumption, made sp. Sharply by von Neumann, that the wave function provides the most complete description of reality that is possible. For when the wave function is constituted of a linear combination of components, the actual state of the system is ambiguous in the sense that there is no way to define it as being in one of the components or the other. The process by which the system collapses is then mysterious and often ultimately paradoxical. In a long article devoted to this whole subject, Schrödinger, 1-4 criticized such assumptions with the aid of his now famous cat-paradox. To formulate this paradox, we begin by assuming a cat isolated in a box with a gun pointed at the CAT. The firing mechanism for the gun is activated when an individual electron strikes it. We further suppose a source of the individual electrons which pass through a beam splitter. The effect of this splitter is to divide the wave function into two coherent parts 1/I1, Z, and IP2, Z. The first part simply goes off harmlessly and is absorbed. The second part is aimed at the device that fires the gun. Classically, one would expect from this arrangement that if a single electron enters the system, there would be equal probability after the experiment was over for the cat to be alive or dead. This statement could be made meaningfully even before anyone had looked into the box to see what had happened. Quantum mechanically, however, we must treat this situation in terms 126 The undivided 1 mver, e, of the wave function. Let Z1, Zn represent the particles constituting the cat, and let Pl, Z1, Zn represent a living cat, while 1/Lv, Z1, Zn represents a dead cat. Furthermore, let 11-1, 11m represent the particles of the goo N, the bullet, the powder, and the firing device. Let 1/U, 11-1, 11m represent the unfired state of the system, and 1pf, 11-1, 11m represent the fired state. Initially, just after the electron passes through the beam splitter, the wave function of the total system is. After the entire process is finished, the wave function is 11 equals 1 y12 1p1 z 1/u y1 u 1h z1 zn 1 plus y121 p2 z t/f y1 u 1/iv z1 zn. Since the two components of this wave function are coherent, it then follows, in terms of the van Neumann interpretation, that the state of the total system cannot be one or the other. It therefore seems that the cat is in a state that is neither alive nor dead. This ambiguity could be removed only when someone looked into the box and saw whether the cat was dead or alive. The question immediately arises then of whether, in the case that the cat was found to be dead, the observer had not actually participated in killing the cat. Schrödinger regarded this whole situation as absurd. Firstly, it did not make sense to him that observation was needed to answer the question of whether the cat was alive or dead. In addition, even before observation, one might well think that the cat should at least know more than this about its own state. Or if one does not wish to attribute consciousness to the cat, suppose instead that it had been a human being in the box. To avoid violence, we could replace the gun by a device that would prick his skin. Would this person find himself in an ambiguous state in which his skin was neither clearly untouched nor clearly pricked by the device? In our approach, this sort of paradox does not arise because we go beyond the assumption that the wave function provides the most complete possible description of reality. To define the actual state of being of the cat, we have to consider in addition the particles that constitute it? It is evident that when the cat is alive, many of these particles will be in quite different places and will move quite differently than they would if the cat were dead. Indeed, one can easily see that in the configuration space of the particles. Measurement as a special case of quantum PROC 127 of the cat. T-air will be no overlap of 6L, 1, N, and PD, 1, N. Therefore 1T1's clear that at the end of the experiment the cat has to be either alive or dead. For the wave function corresponding to the live cat has no effect on the quantum potential acting on the dead cat or vice versa. Indeed, this sort of non-overlap is present also in the conventional interpretations. However, in these latter, there is no way to remove the ambiguity in the state of being in a coherent wave function even when the components do not overlap. But in our interpretation, the state of being also depends on the positions of the particles that constitute it, and it is this which enables us to treat this situation non-paradoxically as in essence a simple case of pairs of alternative and mutually exclusive states. As a matter of fact, it is not even necessary to go as far as the cat to resolve this paradox. Thus, if we consider the system of firing device, plus goo, bullet, and powder, it is clear that there is no overlap between the wave function t/ju, y1, ym, and t/jf, 1, m, i.e. because after firing, the powder will become gas and the bullet will move so that their particles will be in very different positions. Therefore the particles constituting this system will either be in the state corresponding to the firing or non-firing of the goo. If the gun has usually fired, the bullet will be speeding towards the cat, and will not be in an ambiguous state in which it is neither moving towards the cat nor at rest. The state of the dead cat will then follow only if the bullet is actually moving towards it. In other words, once the electron has in effect been detected, everything proceeds in essentially the same way as it does in classical physics. 6. 8. Delayed choice experiment S. Wheeler 3H has given a detailed description of several possible types of delayed choice experiments. These are designed to show that, according to the quantum theory, the choice to measure one or another of a pair of complementary variables at a given time can apparently affect the physical state of things for considerable periods of time before such a decision is made. Like Bohr, Wheeler puts a primary emphasis on the phenomenon, in which the experimental arrangement and the experimental result constitute an indivisible whole in the way discussed in Chapter 2, Section 2. 1. From HIS analysis of the delayed CHOICE type of experiment, he concludes that no phenomenon is a phenomenon until it is an observed phenomenon, so that the universe does not exist outthindependently of all acts of observation. It is in some strange sense a participatory universe. The present choice of the mode of observation SHO old 128 undivided univary influence what we say about the past. The past is undefined and undefinable without the observation. We can agree with Wheeler that no phenomenon is an phenomenon till it is observed, because, by definition, a phenomenon is what appears. Therefore it evidently cannot be a phenomenon unless it is the content of an observation. The key point about an ontological interpretation such as ours is to ask the question as to whether there is a new underlying reality that exists independently of observation, but that can appear to an observer When he locates, in physics, with the aid of suitable instruments, we have proposed a model of such a reality in which we say, along with Wheeler, that the universe is essentially participatory in nature. However, unlike Wheeler, we have given an account of this participation, which we show throughout this book to be rational and orderly and in agreement with all the actual predictions of quantum theory. In doing this we assume, as we have been emphasizing throughout this chapter, that the underlying reality is not just the wave function, but that it also has to include the particles. As we shall see in this section, when we take this into account there is no need to say that the past is affected by our observation in the present t. Nor do we imply even that what we say about the past is us affected. Therefore the need to introduce such ideas is b as ed on the insistence that the wave function provides a complete description of reality. Such insistence has led, as we have seen, to many other strange paradoxical features. E.g. with negative measurements and with the Schrödinger-Cat paradox. It seems to us preferable to consider extending our notion of reality by including the concept of particles, rather than to go on with an indefinite series of paradoxical consequences of sticking rigidly to the assumptions underlying the conventional interpretation of the quantum theory. To illustrate what is involved in the delayed choice experiment, we first describe one of the simplest arrangements suggested by Wheeler 3. The generalization to more complex cases is straightforward. Wheeler uses a photon interference experiment to apply our interpretation 1.5 to this. Experiment would require a treatment of the electromagnetic field, which we do indeed outline in chapter 1.1. However, to simplify the discussion, we shall consider instead the interference of particles such as electrons or neutrons. The experiment is shown in figure 6. 2 respective beams being then reflected by mirrors at E and B. The beams meet at an additional beam splitter F, and interference can be detected either in BEAMG or IN beam H. Two particle detectors are mounted so that they can be moved easily and quickly either to C1 and C2 or to C and C. Then when the detectors are in the position C1 and C2, the relative counting rates will be determined by the phase difference between the two routes reflecting. Measurement as a special case of quantum process 129. C. Asterisk dash dash 11 dash comma dot underscore 111. Essay. Figure 6. 2. Schematic view of the Delaunay choice experiment for photons. Passing rough a half-silvered mirror at A. Counters C1 and C2 can be moved into positions C and C, respectively from E and from B but with the counters at C and C. We can then tell which route a particle actually takes. But with the counters at C1 and C2, there is no way to tell this because the result depends on the interference between the waves that have traverse these two paths. Suppose now that a single particle enters the system, and furthermore, suppose that it is represented by a wave packet that is not too broad. We can make the choice on which of these experiments to perform at some time after the particle has entered the apparatus, but before it reaches the beam splitter F. In the conventional interpretation of the quantum theory, the wave function is, as we have already pointed out many times, assumed to provide a complete description of reality. Therefore we must say that the wave function collapses to the actual result of the measurement. Thus in the first kind of experiment, it will collapse to a state corresponding either to the firing of C or of C, and in the second experiment it will collapse to a state corresponding to the firing of C1 or of C2. if the first experiment is done, then clearly the interference will be destroyed before the waves can arrive at the BEM splitter F. But if the second experiment is done, interference will take place at the BEM splitter F, and then the wave function will collapse. Aside from the difficulties in the von Neumann concept of collapse as 130 TLAE 1 undivided undivided, discussed in Chapter 2, Shin 2. 4, there are yet no further problems in the discussion of this experiment. Such problems arise only if we try, in addition, to give a detailed account of the process by which the previous state of affairs led up to these results. AC according to Bohr, 1-6, ALSO as explained in Chapter 2, Section 2. 1. This is just what we should not try to do. However, Wheeler, apparently at least implicitly disagreeing with Bohr's position, did attempt to provide such an account. What he said was that if the counters are placed at C and Q, and if, say, only Q for ES, one can then say that the particle traversed the path AB. On the other hand, if the counters are at C1 and C2, and if only C1 fires, then, Wheeler says that in some sense, the particle must have traversed both paths together. Therefore one would conclude that what can be said about the PST depends upon the present choice of the mode of observation. It is clear, however, that in our interpretation there is no need for this strange attribution of past properties. For the reality is THAT, in all Ca5Es. The wave is split to traverse BOTH paths while the particle traverses one or other in each individual CASE. But as has been brought out in a number of contexts, THE interaction WITH, the measuring apparatus, implies mutual participation in which the phi-NAL state need not directly reveal the earlier properties of the system. If the counter is placed at C, and fire S, then, as explained earlier, the system is left with the corresponding wave function, and the interference at F is destroyed. But if the counter is placed at C2, and fires, then the system is left with the wave function corresponding to a particle moving from that point. But in getting there, whether it traverses the path ABF or AEF, it will have been affected by the quantum potential in the region of interference at F. Therefore we are not surprised to discover that the frequency of detection of such particles reflects the difference of phase between the two beams. It should be recalled, however, that even the conventional interpretation of this experiment does not imply that what we say about the past is affected by our present choice of experiments. In fact, the conventional interpretation would say THAT, in general, we see not make unambiguous statements about the past on the basis of present observation S. As we have seen, our interpretation agrees with this in a certain way, in that we cannot say from our observations at C1 which path the particle actually took. But we say that it actually took a definite path, even though we cannot say what that path actually was. It is only if with Wheeler we tried to infer this past while holding to the conventional interpretation that we get into TH's sort of paradoxical way of laking about the past. 6.9 The Watchdog Effect and Zeno's Paradox. In the conventional interpretation, the quantum theory puts, as we have seen, the observing instrument into an essential role, in the sense that without it the equations of quantum theory would have no physical meaning. At first sight one might then think that the more carefully we watched a given process, the more that we would learn about how it takes place. Yet, as has been shown 1.7.1.8, in the limit when the system is constantly watched, the process itself disappears and one is left with a constant state. While this is not actually a paradox, it does seem to suggest something unsatisfactory about the whole approach in the conventional interpretation. We shall see, however, that when Th's question is viewed ontologically, the whole effect can be seen to arise quite naturally in a way that is as highly explained. To discuss this question, let us consider the simplified example of an atom of angular momentum h in a magnetic field BIL the z direction. The possible eigenvalues of energy of the atom in this field will be EB 0, 2mc 2mc. Suppose that initially the wave function corresponds to an angular momentum of 0. The transition to THE state with angular momentum, h, can be described more or less along the lines given in Chapter 5, Section 5. 3. 2. Do this, we may assume, for example, that the atom in question contains a loosely bound electron which can, in an auger-like effect, absorb the energy given off in a transition to the state of lower angular momentum, h. Again, as shown in Chapter 5, Section 5. 3. The probability of transition to such a state will then be proportional to the time t. Let us now suppose, however, the angular momentum is measured by means of a very strong interaction WHICH allows the measurement to take place in a time FLT much less THAN1/LE, where AE is THE energy given off in TH's transition. Without THE measurement, the wave function of this atom would be given by 518, but only for times much longer than 1/AE. For shorter times we may write where XO, RA, represents a wave function corresponding to the zero angle AR. Momentum of the atom, WHILEX, Li, RA, represents a wave function corresponding to an angular momentum, 2. ANDAO, RBT, represents the initial wave function of the Auger particle, and _11, RA, T, represents the change of the wave function of this particle as it begins to move out of the atom. As pointed out in Chapter 5, Section 5. 3. For sufficiently short times this wave function is proportional to the TIME. When THE measuring apparatus interacts with THE atom, we will get where cento, Z, represents the initial wave packet of the apparatus, which will not change for a particle of angular momentum 0, while cent 0, Z plus A, represents the apparatus wave packet corresponding to an angular momentum H. As explained earlier in this chapter, cent 0, Z, and cent 0, Z plus O, do not overlap, so that they determine separate channels into one of which the whole system must end R. If the interaction time with the apparatus is very short, then contribution of this term to the normalization of the wave function will be proportional to T2, since the per TUR bed wave function itself is proportional to T. Suppose then we made a series of measurements, each one in a time FLT. In each of these measurements the probability of getting an angular momentum HIS proportional to FLT, 2, and the probability that it is 0 will be 1, FLT, 2, where / is a suitable constant. As FLT decreases by a factor of 1/n, the probability of transition in a given measurement will be proportional to 1/n2, and in n measurements it will be proportional to 1/n. Therefore, as n increases without limit, the net probability of transition goes to 0. Or in other words, the effect of making repeated measurements of the angular momentum at great speeds is to prevent transitions from taking place. In our interpretation, this behavior is perfectly comprehensible and indeed quite easy to explain. In order for a transition to take place, it is necessary that the perturbed wave function interfering with the original one shall produce a quantum potential that allows the auger-like particle to escape. Otherwise it will simply remain stably in its original station, Airy state. However, if we measure the angular momentum very rapidly, then, as shown in equation 518, the perturbed wave function, which is proportional to t for times much less than L/LLE, will never be large. And furthermore it ca not make a significant NTCO attribution to the quantum potential. For this reason no transition can take place. The behavior described above brings out once again the essentially participatory nature of quantum interaction s. To make measurements in very short times requires very strong interactions, hence very intense participation. The idea of measurement, which implies that we are simply watching what is already there and not participating signify cantly, is seen to be particularly inappropriate in this example. Chapter 7. Non-locality. 7. 1. Introduction. We have seen earlier that non-locality is a basically new feature of the quantum theory, at least in our interpretation. In this chapter we shall go into this topic in more detail, especially with regard to the analysis of the experiment of Einstein, Podolsky, and Rosen, EPR.L. We shall first review briefly how this question is to be treated in terms of the various interpretations, and we shall show that all but one of them imply some form of non-locality. However, it has generally been felt that the very concept of non-locality is unacceptable in a scientific theory, and so people have sought an explanation of this behavior in terms of local hidden variables that would in principle determine the results of each measurement. This leads us then to give a brief discussion of Bell's inequality too, which has to be satisfied by any such explanation, and also of the fact that Bell's inequality is not actually satisfied, either by the predictions of the quantum theory or by the experiments that have been done to test Th's point. We then go on to discuss how our own interpretation deals consistently with these questions by bringing in a non-local connection through the quantum potential. We finally explain the fact that non-locality is not commonly encountered at the large scale level by showing that it is generally difficult to maintain the wave functions that are needed for THs except for certain systems at low temperatures, such as superconductors, and highly isolated systems that have to be produced in a rather artificial way.